Welcome to the Introduction to Networking and Storage course. Whether you're skilling up to become a field technician, network support specialist, virtual customer service agent, or just want to learn the basics of working with and managing computer networks, then you need a strong foundation in networking fundamentals. The most recent U.S. Bureau of Labor Statistics report indicates about 667,000 annual job postings and a projected job growth of 13% through 2029. At the time of this course publication, the median U.S. IT salary was $112,161, more than double the U.S. median salary of $41,950 for all jobs. An IT role is right for you if you like change and enjoy ongoing learning. Computing technology is always evolving, and there's always new technology or a new feature to learn. If you're balancing work-life commitments, many companies offer on-site work, remote work, hybrid work environments, and flexible shifts. Employers need coverage 24 hours a day and 7 days a week. IT careers offer multiple paths for career growth. And if you enjoy making a positive difference for others, an IT role can be rewarding. To successfully complete this course, you should be familiar with basic computer operating skills, basic knowledge of computer terminology, knowledge of switching applications, and have a familiarity with the Microsoft Windows operating system. This course is part of a series of IBM courses intended to help you develop IT fundamental skills and knowledge. When you complete this course, you'll be able to identify wired and wireless network types, explain physical and logical topology, differentiate between network cable types and what each is used for, list common network devices, discover what packets are and how IP addresses work, and explain what protocols are and why models are necessary. Determine how to set up and encrypt networks and mobile devices. Diagnose connectivity issues, and utilize the command prompt and Windows settings. List network drive types, explain RAM, ROM, and RAID, and troubleshoot storage issues. Explain storage as a service, and define file, block, and object storage. When taken as part of the series, this course also helps you prepare for CompTIA IT Fundamentals ITF Plus certification, especially for beginners. Guided instructional videos walk you through key concepts with essential need-to-know facts. Interactive activities reinforce what you've learned in videos, get you applying new knowledge and skills as you learn. Forums provide connections where you can introduce yourself to others, provide feedback, and get support. Practice assessments help you gauge your knowledge, and graded assessments prove what you've learned, leading to a shareable badge and certificate that you can show prospective employers. We're here to support your success, and we're excited that you're here. Let's get started.
Welcome to Types and Topologies. After watching this video, you will be able to define what a computer network is and its purpose, identify the most popular network types, and list the characteristics of the 5 main network topologies. Computer networking refers to connected computing devices like laptops, servers, and smartphones, and an ever-expanding array of IoT devices like security cameras, door locks, doorbells, refrigerators, thermostats, and more. Computer networks enable data transfer and resource sharing through emails, files, documents, databases, and notifications amongst multiple users. There are multiple network types: PAN, or Personal Area Network; LAN, or Local Area Network; MAN, or Metropolitan Area Network; WAN, or Wide Area Network; WLAN, or Wireless LAN; and VPN, or Virtual Private Network. A PAN, or Personal Area Network, enables communication between devices around a person. PANs can be wired or wireless, such as USB, Firewire, infrared, Zigbee, and Bluetooth. They range from a few centimeters to a few meters. PANs are also used to connect laptops, tablets, printers, keyboards, and other computerized devices. One of the most common real-world examples of a PAN is the connection between a Bluetooth earpiece and a smartphone. A LAN, or local area network, is typically limited to a small, localized area, such as a single building or site. A LAN is a group of computers and peripheral devices that share a connection to a server. A LAN may serve 2 or 3 users in a home office or several hundred users in a corporation's central office. LANs enable network devices to share resources like printers or network storage. LANs require cables, switches, and routers so users can connect to internal servers, websites, and other LANs. A MAN, or Metropolitan Area Network, is a network that spans an entire city, a campus, or a small region. MANs are sometimes referred to as CANs, Campus Area Networks. A MAN is optimized for a larger geographical area than a LAN, ranging from several building blocks to entire cities. A MAN is often formed by connecting multiple LANs. Examples of MANs include cable TV networks, telephone networks providing high-speed DSL lines, or any public or free Wi-Fi system provided to residents of a city. A WAN, or Wide Area Network, is a network that extends over a large geographic area. WANs are often established with leased telecommunications circuits. WANs are often used by businesses, schools, and government entities to relay data from almost anywhere in the world, allowing them to carry out daily functions regardless of location. The Internet is an example of a WAN. A WLAN, or wireless LAN, links 2 or more devices using wireless communication to form a LAN within a limited area, such as a home, school, computer lab, campus, or office building. Users can move around within the area and remain connected to the network. Through a gateway device, a WLAN can also provide a connection to the wider Internet. WLANs are used in smartphones, tablets, laptops, and gaming consoles. A VPN, or Virtual Private Network, establishes a private or protected network connection across public networks. VPNs encrypt your Internet traffic, disguise your online identity, and safeguard your data by preventing unauthorized people from eavesdropping. The encryption takes place in real time and ensures that sensitive data is securely transmitted. Topology defines a network's structure, its physical layout, and virtual shape. A network's topology type is chosen based on the specific needs of the group installing that network. Each topology type has its own set of advantages and disadvantages. Physical topology describes how network devices are physically connected. Logical topology describes how data flows across the physically connected network devices. The 5 main types of physical network topology include star, ring, bus, tree, and mesh. Star topology networks feature a central computer that acts as a hub. Each device connects to the central computer with a dedicated cable known as a backbone cable. Star topologies are the most common type used in many networks, large and small. Ring topology networks connect all devices in a circular ring pattern where data only flows in one direction, clockwise. Each device receives and passes on the data until it reaches the intended recipient device, which processes the data. A small office with only a few nodes may use a ring network topology. Bus topology networks connect all devices with a single cable or transmission line. This cable functions as a shared communication channel that devices can tap into without a separate network connection device. Bus topology is the simplest kind of topology used. It is mainly suited for small networks, such as LAN. Tree topology networks combine the characteristics of bus topology and star topology. Tree topology is a type of structure in which all the computers are connected with each other in a hierarchical fashion. An example of a tree topology use case is a university campus in which each building has its own star network, and all the central computers are linked in a campus-wide system. Mesh topology networks connect all devices on the network together. Each mesh network device has a special mesh network software installed so that it can automatically choose the quickest path to the intended recipient. This is called dynamic routing. Mesh topology is commonly used in WAN for backup purposes. This topology is not used in LAN implementations. The Internet is an example of mesh topology. In this video, you learned a computer network enables 2 or more computers to be connected so users can communicate and share resources. There are different network types, ranging from the smallest that cover only a few meters to the largest that span across the whole world. They include PAN, LAN, MAN, WAN, WLAN, and VPN. Network topology defines the structure of a network and its physical and logical types. Network topology types include star, ring, tree, bus, and mesh. Welcome to Wired Connections. After watching this video, you will be able to identify wired connection types, understand which wired connection types are older and which are newer, and list the pros and cons of wired connection types. Older internet connection types that use phone lines are dial-up, cannot use the phone and internet at the same time. ISDN, or Integrated Services Digital Network, transmits data and phone conversations digitally. And DSL, or Digital Subscriber Line, faster than dial-up, can use the phone and internet at the same time. Newer internet connection types are satellite, relies on communication satellites, popular in remote and rural areas. Cable, uses the same coaxial cables as cable television, one of the most common connection types. Fiber optic, relies on fiber optic cables to transfer data with light waves instead of electricity, the fastest connection type. And cellular, uses the same channels as cellular phones, allows connection almost anywhere. Wired networking refers to the use of wire connections that allow users to communicate over a network. Most computer networks still depend on cables or wires to connect devices and transfer data. Dial-up requires a modem and phone line to access the internet, popular in the past but has steadily been replaced by broadband internet services. Pros: available to everyone with a phone line, computer, and modem. Can serve rural or remote areas. Low cost and easy setup. Cons: very slow, unsuitable for gaming or downloading media, and cannot use the phone at the same time. DSL, or Digital Subscriber Line, connects to the internet using a modem and 2 copper wires within phone lines to receive and transmit data, slower than cable and fiber. Pros: faster than dial-up, inexpensive, dedicated connection, provides Wi-Fi, and transmits data using existing phone lines. Cons: slow and weak over long distances. Speed rarely exceeds 100 megabits per second, and not always available. Cable delivers internet via copper coaxial television cable. It is the best option for fast and reliable internet if you don't have access to fiber optic. Pros: uses existing TV infrastructure to reduce cost. High speeds rival pure fiber in ideal implementations. Higher bandwidth than DSL in most cases, and speeds not substantially affected by distance from ISP office. Cons: bandwidth sharing with neighbors is slow during peak times. Upload speeds much slower than download, susceptible to electromagnetic interference, and lower latency than DSL in most cases. Fiber optic cables transmit data by sending pulses of light across strands of glass, up to 200 gigabits per second. Fast, reliable, and consistent. This connection rarely lags, which makes it perfect for HD streaming or online gaming. Pros: efficient, reliable connection, great for long distances, fast speeds, up to 200 gigabits per second. Best for streaming and hosting. Cons: expensive, not available everywhere. In this video, you learned that older internet connection types like dial-up, ISDN, and DSL are low cost and offer low to medium speed. Newer internet connection types, like satellite, cable, fiber optic, and cellular, are higher in cost but offer useful features such as higher speed and mobility. And wired connections like cable and fiber optic have gotten faster and stronger, but older technology like dial-up and DSL still works when you need it. Welcome to cables. After watching this video, you will be able to list the common cable types and their characteristics, understand the purpose of each cable, and identify the most appropriate cable type in varied scenarios. Here are the common cable types: Hard drive cables like SATA, IDE, and SCSI connect a central processing unit, or CPU, to a device's main or default storage. Network cables like coaxial, fiber optic, and Ethernet connect devices and transmit data. Serial cables, like you might find on a keyboard or mouse, are used for transferring power or data slowly over a distance. Video cables like VGA, HDMI, mini HDMI, DisplayPort, and DVI transmit video signals from a device to a monitor. And multipurpose cables, like USB, Lightning, and Thunderbolt, are used for fast data transfers, fast power transfers, and connecting devices. Hard drive cables connect a hard drive to a motherboard or controller card. The same cables may also be used to connect optical drives and older floppy drives. Hard drive cables include SATA, IDE, and SCSI. Serial Advanced Technology Attachment, or SATA, is the next-generation hard drive cable. SATA carries high-speed data and connects to storage devices, hard disk, optical, and solid-state drives. Integrated Drive Electronics, or IDE, is an older interface. The IDE cable is a 40-wire ribbon cable that is connected from the motherboard on one end to one or two drives on the other end. Small Computer System Interface, or SCSI, was designed to support a wide variety of device types. This means there are different types of SCSI cables. They may be ribbon cables or standard round cables of 50, 68, or 80 wires. Up to 16 devices, including the motherboard or SCSI controller card, may be connected to one SCSI cable or daisy-chained together. Multipurpose cables connect devices and peripherals directly together without a network connection. They can transfer both data and power. Multipurpose cables include USB, Lightning, and Thunderbolt. USB cables connect to a wide variety of peripheral devices. USB supports two speeds. Low speed supports data transfer rate of 1.5 megabits per second at lengths up to 3 meters. Full speed supports data transfer rates of 12 megabits per second at lengths up to 5 meters. USB cables can carry data and power. Lightning cables are proprietary to Apple. They are used to connect Apple devices to USB ports. It can carry both data and power to charge the device. Thunderbolt is another Apple proprietary cable. It comes as either copper or optical cable. The maximum length is 3 meters for copper and 60 meters for optical. It provides both data and power to peripheral devices, most commonly storage and display devices. Video cables connect a specific type of video port on a computer to a display. Each has its own connector type. VGA cables connect older analog video graphics adapters to a display. HDMI cables connect a high-definition multimedia interface to a display. There are different types of HDMI cables. Type A is most common, but is usually just referred to as HDMI cable with no type designation. Mini HDMI is an HDMI Type C cable. DisplayPort cables connect a DisplayPort interface to a display. DVI cables connect a digital visual interface to a display. DVI-D, D for digital, supports only digital signals. DVI-I, I for integrated, supports digital and analog signals. There are single-link and dual-link DVI cables. A serial cable is used to transfer information between two devices using the RS-232 standard, which states that data bits must flow in a line, one after another, over the cable. Serial cables are used in modems, keyboards, mice, and other peripheral devices, which is why serial cables are sometimes called peripheral cables. However, video and multipurpose cables are also called peripheral cables for the same reason, even though they might not use the RS-232 standard. In wired networks, network cables connect devices and route information from one network device to another. A network's topology, protocol, and size determine what type of cable is needed. Some networks use only one type of cable, while others use a variety of cable types. Here we will cover 3 types of network cables: coaxial, fiber optic, and Ethernet cables. The coaxial, or coax cable, was originally developed to connect TVs to home antennas. These days, it is used to send cable TV signals to cable boxes and internet to home modems. Coaxial cables contain an inner copper wire that is surrounded by insulation and other shielding. They are highly resistant to signal interference and can support greater cable lengths between network devices than twisted pair Ethernet cables. The coax cable has a 10 megabits per second capacity. The Data over Cable Service Interface Specification, or DOCSIS, is a networking standard used in systems that provide internet across cable TV lines. Coaxial cables use the DOCSIS standard. Fiber optic cables are used in wide area networks, or WANs, because they work over long distances without much interference and can handle a heavy volume of data traffic. Different types of fiber optic cables are used depending on the cost and the amount of bandwidth the cable can support. There are two basic types of fiber cables. Single mode carries only one light path, typically sourced by a laser. It has a much longer transmission distance. Multi-mode carries multiple light paths and is sourced by an LED and can carry multiple signals in the same line simultaneously. Ethernet, or twisted pair cables, consist of 4 pairs of twisted wires to reduce interference. These cables hardwire a computer to a LAN. Hardwiring is faster and more consistent than Wi-Fi. They are available in 2 types: shielded wires or unshielded wires. Unshielded twisted pair, or UTP cables, are cheaper and more common. Shielded twisted pair, or STP cables, are more expensive and designed to reduce any outside interference that might interrupt data transmission. Ethernet cables also have category numbers. A higher category number means the cable is newer and usually faster with better bandwidth. Category, distance, and bandwidth are factors that are considered when building networks using Ethernet. There are many types and categories of Ethernet cables. While all of them use the same connector on both ends, mixing up types can damage cables or hardware. In this video, you learned there are many cable types and each has a specific purpose. SATA cables have the latest hard drive cable technology. Multipurpose cables can be proprietary or universal. Video cables come in a wide variety. Serial cables are used for peripheral devices. And network cables include coaxial, fiber optic, and Ethernet. Welcome to Wireless Connections. After watching this video, you will be able to understand wireless network types and their differences. Identify specific connection examples for each wireless network type, and list the latest networking trends. A wireless network is a network that lets users connect without cables. Wireless networking is when people communicate and access applications and information without being physically plugged in. There are 4 main types of wireless networks. WPAN, or Wireless Personal Area Network, interconnects devices in a short span, generally within a person's reach. WLAN, or Wireless Local Area Network, links 2 or more devices using a wireless distribution method, providing a connection to the wider internet through access points. WMAN, or Wireless Metropolitan Area Network, connects several wireless LANs, generally used to cover an entire city. And WWAN, or Wireless Wide Area Network, covers large areas such as neighboring towns and cities. WPAN is used for peripheral devices. Bluetooth, radio communication that enables low-power, short-distance wireless networking between phones, computers, and other network devices. RFID, or radio frequency identification, communicates using electromagnetic or electrostatic coupling to uniquely identify an object, animal, or person. NFC, or near-field communication, a method of data transfer that allows short-range communication between compatible devices. And IRDA, or Infrared Data Association, a set of infrared communication protocols that provide wireless line-of-sight connectivity between devices. WLAN is used for mobile extension of wired networks. Wi-Fi, radio signal sent from a wireless router. Standards 802.11, A, B, G, N, and AC. Older IEEE standards for WLANs that evolved to become faster and more efficient. 802.11ac, also known as Wi-Fi 5, was introduced in 2013, and Wi-Fi 6, standard 802.11ax, an IEEE standard for WLANs that provides faster throughput speeds, better battery life, and less bandwidth congestion than Wi-Fi 5 technology. WMAN is used for fixed wireless between the Internet and homes and businesses. Proprietary, a vendor-specific wireless municipal network with proprietary standards and equipment. IEEE 802.16, the standardized version of WiMAX with added features like OFDM and quality of service. It was developed in the mid-2000s. And WiMAX, a broadband wireless solution developed in the early 2000s as an alternative to wired DSL or cable, especially in rural areas. WiMAX stands for Worldwide Interoperability for Microwave Access. WWAN is used for mobile access to the Internet from outdoor areas. LTE, or Long-Term Evolution, a converged 4G standard supported by both the GSM and CDMA network providers. In theory, LTE has a maximum downlink of 150 megabits per second. LoRaWAN, or Long-Range Radio, an open standard network that balances low power with long-range communication requirements. And cellular, 4G and 5G, a network based on a collection of cell areas, each with a cell tower at its center that connects to the Internet via satellite. Cellular provides consistent speeds, reliability, and efficiency. Wired and wireless networks have different advantages and disadvantages. The mobility you gain from a wireless network might mean putting up with higher costs and additional security concerns. Wired networks offer more speed and security, but installation may be more difficult. Let's look at the latest networking trends. Wi-Fi 6, standard 802.11ax, is an IEEE standard for WLANs that brings faster throughput speeds, better battery life, and less bandwidth congestion than what you would get with Wi-Fi 5 technology. Network analytics, leveraging AI for smarter insights. When a disruption hits, NetOps teams need the help of advanced analytics to make smart and timely decisions. Network analytics uses AI and machine learning to manage such disruptions and issues. Network automation, automating operations for faster recovery. There's an extraordinary strain on today's NetOps teams, with unprecedented volume in client counts, application traffic patterns, and new use cases like e-learning, video conferencing, virtual events, and remote care. Network automation is critical to ensure continued service and performance. And SASE, Secure Access Service Edge, is a solution for today's combined networking and security challenges, adopted in cloud or hybrid models and in on-premises data centers. In this video, you learned that common technologies like RFID and Bluetooth are commonly used in many WPANs around the world. There are many evolutions of Wi-Fi, with 802.11ax being the latest and most advanced. Cellular works because of the vast regional coverage provided by cellular and LTE WWAN networks. Wireless connections are slower and less consistent than newer wired connections, but wireless connections can be accessed almost anywhere and are easier to install and deploy. And new networking trends include the Wi-Fi 6 IEEE standard, network analytics and automation, and Secure Access Service Edge, or SASE.
Welcome to Advantages and Disadvantages of Network Types. After watching this video, you will be able to define the pros and cons of networking, explain how size and connection type affect a network, and describe the pros and cons of each network type. Computer networking refers to connected computing devices like laptops, servers, and smartphones. Networking has expanded to include Internet of Things devices like security cameras, door locks, doorbells, refrigerators, thermostats, and more. Networks provide communication tools like email and chat and enable the sharing of files and devices like printers, security cameras, and sensors. Networks provide centralized resources like storage databases, which enable bulk software installations, easy backups, and larger storage capacity. Networks allow remote access when you're away from your computer but need to perform a task or get to specific files. Networks also reduce hardware and software costs and enable control over security and access. However, networks also require technical expertise and more maintenance than just one device. Networks are more vulnerable to viruses and hacking, more expensive than using a single device, and require other users and systems to function. Smaller networks are easier to troubleshoot than larger networks. They require less hardware and are easier to secure, upgrade, and manage. Smaller networks are not as flexible as larger networks when it comes to access, resources, and mobility, but they are less expensive. Wired networks have fixed access points, while wireless networks can be accessed from anywhere in the network. Wired networks have less expensive hardware than wireless, but require more devices and cabling. Wired networks are also easier to manage and offer faster connectivity and more security. However, wired networks are less flexible than wireless when it comes to mobility and are also harder to set up and scale. The basic network types can be wired or wireless. From smallest to largest, they are PAN or WPAN, LAN or WLAN, MAN or WMAN, and WAN or WWAN. A personal area network, or PAN, enables communication between devices around a person. PANs are wired and WPANs are wireless. PANs use technology like USB and FireWire. WPANs use technologies like infrared, Zigbee, and Bluetooth. PANs and WPANs range from a few centimeters to a few meters. PANs and WPANs are flexible and mobile, have a one-time easy setup, and are portable. But they also have limited range and limited bandwidth. A local area network, or LAN, is a group of computers and peripheral devices that share a connection to a server. LANs use wired connections, and WLANs use wireless connections. A LAN or WLAN may serve 2 or 3 users in a home office or several hundred users in a corporation's central office. LANs and WLANs enable network devices to share resources like printers or network storage. LANs provide connection via cables, switches, and routers. WLANs provide connection via Wi-Fi signals from Wi-Fi routers, modems, and wireless access points. Advantages include reliability and versatility, high data transmission rates, and they are easier to manage. Disadvantages include smaller network coverage area, the number of devices affects speed, and there are security risks. A metropolitan area network, or MAN, is optimized for a larger geographical area than a LAN, ranging from several building blocks to entire cities. A MAN is often formed by connecting multiple LANs. Examples of MANs and WMANs include cable TV networks, telephone networks providing high-speed DSL lines, or any public or free Wi-Fi system provided to residents of a city. A MAN or WMAN covers multiple city locations, is easy to use, extend, and exchange, and is managed by an ISP, government entity, or corporation. However, it requires special user permissions and has the higher costs and security risks that come with larger networks. Wide area networks, or WANs, provide global coverage. WAN and WWAN examples include the Internet and cellular networks. WANs and WWANs offer global coverage and more security. However, they are expensive and difficult to maintain. In this video, you learned that Networks offer control, remote access, and sharing, but are harder to manage, vulnerable, and depend on other systems. Smaller networks cost less and are easier to learn and manage, but have less power, capacity, and flexibility. Wired networks are faster, more secure, and easier to manage, but require more hardware and offer less flexibility. And each network type has its own pros and cons.
Welcome to Networking Hardware Devices. After watching this video, you will be able to identify common networking hardware devices, list differences between similar network devices, and explain the significance of each type of network device and its functions. Network devices, or networking hardware, are physical devices that enable communication and interaction on a computer network. This includes cables, servers, desktops, laptops, tablets, smartphones, and Internet of Things, or IoT devices. This video covers network devices that connect or route, such as hubs, switches, routers, bridges, and gateways. A server is a powerful computer that stores files and applications. Other computers or devices on the same network can access the server as a central place to store information or use applications. The devices that access the server are known as clients. The server controls the level of access that clients have. A user can access a server file or application from anywhere if they use a client that is connected to the server's network and has the proper level of access, usually password-based. A node is a network-connected device that can send or receive information. A client is a node that accesses the network through a server. All devices that can send, receive, and create information on a network are nodes. The nodes that access servers to get on the network are known as clients. The server controls the level of access that clients have. If a client fails, the network remains unchanged. Client-server networks are common in businesses. They keep files up to date and easy to find by ensuring users work on one shared file in one location. Examples of services that use client-server networks include file transfer protocol sites, or FTP sites, web servers, and web browsers. Peer-to-peer networks are common in homes and on the Internet. Examples include file-sharing sites, discussion forums, media streaming, and voice-over IP services, also called VoIP services. A hub connects multiple devices together in a network. When data is sent to a hub, it broadcasts that data to all devices on the network, except for the one that sent the data. A switch is similar to a hub, except it keeps a table of MAC addresses. When a switch receives any data, it looks up the proper MAC address and forwards the data to the right place. Switches are more efficient than hubs because they only send data to the intended recipient. Switches and hubs connect to modems. If a switch or a hub fails, it brings the entire network down. Routers interconnect different networks or subnetworks. A router serves two primary functions. They manage traffic between networks by forwarding data packets to their intended IP addresses, and they allow multiple devices to use the same internet connection. Routers connect to modems. To direct packets effectively, a router uses an internal routing table, which is a list of paths to various network destinations. The router reads a packet's header to determine its path, consults the routing table to figure out the most efficient path, then forwards the packet to the next network in the path. A modem, or modulator-demodulator, converts data into a format that is easy to transmit across a network. Once that data reaches its destination, the receiving modem converts it back to its original form. The most common modems in use today are cable and DSL modems. A bridge joins two separate computer networks so they can communicate with each other and work as a single network. Bridges can be wired or wireless. Wireless bridges can support Wi-Fi to Wi-Fi, Wi-Fi to Ethernet, and Bluetooth to Wi-Fi connections. A gateway is hardware or software that allows data to flow from one network to another. For example, a home network to the Internet. Gateways are distinct from routers or switches in that they use multiple protocols to connect multiple networks. A repeater, or extender, receives a signal and retransmits it. Repeaters are used to extend a wireless signal so it can cover longer distances or be received on the other side of an obstruction like brick, steel, or concrete. Repeaters connect to wireless routers. A wireless access point, also known as WAP or AP, allows Wi-Fi devices to connect to a wired network. The WAP usually connects to a wired router as a standalone device. The WAP can also act as a central wireless connection point for computers equipped with wireless network adapters. The WAP is plugged into a wired network switch. The WAP reads each computer's MAC address and forwards that to the wired switch. If the wired network is connected to a router with Internet access, the wireless network will also have Internet access. Network interface cards, or NICs, connect to individual devices to a network. NICs can be wired or wireless. Today's computers usually come with wireless NICs already built in. Most include ports for network cables, so users can easily connect their computer to a network. A firewall monitors and controls incoming and outgoing network traffic based on predetermined security rules. A firewall typically establishes a barrier between a trusted internal network and untrusted external network, like the Internet. Firewalls can be either software or hardware. Wireless routers and computer operating systems often have built-in firewalls. A proxy server acts as an intermediary between a LAN and the Internet to minimize security risks. The proxy server evaluates requests from clients and forwards them to the appropriate server if those requests meet preset security requirements. Proxy servers hide an IP address. If an IP address is hidden, it cannot be tracked. Proxy servers save bandwidth. For example, a proxy server will download files or updates for the first user, then keep them stored for any future users who need them. An intrusion detection system, or IDS, monitors network traffic and reports malicious activity to the network administrator. An intrusion prevention system, or IPS, inspects network traffic and removes, detains, or redirects malicious items based on rules set by the network administrator. In this video, you learned network devices, which can be a variety of different types, enable communication and interaction on a network. Servers are powerful computers that store files and applications and are accessed by other computers on the same network. Nodes and clients can be configured in different ways. Routers and modems transmit and convert data to ensure interconnections happen and information reaches its destination correctly. And firewalls, proxy servers, IDS, and IPS work to keep networks secure. Welcome to Packets, IP Addressing, DNS, DHCP, and NAT. After watching this video, you will be able to explain what packets and IP addresses are and how they relate to networking, and explain the importance of DNS and DHCP servers and the NAT process. Everything you do on the Internet involves packets. Every web page that you visit arrives as a series of packets, and every email you send leaves as a series of packets. Packets are also called frames, blocks, cells, or segments. There are 3 data transmission flow types. In simplex mode, the communication is unidirectional, where one of the 2 devices on a link can only transmit but not receive, and the other only receive but not send, like a radio or a keyboard. In half-duplex mode, each station can both transmit and receive, but not at the same time, like a walkie-talkie. In full duplex mode, both stations can transmit and receive simultaneously, like a phone or a messaging app. There are 4 basic transmission modes for IP packets. Unicast, transmission to a single specific destination, used for most Internet traffic such as HTTP and FTP. Anycast, transmission to the closest of multiple nodes that have had the same unicast address assigned to them. Multicast, transmission to all nodes that have subscribed to the destination multicast group or address. Multicast transmission is limited to UDP protocol. And broadcast, transmission to all other nodes on the subnet, for example, to find a DHCP v4 server. Broadcast transmission is limited to UDP protocol over IPv4 only. When you send an email, it is broken down into individually labeled data packets. Each packet travels independently over the network and arrives at their destination in no set order. They are then compiled in the correct order to produce the original message. Internet Protocol version 4, or IPv4, is one of the core protocols for the Internet. It was developed to provide identification for every network device. Internet Protocol version 6, or IPv6, is the newest version of Internet Protocol. IPv6 solves many of the limitations of IPv4, including address space and security. IPv4 only allows around 4.3 billion IP addresses. With all the smartphones, hotspots, and IoT devices, that's just not enough anymore. IPv6 allows over 340 undecillion IP addresses. An undecillion has 36 zeros. IPv6 ensures larger network capacity with added efficiency and security features. An IP address is used to logically identify each device, or host, on a given network. An IPv4 IP address is a 32-bit binary value. It is broken into 4 8-character binary values called octets. Each octet has a decimal value between 0 and 255. Any IP address with any octet higher than 255 is not a valid IP address. An IPv6 IP address is a 128-bit binary value broken into 8 fields, each separated by a colon. Each of the IPv6 binary values are represented by alphanumeric hexadecimal numbers. There are several different types of IP addresses. Static IP addresses are manually assigned. Network servers or network devices that have specific protocol settings often use static IP addresses. Dynamic IP addresses are automatically assigned. They change every time the device connects to a network or changes location. A public IP address is used to communicate publicly outside of the local network. It connects to the Internet. A private IP address is used to connect securely within an internal private network. It does not connect to the Internet. Loopback IP address is the range of IP addresses reserved for the local host address. And reserved IP addresses are addresses that have been reserved by the IETF and the IANA for special purposes. The Domain Name System, or DNS, is the phone book of the Internet. When you type a URL like www.google.com into a browser and press Enter, the browser sends the URL to the DNS server. The DNS server replies with the proper IP address. Your browser will connect to the IP address provided. Because number-only IP addresses are not as easy for people to remember, DNS translates easy-to-remember web addresses to number-only addresses and ensures that both network devices and the people that use them know where they're going. The Dynamic Host Configuration Protocol, or DHCP, automates the configuring of IP network devices. A DHCP server uses a pool of reserved IP addresses to automatically assign dynamic IP addresses or allocate a permanent IP address to a device. DHCP static allocation, the server uses a manually assigned permanent IP address for a device. DHCP dynamic allocation, the server assigns a different IP address to a device each time it connects to the network. And DHCP automatic allocation, the server assigns a permanent IP address for a device automatically. Subnetting is the process of taking a large single network and splitting it up into individual smaller subnetworks, or subnets. Subnetting makes network routing much more efficient, where traffic travels a shorter distance passing through fewer routers to reach its destination. Each subnet mask identifies the boundary between the IP network and the IP host. A subnet mask is like an IP address, but for only internal usage within a network. Routers use subnet masks to route data packets to the right place. Automatic Private IP Addressing, or a PIPA, is a feature in operating systems like Windows that let computers self-configure an IP address and subnet mask automatically when the DHCP server isn't reachable. If a device can reach the local network but not the Internet, chances are the device was assigned an APIPA address. Find out by typing ipconfig into the command prompt. Network Address Translation, or NAT, is a process that maps multiple local private addresses to a public one before transferring the information. Organizations that want multiple devices to employ a single IP address use NAT, as do most home routers. NAT conserves public IP addresses and improves security. When data packets arrive at the public IP address, the NAT instructions send all data packets without revealing the private IP addresses of the intended destinations. That single network device acts as an intermediary between the private network and the Internet. A Media Access Control Address, or MAC address, is the physical address of each device on a network. A MAC address usually consists of 6 sets of 2 digits or characters separated by colons. Technologies like Wi-Fi, Bluetooth, and Ethernet use MAC addresses. A Universally Administered MAC address, or UAA, is uniquely assigned to a device by its manufacturer. A Locally Administered MAC address, or LAA, is assigned to a device by software or a network administrator, overriding the burned-in address for physical devices. MAC addresses handle the physical connection from computer to computer, while IP addresses handle logical network connection routes. In this video, you learned data packets travel in any order across networks to be reassembled at the recipient point. The 3 types of data transmission modes are simplex, half-duplex, and full duplex. IPv4 and IPv6 are core protocols for the Internet, with IPv6 being newer, more efficient, and more secure. Different IP address types are assigned and used for different purposes and security levels. And subnetting allows large networks to split into smaller, more efficient subnets. Welcome to Models, Standards, Protocols, and Ports. After this video, you will be able to explain networking models and standards, list the role of each protocol type, and define common ports. A networking model describes the architecture, components, and design used to establish communication between the source and destination systems. Data packets follow the protocols of network models. There are 2 types of networking models. The OSI, or Open Systems Interconnection Model, is a conceptual framework used to describe the functions of a networking system. The TCP/IP, or Transmission Control Protocol Internet Protocol Model, is a set of standards that allow computers to communicate on a network. TCP/IP is based on the OSI model. The OSI model is a conceptual framework used to describe the functions of a networking system. Data flows across these layers when communicating over a network. The 7 layers of the OSI model include application. Users and applications interact directly with the software application. Presentation. Ensures that data is in a usable format and is where data encryption occurs. Session. Controls the flow of information between different computers, including authentication and reconnections. Transport. Manages the delivery and error checking of data packets. Data is commonly transported using Transmission Control Protocol, or TCP. Network. Responsible for interpreting the addresses and directing the path the data will take. Data link. Defines the format of data on the network. This layer also corrects errors that may have happened at the physical layer. And physical. Electrically or optically transmits raw, unstructured data over a physical medium. The TCP/IP model is a set of standards that allow computers to communicate on a network. TCP/IP is based on the OSI model and functions similarly. The background protocols are still in place, but the way they are organized is slightly different. The data travels through fewer layers on both ends. Networking standards define the rules for data communications that are needed for interoperability of networking technologies and processes. Standards are widely accepted protocols that engineers use to make sure the things they build integrate with existing devices and technology. There are 2 types of network standards. De jure, or formal standard, are formal standards developed by an official industry or government body. Formal standards have gone through formal processes to obtain consensus, including publicly available documentation. Examples include HTTP, HTML, IP, and Ethernet 802.3d. De facto standards result from marketplace domination or practice. De facto standards are accepted in practice but have not undergone any formal process to obtain consensus and may not have publicly available documentation. Typically, de facto standards result from marketplace domination or practice. Examples include Microsoft Windows and QWERTY keyboard. Standards are usually created by government or nonprofit organizations for the betterment of an entire industry. This ensures a broader compatibility across vendors and industries. Some of the well-known organizations that have created network standards are International Standards Organization, or ISO, established the well-known OSI reference networking model. International Telecommunication Union, or ITU, standardized international telecom and set standards for fair use in radio frequency. Defense Advanced Research Projects Agency, or DARPA, established the TCP/IP protocol suite. Institute of Electronics and Electrical Engineers, or IEEE, established the IEEE 802 standards. The World Wide Web Consortium, or W3C, established the World Wide Web, WWW, standard. Finally, the Internet Engineering Task Force, or IETF, maintains the TCP/IP protocol suites. IETF also developed the Request for Comment, or RFC, standard. A network protocol is an established set of rules that determine how data is transmitted between different devices in the same network. Network protocols are typically created according to industry standards. There are thousands of different network protocols, but they all perform one of three primary actions: security, communication, and network management. Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP, are two primary Internet protocols. TCP guarantees sent data makes it to its intended recipient. It's slower and requires more resources. File Transfer Protocol, or FTP, web browsing, and email are typical applications of TCP. UDP doesn't guarantee all packets will arrive, but it's fast and needs fewer resources, good for live streaming, online gaming, and calls over the Internet. The TCP/IP suite is a collection of protocols. Together, these protocols provide a complete networking solution. The Internet of Things, or IoT, network model comprises diverse protocols for communication, which include data collection, data package, data transfer, and data control. The Crypto Classic protocol is designed to serve as one of the most efficient, effective, and secure payment methods, built on the blockchain network. It ensures privacy and transparency of payments directly transferred between two parties who have an address on the blockchain network. Ports are the first and last stop for information sent across a network. A port is a communication endpoint. A port always has an associated protocol and application. The protocol is the path that leads to the application's port. A network device can have up to 65,536 ports. Port numbers do not change. In this video, you learned that networking models describe the design used to establish communication between source and destination, and there are two types of networking models, OSI and TCP/IP. Network standards define the rules for data communication and ensure broader compatibility across vendors and industry. And network protocols are based on an established set of rules that determine how data is transmitted between different devices. Welcome to Wireless Networks and Standards. After watching this video, you will be able to explain the different wireless network types, list the advantages and disadvantages of each wireless network type, and describe the wireless networking standards. As an alternative to traditional cable and fiber optic networks, wireless networks have become crucial for enabling mobility. Wireless networks like WPAN, WLAN, WMAN, and WWAN use radio waves for data transmission and reception instead of wires. And they follow IEEE wireless standards. These are the sets of protocols that define how all wireless communication works. This video describes how wireless networks function and what each one is used for. A WPAN connects devices within the range of an individual person, around 10 meters. WPANs use signals like infrared, Zigbee, Bluetooth, and ultra-wideband. WPANs use the IEEE 802.15 wireless standard. Bluetooth and Zigbee are some of the IEEE 802.15 signals that wirelessly connect devices over short distances. Advantages include flexible and efficient, one-time easy setup, and portable. Disadvantages include limited range, limited data rates, and more expensive. A WLAN connects computers and devices within homes, offices, or small businesses. WLANs use Wi-Fi signals from routers, modems, and wireless access points to wirelessly connect devices. Wi-Fi follows the IEEE 802.11 wireless standard. The latest version of IEEE 802.11ax enables 8K video streaming, data-heavy cloud computing, and virtual reality experiences. Advantages include reliable and versatile, high data transmission rates, and easy to manage. Disadvantages include low network coverage area, number of devices affects speed, and less secure. A WMAN spans a geographic area. It serves ranges greater than 100 meters. Worldwide Interoperability for Microwave Access, or WiMAX, is a family of wireless communication standards that provide WMAN broadband connectivity. There are similar open-source and proprietary broadband technologies, but WiMAX is the accepted suite of standards based on IEEE 802.16. Advantages include covers multiple city locations, easy to use, extend, and exchange, and managed by an ISP, government entity, or corporation. Disadvantages include require special user permissions, less secure, and slower than wired. A WWAN provides regional, nationwide, and global wireless coverage. This includes private networks of multinational corporations, the Internet, cellular networks like 4G, 5G, long-term evolution, or LTE, and LoRaWAN, which is a low-power WAN protocol built on top of the techniques used in long-range radio modulation. Advantages include global wireless coverage, better security than WLAN, and centralized flexible infrastructure like cloud apps and storage. Disadvantages include expensive, difficult to maintain, and decreased coverage over large areas. A wireless ad hoc network, or WANET, uses Wi-Fi signals from whatever infrastructure happens to be available at the time to connect devices instantly, anywhere. WANETs are similar in size to WLANs, but use technology that is closer to WWANs and cellular networks. Advantages include flexible, no required infrastructure, and can be set up anywhere instantly. Disadvantages include limited bandwidth quality, not robust, and has security risks. There are also MANETs, or mobile ad hoc networks, and VANETs, or vehicle ad hoc networks. These are similar to WANETs but have different specifications. A cellular network provides regional, nationwide, and global mesh coverage for mobile devices. Each version below represents a cellular network evolution. 2G supported digital voice and simple data with 64 kilobits per second speed. 3G supported mobile broadband with 2 megabits per second speed, which enabled basic GPS, media downloads, and streaming. 4G advanced speeds and efficiencies with 100 megabits per second speed. And 5G brought 1 gigabits per second speed, which is still bringing cellular networks to a whole new level. Advantages of cellular networks include flexibility, access, and speed and efficiency as it evolves. Disadvantages include expensive, decreased coverage in rural areas, and hardware limitations, like screen size and mobility of peripherals. The IEEE 802.20 and IEEE 802.22 network standards support WWANs, cellular networks, and WANETs. Well-known use cases include emergency mobile operations, internet on airplanes, internet service provider networks, and large-scale monitoring for things like earthquake zones, flood warnings, and space exploration. IEEE 802.20 uses smart antennas to optimize bandwidth for increased coverage or mobility. It is no longer being actively developed, but it is still used to fill the gap between cellular and other wireless networks. IEEE 802.22 uses empty spaces in the TV frequency spectrum to bring broadband to low population, hard-to-reach areas typical of rural environments. In this video, you learned that WPANs use IEEE 802.15 for nearby devices. WLANs use IEEE 802.11 for home or office networks. WMANs use IEEE 802.16 for city or campus networks. WWANs supply regional or global networks. WANets are LAN-sized temporary mobile networks. Cellular networks have evolved over time to become faster and more efficient. And IEEE 802.20 and 802.22 are the standards for WWANs, WANets, and cellular networks.
Welcome to Protocol Table. After watching this video, you will be able to explain the difference between TCP and UDP, describe the relationship between ports and protocols, and list common protocols and their uses. A network protocol is an established set of rules that determine how data is transmitted between different devices in the same network. Network protocols are typically created according to industry standards. There are thousands of different network protocols, but they all perform one of three primary actions: security, communication, and network management. Ports are the first and last stops for information sent across a network. A port is a communication endpoint. A port always has an associated protocol and application. The protocol is the path that leads to the application's port. A network device can have up to 65,536 ports. And default port numbers do not change. Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP, are two primary Internet protocols. TCP guarantees that sent data makes it to its intended recipient. It's slower and requires more resources. Typical applications include File Transfer Protocol, or FTP, web browsing, email. UDP doesn't guarantee that all packets will arrive, but it's fast and requires fewer resources. Typical applications include live streaming, online gaming, calls over the internet. Ports send and receive data using TCP, UDP, and sometimes both. Web page protocols control access and connection between internet users and the sites they visit. Hypertext Transfer Protocol, or HTTP, is responsible for standard internet or web page access. The default port for HTTP is 80. And Hypertext Transfer Protocol Secure, or HTTPS, is responsible for encrypted internet or web page access. HTTPS should be used on a web page that prompts for sensitive data, such as credit card numbers. The default port for HTTPS is 443. File transfer protocols control how data is managed when sent from one location to another. File Transfer Protocol, or FTP, is responsible for file transfer. FTP transfers files to and from an FTP server or client. The default port for FTP is 21. And Secure File Transfer Protocol, or SFTP, is responsible for encrypted file transfer. The default port for SFTP is 22. Remote access protocols enable device control from a remote location. Teletype network, or Telnet, is used to remotely control another device via console or command shell. Telnet lets users configure network devices from almost anywhere worldwide, so long as both devices have network connectivity. However, Telnet should not be used due to data being in clear text, no encryption. The default port for Telnet is 23. Secure Shell, or SSH, is used to remotely control another device via console or command shell securely with encryption. SSH uses encryption to secure remote data. The default port for SSH is 22, which is the same port that SFTP uses, since they both offer similar secured services. And Remote Desktop Protocol, or RDP, is used to remotely control another computer via a graphical user interface, also called GUI, or GUI for short. Email protocols determine how email messages are received, stored, downloaded, removed, or retained. Post Office Protocol Version 3, or POP3, is an older protocol that was the standard for receiving email. With POP3, email is downloaded from an email server to a single device, and then the email is deleted from the server. The default port for POP3 is 110. Internet Message Access Protocol Version 4, or IMAP4, is a protocol responsible for receiving email. With IMAP4, email is stored on the server and synchronized to multiple devices, like laptops and mobile phones. The default port for IMAP4 is 143. And Simple Message Transport Protocol, or SMTP, is responsible for sending email. The default port for SMTP is 25. Network protocols monitor, control, and help the network locate, share, and transfer data. Dynamic Host Configuration Protocol, or DHCP, automatically assigns IP addresses to devices. The default ports for DHCP are 67 and 68. Domain Name System, or DNS, resolves or translates domain names to IP addresses. The default port for DNS is 53. Server Message Block, or SMB, enables sharing files and printers on the network. The default ports for SMB are 137 through 139. Simple Network Management Protocol, or SNMP, monitors the network. The default port for SNMP is 161. And Lightweight Directory Access Protocol, or LDAP, allows directory services to store and authenticate passwords, usernames, and accounts and share them over the network. The default port for LDAP is 389. In this video, you learn that protocols determine how data flows on a network. Ports are the first and last stops on a network. Ports send and receive via TCP, UDP, or both. HTTP and HTTPS are web page protocols. FTP and SFTP are file transfer protocols. Telnet, SSH, and RDP are remote access protocols. POP3, IMAP4, and SMTP are email protocols. And DHCP, DNS, SMB, SNMP, and LDAP are network protocols.
Hello and welcome to Using Your Windows Lab Workspace. We're excited for you to take these next steps in your skills journey. The labs in this course and other courses provide you with a virtual, hands-on lab environment where you can boost your skills by practicing what you've learned in your course videos and readings. Your lab space, also known as a guided project or the My Cloud Workspace window, contains all the software you need to successfully complete your lab tasks. You'll also open a lab instructions file. For your best experience, we recommend displaying your lab space and instructions side by side. To access your hands-on lab, first open the item in the course for the hands-on lab. If the lab instructions display in a new tab, hover over the tab and pull the tab down onto the desktop. You can drag the window edges to resize the window to about 1/3 of the screen size. You'll return to this window later. Return to the course screen and scroll through the displayed course lab instructions. Select the checkbox to accept the Coursera honor code conditions. Then click the Open Tool button. Next, you'll see the Coursera Guided Project window. This window may take a moment to display. The displayed My Cloud Workspace window is divided into two panes. The left pane is named the Cloud Workspace window, and the right pane is named the Instructions window. You won't use this Instructions window. Now, you can expand the Cloud Workspace pane on your screen's left side using one of two methods. Drag the vertical slider between the Cloud Workspace and the Instructions pane to the far right side of the screen, or click the Expand Cloud Workspace window button displayed on the top right of the left pane. Take a moment to view your lab window. You can click the lab window resolution drop-down arrow to adjust the size of the on-screen icons in the cloud workspace. And next, let's adjust your browser windows to see your cloud workspace and lab instructions side by side. On the Cloud Workspace Lab window, hover over the double box icon located in the top right of the browser window to reduce the size of your window. Move the window to the left side of the screen. Now, drag the window's right edge so that the Cloud Workspace Lab window uses about 2/3 of the available desktop space. Next, select the browser window that displays your lab instructions. Drag the instructions window so that the window is to the right of the Cloud Workspace Lab window. Now, you can perform the lab tasks in the Cloud Workspace window while using the lab instructions. After completing the lab, select Leave Session to close the Cloud Workspace window, then close your lab instructions using the option available for your browser. Also, before you begin, here's some extra information you need to know. Each time you connect to these labs, Coursera creates a fresh new environment. Data or files you saved in a previous session are no longer available. To avoid losing your data, plan to complete your lab tasks in a single session. These labs are timed to provide enough time to complete lab tasks, but if you leave the lab session unattended, your lab may time out or end. Now, these setup instructions used a Chrome browser within Microsoft Windows 10. Other browsers and web browsers on Mac or Linux computers may use different navigation. You're now lab ready. Let's get started.
Welcome to configuring a wired SOHO network. After watching this video, you will be able to describe the features of a SOHO network, list the requirements for setting up a SOHO network, and explain how to configure, test, and troubleshoot a SOHO network. A small office home office, or SOHO network, is a local area network, or LAN, with less than 10 computers that serves a small physical space with a small number of employees or home users. It can be a wired Ethernet LAN or a LAN made of both wired and wireless devices. A typical wired SOHO network includes a router with a software-based firewall, a switch with 4 to 8 Ethernet LAN ports, a printer, and several desktops or laptops. SOHO networks often use email, website, and cloud subscription services, since maintenance and reliability are included. Internet is provided via cable, DSL, or ISDN. Basic equipment maintenance is easy since there are only a handful of devices and cables to consider. When setting up a SOHO network, knowing the compatibility requirements is very important. The hardware, software, adapter cards, and cables all need to be compatible for the network to function properly. Before setting up any SOHO network, review and confirm everything in your plan to ensure a successful installation. SOHO networks need a switch to act as the hub of the network. If internet is desired, a router can be added or used instead. SOHO routers often have other integrated features, like a cable or DSL modem, switch ports, and a built-in firewall. A modem provides an internet connection. Ethernet cables provide a wired connection. Category 5, 5E, and 6 cables are the current standard. A router automatically assigns IP addresses to each device on the network, which is necessary if you intend to share your internet connection with all the connected devices. And a SOHO network switch typically allows 4 to 8 connected devices to talk to each other, but does not assign IP addresses or provide internet. Switches are best used to expand the number of LAN ports available on the network, since the number of ports on a router can be limited. Set up the hardware in a SOHO network using the following steps. Plug the switch or router into a power source. Connect the switch to the router, if necessary. If you're using a switch and a router, plug one end of an Ethernet cable into any LAN port on the router, and the other into any LAN port on the switch. This will expand the network to the rest of the LAN ports on the switch. Connect your modem to your router, if necessary. If you're sharing an internet connection from a modem, connect the modem to the WAN internet port on the router. This is usually a different color than the other ports. Connect your computers to open LAN ports. Use Ethernet cables to connect each computer to any open LAN port on your router or switch. Keep devices close to the router or switch since Ethernet doesn't transfer data reliably over long distances, 100 meters maximum. The next steps are to configure router settings. Log in to Router Settings. Enter ipconfig into a command prompt window to find your router's public IP address. It will be listed next to Default Gateway. Enter it into a browser and log in. Update username and password. All routers have default administrator usernames and passwords. Anyone with access can change the admin password or other settings and even lock you out. To improve security, always change the default username and password. Update firmware. Updating router firmware solves operational problems and enhances security. Check the manufacturer website for available firmware updates. Download and install if your firmware is not up to date. As you configure, remember that the model number, revision number, and login defaults are printed on the router or its manual, and that the local or private IP address of any router is usually set to 192.168.1.1. The security of a wired SOHO network primarily depends on a firewall, since all data packets in a wired network travel through secure Ethernet cables. Most broadband routers have a built-in firewall, and additional software firewalls can be installed on individual machines. Servers and hardware have built-in dynamic host configuration protocol and network address translation actions. DHCP servers use IP addresses to provide network hosts, while NAT maps a public IPv4 address to private IP addresses. SOHO network administrators don't have to configure firewall or server settings unless more than a basic setup is required. User account setup is included in most operating systems. Apple or Linux setup steps will vary. In Windows, open the control panel and select User Accounts. Configure your account and settings. Add or configure other users by selecting Manage Another Account. If you wish to add and configure local users and groups, search and select Computer Management, then select Local Users and Groups. In Windows 10 or higher, Device Manager allows you to add devices to a network, set default printers, and more. If the network firewall uses MAC filtering, be sure to modify the whitelist for each authorized client. Network performance depends on internet strength, cable specification, installation quality, connected devices, and network and software settings. Test and troubleshoot to ensure proper network performance. To troubleshoot performance, run security tools, check for updates, restart devices, run diagnostics, reboot the router or modem, and check equipment for damage. In this video, you learned that wired SOHO networks have a router, switch, printer, and connected devices. Compatibility requirements are very important. Physical setup includes connecting the router to the modem and a device to the router. ipconfig shows your router's public IP address. Router settings are configured from a browser, and groups and users are configured through the control panel and computer management tools. Welcome to configuring a wireless SOHO network. After watching this video, you will be able to list the features of a SOHO wireless network, describe how to configure a WAP, SSID, security, and encryption, and explain how to test and troubleshoot a SOHO wireless network. A small office home office or SOHO wireless network is a wireless local area network or WLAN that serves a small physical space with a small number of employees or home users. A SOHO wireless network can be configured with the help of a central wireless access point, or WAP, which can cover a range of wireless devices within a small office or home. SOHO networks often use email, website, and cloud subscription services, since maintenance and reliability are included. Some common broadband types that enable network connection include Dynamic Host Configuration Protocol, or DHCP, which is the most common broadband type. It is used in cable modem connections. PPPoE, or Point-to-Point Protocol over Ethernet, is used in DSL connections in areas that don't have newer options. Static IP is more common in business. DHCP is the easiest broadband type to use. Internet service providers can provide other options if needed. Wireless networks can be set up to be either open or encrypted. Open networks are popular in public spaces because they don't require a password. However, they are easily exploited because anyone can join. Encrypted networks require a password before users can connect. There are different types of Wi-Fi encryption, the strongest being WPA2. A captive portal is a web page pop-up that authenticates users who try to log in to Wi-Fi in places like apartment houses, hotel rooms, and small business centers. However, a captive portal is not a secure connection. On the rear of a typical wireless router, you'll see several connections: a power input jack, one or more wired Ethernet jacks for wired connections. These may include a jack for broadband connection, often labeled WAN or Internet. A USB port, which lets you connect a printer or external hard drive for sharing on the network. And a Wi-Fi on-off button, which allows you to easily enable or disable a wireless network. To manage a router, you must find its default IP address. First, type CMD into the Windows search bar to open the command prompt. Then, type ipconfig in the command prompt window to see IP information for your network. Next, copy the default gateway IP address. Paste it into a web browser and hit Enter. A login will appear. The default router username and password are usually admin. Change these during setup to protect the network. Whenever a change is made, Save Settings must be clicked. After setup, if you cannot access the web, the router is not connected. This is usually caused by choosing the wrong broadband connection type for your service. A Service Set Identifier, or SSID, is the name of a wireless network. This name is chosen during the setup of a wireless network. It's a good idea to choose a unique name to distinguish your router from any neighboring wireless routers nearby. Each country determines the band usage and the available 802.11 modes. The supported modes for the 2.4 GHz band are 802.11, B, G, and N. And the supported modes for the 5 GHz band are 802.11, A, N, and AC. Every router has a default option which supports all types. If you are not sure which modes are supported, select the default one. Most wireless network users will select one of the common forms of secure encryption. Wired Equivalent Privacy, or WEP, was the first security protocol developed. It was retired due to security flaws. It is only in use now when equipment is old or not updated. Wireless Protected Access, or WPA, is stronger than WEP and supports a wide variety of devices. WPA2 is even stronger and is supported on newer wireless devices. WPA2 is the most common and most secure. When you configure your encryption, select the WPA2 security mode. Set your pre-shared key, this is your WPA password. It must be 8 to 63 characters long. Choose a longer, harder-to-guess key for stronger security. Once the router is configured, your wireless network is ready. Users will see it among the available wireless networks when they click the Wi-Fi icon, located at bottom right of PC screens and in the drop-down menu of mobile devices. Test network performance and internet connectivity on each wireless device in the vicinity of the WAP. If needed, troubleshoot performance issues like network lags, glitches, or blocked access with the following actions. First, check the router configuration settings. Next, run security tools. Check for updates. Restart devices, run diagnostics, reboot router or modem, and finally, check your equipment for damage. In this video, you learned that a SOHO wireless network is configured with a central wireless access point, WAP, to cover all wireless devices within a small office or home. DHCP is the most common broadband type over PPPoE and static IP. The ipconfig tool lists the IP address of a host on a network and the IP address of its assigned default gateway. SSID is the name of a network and can be changed in the router settings. And WPA2 is the best encryption choice because it is the strongest. Welcome to Mobile Configurations. After watching this video, you will be able to perform mobile devices basic setup, understand mobile device configuration settings, and apply security features to mobile devices. Setting up a new mobile device is an automatic, easy-to-follow process. Steps will vary depending on make and model, but the general process is outlined below. First, insert your SIM card, turn on your phone, and ensure that it is fully charged. Next, select a language and connect to Wi-Fi. Enter your account details using Google for Android devices and Apple for iPhones. Select desired settings like data backup, location service, and diagnostics sharing. Set the date and time, and set up a pattern, PIN, password, and/or fingerprint. After that, the next steps would be to personalize ringtones, phone sounds, wallpaper settings, and to download and configure apps. Updates to PRI, PRL, and firmware improve mobile device reliability and provide the latest technology and security features. Product Release Instruction, or PRI, are the set of configuration settings for the device's network. Preferred Roaming List, or PRL, tells a device which cell towers to use when roaming. Radio firmware is software that manages connections for cellular, Wi-Fi, GPS, Bluetooth, and NFC. Connection types for mobile devices include both wired and wireless options. Wired connections enable data transfer and charging. Mini USB and micro USB are examples of older wired connectors, and USB-C is the fastest and newest mobile connector. Lightning is an Apple-only connector and is equivalent to USB-C. Wireless connections enable sharing data over short distances. Near-field communication, or NFC, is used for tap-to-pay, to unlock doors, or to share with nearby devices. And Bluetooth is used for sharing audio, video, and other files with nearby devices. Infrared, or IR, is used for remote control capabilities. Mobile devices can be configured to provide network connectivity or to restrict it completely. Tethering enables a phone's cell network to provide service to another device. Hotspot is a broadband access point created by tethering. Airplane mode toggles Wi-Fi, Bluetooth, and cellular on or off. Bluetooth is a wireless technology that exchanges data over short distances. Mobile users can turn on their phone's hotspot to tether other devices to the internet, or they can block connectivity with airplane mode, then turn on Bluetooth to watch downloaded content with wireless headphones. Synchronization lets you transition from one device to another without losing any newly added information. Mobile devices can sync via wired or wireless connection. Cloud Sync lets you collaborate on a work document from a public computer or take a work meeting from your phone. Desktop Sync lets you access phone photos on your desktop or view PC bookmarks on your phone. Vehicle Sync lets you turn your car on remotely or turn your oven off from your car. Single Sign-On, or SSO, lets you use a single ID to log into multiple apps from any device. Tech companies provide SSO to give users easy access to their cloud-synced apps and files. To receive email on a mobile device, configure it to use POP3 or IMAP4. Post Office Protocol version 3, or POP3, removes downloaded emails from the server, and it is better for single-device users. Internet Message Access Protocol version 4, or IMAP4, saves emails on the server so multiple devices can see the same messages. Use protocols like SSL or SMIME to encrypt emails for security and authentication. IMEI and IMSI are used to identify cellular devices and network users when troubleshooting device and account issues. International Mobile Equipment Identity, or IMEI, is a unique number for phones on the GSM, UMTS, LTE, and IDEN networks. It can be used to block stolen phones. International Mobile Subscriber Identity, or IMSI, is a unique number for cell network subscribers. It is usually stored in a device's SIM card. Using VPN on a mobile device provides a secure, private connection over public Wi-Fi. iOS, Android, and Windows 10 devices support VPN. There are many mobile accessories. including headsets, speakers, gamepads and controllers, battery packs and chargers, phone cases, credit card readers, used to process payments using a phone app, and micro SD cards, used to expand storage capacity. Mobile device settings can be configured via the Settings app, which is usually depicted by an icon shaped like a cogwheel or gear. Manage Apps lets you manage, uninstall, and configure data storage locations for apps. Backup lets you store settings, apps, messages, and call history in case of new device or reset. In this video, you learned that basic mobile device setup is easy and automatic. USB-C is the fastest wired type for data and power transfers. Applying updates, VPN, and protocols like S/MIME secures mobile devices. You can use your device as a hotspot to tether other devices to the internet. Synchronization lets you access your apps and files from multiple devices. Settings are configured through the Settings app. And tech support uses IMEI and IMSI to troubleshoot device and account issues.
Welcome to Network Settings in Windows. After watching this video, you will be able to explain where common network resources are in Windows, list network tools available in Windows settings, describe when you would and wouldn't use a network reset. Windows Settings is a key troubleshooting tool. To get to it, type Settings in the Windows search bar. From there, you can select Network and Internet to access related information and tools. You can get to this same location by right-clicking your Start menu and selecting Network Connections. When the Network Status page loads, it shows the network you're connected to. It also shows the Properties button and the Data Usage button. The Data Usage button loads the Data Usage subpage, which shows you how much data each application has used on the network. Here, you can set a data limit and reset usage stats. The Properties button loads the Network and Internet Properties subpage. You can select the Public option to block access from other devices, or select the Private option, making your device shareable when you're on a trusted private network. You can create random hardware addresses to make device tracking difficult, and you can adjust metered connection settings to reduce data usage and set a data limit. The Properties subpage also shows you your network name, the type of Wi-Fi you're on, what network band you're using, your data transmission speed, your IP addresses, and information on your network router. This information is useful in many scenarios. As an example, when you are troubleshooting a network speed problem, you can use Properties to see if your network is on a faster, shorter range 5 GHz band, rather than a slower, longer range 2.4 GHz band. If you're farther away from a wireless signal, a 2.4 GHz band connection is better. Back on the main network status page, you can scroll down to Advanced Network Settings to adjust adapter options, configure sharing settings, and use the Network Troubleshooter tool. You can also get a deeper view into hardware and connection properties, go to Firewall settings, or perform a network reset. Let's take a deeper look at advanced options. The Network and Sharing Center has basic network information and tools like the network name, Network Troubleshooter, and the Advanced Sharing Settings. Advanced Sharing Settings let you choose the level of access each network type has for things like network discovery and the sharing of files and printers. The Network Troubleshooter is an automated tool that detects and helps fix common network problems. With a single click, the Network Troubleshooter automatically searches for network issues and provides solutions or guidance for further troubleshooting. The Hardware and Connection Properties subpage lists the name, type, status, MAC address, DHCP information, default gateway, DNS server, and IP addresses for a device's connections, which can include Wi-Fi, Bluetooth, Ethernet, and more, even when some of those connections are not active. If you want to find out if the IP address for a connection is static or dynamic, this is where you look. Here we see that DHCP is enabled, which means that the IP address is dynamic. the Firewall and Network Protection page has firewall status information and firewall customization settings. You can see firewall status for each type of network you connect to, whitelist apps, adjust notification settings, and configure advanced settings. The Network Reset tool lets you restore original network settings. This can be useful, but should be avoided if a network has a detailed or custom setup, because you may have to reinstall and reconfigure network software and settings after the reset is completed. As you can see, network information and troubleshooting tools are easy to find and work with in Windows settings. From network names to sharing settings, the Network and Internet section has the information and tools you'll need to troubleshoot common network problems. In this video, you learned that the Network Status page shows the SSID and IP address for the connected network and provides tools for troubleshooting and setup. DHCP data and default gateway addresses can be found in hardware and connection properties. Advanced sharing settings let you adjust network discovery and file and printer sharing. Network Reset restores a network back to its original settings. Welcome to Troubleshooting Network Connectivity. After watching this video, you will be able to explain the two main symptoms of network connectivity problems, list the common causes of network connectivity problems, explain how to resolve common network connectivity problems. Can't connect or slow connection are two of the most common network problems. These symptoms can be caused by several different things. Let's explore some of their causes. Here are some common causes of network connectivity problems: cable damage, equipment malfunction, out of range, missing network name or SSID, interference, weak signal, DNS and software malfunction, and malware. Now let's take a look at how to resolve each one. Cable damage slows or stops network connections. The damage can be obvious or hidden from view. To fix this, check for physical damage. Test the cable using different devices or a specialized tool. Replace the cable. An equipment malfunction can slow up or stop network connections. To fix this, check the network adapter drivers in Device Manager. Make sure your switch's port settings are correct in the management software. Or, replace the malfunctioning equipment. When a user is too far away from a wireless signal, their connection will lag or fail. To fix this, move physically closer to the source of the wireless connection. Move the wireless connection source closer to the affected users. Use stronger devices to boost the signal strength. Or use more devices to ensure the Wi-Fi reaches users who are farther away. Network connections can fail when a user can't find the network name, SSID, in the available network list. To fix this, move physically closer to the Wi-Fi source. Reconfigure the network to ensure the SSID is not hidden. Upgrade devices or use compatibility mode on newer networks so older devices can still connect. Note that compatibility mode can slow an entire network down. To correct this, reserve the 2.4 GHz band for legacy devices. Interference is when a radio or microwave signal slows or breaks a wireless connection. To fix this, remove the source of the interfering signal. If on a wireless connection, use a different Wi-Fi frequency. If on a wired connection, use shielded cables to connect. Or, remodel the building with signal blocking materials. When signal strength is weak, a wireless adapter might slow speeds down to make the connection more reliable. This is one reason why fast hardware sometimes lags. If the signal is too weak, the connection may be completely dropped or batted back and forth between multiple weak network signals. This can happen when you are out of range. However, if you are in range but the signal is still weak or the connection keeps dropping, there may be interference from other devices or from physical obstacles made of dense materials like concrete or metal. To fix this, Get closer to the wireless signal. Adjust the wireless frequency channel, or physically realign devices and antennas for better reception. It's important to note that wireless access points should be placed up high and in the middle of the space. Network connections can fail when DNS servers and apps and OSs are configured incorrectly. To ensure proper configuration of the DNS server, run ipconfig in a command prompt. To ensure proper configuration of apps and OSs, use the Network Troubleshooter in Windows Settings. Malware slows or stops network connections intentionally or as a result of overloading a system with other tasks. To fix this, use anti-malware tools in Windows Security, adjust firewall settings in Windows Settings, and configure privacy settings in Windows and in your browser and email applications. In this video, you learn that can't connect or slow connection are symptoms of network connectivity problems. Connectivity problems can be caused by cable damage or equipment malfunction. Wireless connectivity can be affected by range, a hidden SSID, interference, or weak signal. DNS, software configuration, or malware can also cause connectivity problems. Welcome to Network Troubleshooting with Command Line Utilities. After watching this video, you will be able to list the common network-related command line utilities, explain the function of each command line utility, describe how to use each command line utility. The command prompt is very different from Windows settings, but it has many useful diagnostic and troubleshooting features. It provides system information based on the commands a user enters in its command line. To access the command prompt, type Command or the letters CMD into the Windows search bar. Now, let's review a few common command line utilities using the command prompt. Common command line utility commands that you would use to troubleshoot or diagnose network issues include ipconfig, ping, nslookup, traceRT, netstat. ipconfig shows the information and status for network adapters in a system. For configured adapters, ipconfig shows IP address, subnet mask, and the default gateway. If a network adapter is not configured, it will show as media disconnected. The ping utility sends an echo request to another computer to see if an echo reply message is received. You can ping IP addresses or domains. If you ping your computer's loopback address and get a reply, that means your network interface card is working properly. If you ping an IP address or domain and get a reply, that means those locations are reachable from your network. If you ping a domain or IP address that doesn't exist or that isn't connected, you will receive a request timed out message. If nothing is returned, there is no connectivity. Sometimes, not all packets will return, which indicates a possible problem in connectivity. When this happens, re-ping to verify results. nslookup is a command line utility used to find the IP address of a domain or host. nslookup lists the server and IP address used to query the domain, the query domain or host name, and its IP address. nslookup is useful when trying to resolve DNS problems. If you get an error message, then there is a local DNS problem. To verify your results, you can run the same query from a different DNS server. This is done in the nslookup command by adding the different DNS server's address after the domain. The traceRT utility is similar to the ping utility, except that it follows or traces the route a data packet takes to its destination, instead of just tracking start and end points of a connection. traceRT lists where a data packet was sent from, where it was sent to, how many times it was transferred, transfer point locations on the network, and the time limit it took for each step of the route. TraceRT helps you discover where issues are happening on the network and whether network traffic is flowing properly. Be aware that firewalls affect TraceRT tests, often providing a request timeout message. Netstat, short for Network Statistics, is a command utility that shows if a server's email and file sharing ports are open and connecting to other devices. Netstat lists a connections protocol, local address, foreign address, and current state. Netstat is useful when you want to find where a problem is in a network. It identifies errors and provides robust diagnostics information that can be used in further troubleshooting. In this video, you learn that ipconfig lists the device's IP address, subnet mask, and default gateway. Ping checks to see if data can be sent and received. NSLOOKUP shows the IP address of a domain. TraceRT traces the route a data packet takes to get to a destination. Netstat shows if a server's email and file sharing ports are open and connecting to other devices.
Welcome to Types of Local Storage Devices. After watching this video, you will be able to list the difference between RAM and ROM, identify the different types of storage drives, and explain the differences between storage drives. Random access memory, or RAM, and read-only memory, or ROM, are computer hardware chips that store data. RAM, or volatile, cache, or temporary memory, fetches data at a high speed, only stores data for a short time, and automatically deletes data if the device is shut off. ROM, or non-volatile memory, fetches data at slower speeds, stores larger amounts of data for as long as needed, and keeps data even if the device is shut off. RAM is used for copy-paste, opening programs, and background processes. ROM is used for computer booting and process initialization. A hard drive, or hard disk drive, also called HD or HDD, is a storage drive made of spinning magnetic plates and a read-write head that reads or writes data. HDDs are known for having a large storage capacity, speeds up to 200 megabytes per second, and a tendency to overheat. HDDs were the standard PC storage for decades. They are best for large archival activities. A solid-state drive, or SSD, is the fastest storage option. It has no moving parts, doesn't need power to retain data, and can read, write, and fetch faster than any HDD, up to 7,000 megabytes per second, as opposed to 200 megabytes per second with HDDs. SSDs are the new standard for PC storage. They are small, fast, and durable, but also expensive with limited capacity, and they can fail suddenly. SSDs are best for activities that require speed, like browsing online or editing large files. Solid-state hybrid drives, or SSHDs, integrate the speed of an SSD and the capacity of an HDD into a single device. It decides what to store in solid-state versus hard disk based on user activities. SSHDs are faster than HDDs, offer better performance than HDDs, cost less than pure SSDs, and have higher capacities than SSDs. Hard drives and solid-state hybrid drives are sometimes referred to as spinning drives because they use spinning plates to read, write, and fetch data. Optical disc drives, or ODDs, read, write, and store data on optical discs like DVDs, CDs, and BDs, or Blu-ray discs. Optical disc drives use a laser to reflect light off a disc's surface so it can read the reflected light. The process is reversed when writing data to a disc. Optical disc drives are also called CD drives, DVD drives, BD drives, disk drives, and optical drives. Optical drives are best for reading large media files stored on disks. Flash drives store data on solid-state drives. Less energy is needed to run flash drives as they don't have moving parts that require cooling. High-end versions deduplicate and compress data to save space. Flash drives are small, fast, and inexpensive to run, but they have smaller capacity than hard disk drives and are expensive to purchase. Flash comes in multiple form factors, including USB thumb drives and digital memory cards. Flash is best for activities that require speed, like browsing online or editing files. In this video, you learned that RAM is used for fast, short-term computer memory, and ROM is used for slower, longer-term computer memory. SSDs are faster and more efficient than HDDs. Hybrid drives offer the speeds of SSDs with the high capacity of HDDs. And optical drives can read or write to disks like CDs and Blu-rays. Welcome to local storage with multiple drives. After watching this video, you will be able to list the difference between SSHDs and hybrid disk arrays, define ephemeral storage, and explain how RAID works. Hybrid disk arrays physically combine multiple SSD and HDD devices into an array of drives working together to achieve the fast and easy performance of solid-state and the lower costs and higher capacities of hard disk. Hybrid disk arrays are small, fast, have lower setup costs than pure flash, but they also have performance concerns and are complex to manage and maintain. Hybrid disk arrays are best when you want both fast speeds and high capacity. Direct Attached Storage, or DAS, is one or more storage units within an external enclosure that is directly attached to the computer accessing it. A DAS can contain hard drives, solid-state drives, and optical disk drives. DAS is best for small to medium networks with moderately high storage needs. External drives are portable DAS that connect to your computer via USB. In DAS units and other storage devices, you can configure storage settings to be ephemeral or persistent. Ephemeral storage deletes saved data on restart. It resets things back to their original state, even if settings, updates, and files are adjusted and saved. It is used in things like application demos and OS restarts in computer labs. Persistent storage keeps saved data on restart. It behaves like the storage you're used to in your everyday computer. It is used in things like personal computers and network archives. Most storage drives are configured to use persistent storage. A redundant array of independent disks, or RAID, spreads data across multiple storage drives working in parallel. RAID 0, or striping, splits data into storage units called blocks and stores those across two or more drives in an array. RAID 0 is fast, has 100% usable disk capacity, but not fault-tolerant. If one drive fails, all data is lost. RAID 0 is popular with gamers and photographers who need to save large amounts of data quickly. RAID 1, or mirroring, copies and stores data twice across two or more drives. RAID 1 cuts space to 50% usable capacity, and if one drive fails, no data is lost. RAID 10 combines RAID 0 and RAID 1. It stripes or spreads data across drives that are part of the array. RAID 10 is fast, fault-tolerant, and if 3 drives fail, all data is lost. RAID 5, or striping with parity, is the most common form of RAID. It splits data into blocks and stores those across 3 or more drives. If data loss occurs, the computer will recalculate the lost data using error-checking tags, known as parity bits, that it has stored across the drives. RAID 5 is fast, fault-tolerant, and if one drive fails, no data is lost. RAID devices can use SSDs, HDDs, and hybrid drives. Companies choose RAID devices for their durability and performance. Multiple drive failure is rare, but it happens. Maintaining RAID devices, keeping spare drives handy in case of drive failure, and having a backup routine will make data loss nearly impossible. In this video, you learned that hybrid disk arrays combine SSDs and HDDs for fast performance, high capacity, and low costs. DAS are external storage drives directly attached to a computer for additional storage capacity, or if you need a different storage interface. Ephemeral storage deletes saved data on restart. Persistent storage keeps saved data on restart. And RAID devices use multiple drives in different configurations to prevent data loss.
Welcome to Troubleshooting Storage Issues. After watching this video, you will be able to describe common causes of storage failures, explain the troubleshooting steps for various storage types, investigate and resolve slow performance. Disk failure or hard drive failure can be caused by wear and tear over time, faulty manufacturing, or power loss, especially when the disk is reading or writing. Here are some symptoms of disk failure. With read-write failure, you get an error message when you open or save a file. Blue screen of death, or BSOD, is a system stop error caused by a severe read-write failure. A bad sectors error means that part of a disk is unreliable and needs to be fixed. Constant LED activity, or disk thrashing, may indicate insufficient RAM, with data moving back and forth between RAM and the hard disk. A clicking or grinding noise is a sign of a problem. When you see these symptoms, replace the disk to avoid data loss. The Check Disk tool and the SMART program are used to monitor and troubleshoot disk health. SMART, or Self-Monitoring Analysis and Reporting Technology, can be set to send an alert when a disk is unreliable. Check Disk tools find bad sectors and fix symptom errors. A Check Disk run test, checkdisk/r, locates bad sectors each time it is run. You can use Check Disk Fix, checkdisk/f, to fix file system errors, but it won't find bad sectors. Additional diagnostic programs are available from software and hardware vendors or may come prepackaged with certain systems. When a computer fails to boot, the first step is to check for lights and sounds associated with power up. If these don't come on, check to see if the device is plugged in. If the device powers up but still does not boot, check the drive configuration to ensure that firmware system setup has the correct boot sequence and no removable disks are present. Data cables are connected to the drive correctly and free from damage. Motherboard port is not disabled by system setup. If the drive configuration is fine, it may be a file system error. Use the Windows setup disk to boot into the recovery environment and enter C: in the command prompt. If it says invalid media type, try the bootrec tool or reformat the disk. Erases all data. If it says invalid drive specification, check the partition structure with diskpart. Errors like invalid drive specification or OSS not found indicate boot errors. Boot errors are caused by disk corruption, incorrect OS installation, or viruses. To resolve, try your antivirus software's boot disk option to detect potential viruses. Then, use the antivirus software's recovery disk option if available. If the problem persists, boot with the original product disk and choose Repair. Try Startup Repair first, or use the command prompt to try fixing MBR, try fixing boot sector, or to try correcting missing installations in the boot configuration database. Then, restart. For computers that won't boot, you can try to recover files by removing the hard drive and connecting it to another computer. External enclosure kits let you secure the removed drive and connect it to other computers using a USB cable. If possible, inspect and recover the drive's files via Windows Disk Management, or use Check Disk to restore fragments of corrupted files. But keep in mind that third-party file recovery software may work better. Disk performance can slow if a disk is older, too full, or its files are not optimized for fast access. To improve performance, defragment the drive for faster file access. Add RAM. Upgrade to a solid-state drive or hybrid drive. Remove files and applications. Or add additional drive space. Optical drives are laser-based and don't physically touch disks. Here are some useful optical drive tips. Cleaning kits can often resolve common read-write errors. CD-ROM drives cannot read DVD-ROM discs. Third-party software is available for DVD and Blu-ray disc support. Writable discs have recommended write speeds that affect quality and vary depending on the brand. When the OS is too slow for the optical drive's write process, buffer underrun, errors occur. To fix this issue, use the latest CD and DVD writers. Burn at a lower write speed. Close all other applications when burning. Or copy data to the hard drive instead of to the disk. Here are some common RAID troubleshooting steps. If a RAID array is not detected at setup or boot, ensure RAID controller drivers are installed and verify status. If the configuration tool is unavailable, the controller may have failed. If a RAID disk fails, you will get an alert. If the RAID array supports redundant drives and hot swapping, just insert a new drive and then rebuild the array with the configuration tool. Performance is impacted during the RAID array rebuilding process, as it commonly involves large data transfers. Take care to only remove the failed disk. Removing a healthy disk can also cause a RAID array to fail. If too many disks fail, use backup and recovery solutions. A non-redundant RAID failure, like RAID 0, means both disk and data are lost. If the controller fails, install a new controller or import the disks into another system. In this video, you learn that disk failure is caused by faulty manufacturing, wear and tear over time, or power loss. Disk integrity is checked with Check Disk and Smart. In boot failure, first, check for power-up, lights and sounds, then drive configuration. Space, RAM, or new drives improves performance. Fast write speeds cause optical drive errors. Rebuilding a RAID array slows performance. Removing a healthy disk can cause RAID failure.
Welcome to Types of Hosted Storage and Sharing. After watching this video, you will be able to explain how storage as a service works, describe what a repository is and how it's used, and list the benefits of Active Directory. Storage as a service, or SaaS, is when companies sell network storage space to customers. This saves their customers from having to purchase and maintain network equipment. Dropbox, OneDrive, Google Drive, Box, and Amazon Drive are all examples of storage as a service. Most email today is stored in the cloud. Companies store your data, emails, and attachments in their data centers. The same is true for social media storage. Companies store your photos, videos, and messages in their data centers. Security and data retention policies vary. Gmail will recover deleted email for 30 days before permanent removal. Facebook deletes after 90 days, but keeps certain user data indefinitely. A work group or home group is a group of computers on a Soho network, typically without a server. To share files and folders, users set them to public. Data is stored on the user device that created it. The added points of failure create higher risk of data loss. Newer cloud solutions provide the same features more securely. Work groups and home groups are less common. Home groups have been removed from Windows 10 altogether. A repository is a network location that lets users store, manage, track, collaborate on, and control changes to their code. Repositories save every draft, and users can roll things back if problems occur. This can save software developers months of time. Examples of repositories include GitHub and Docker Hub. Active Directory is a Microsoft technology that manages domain elements such as users and computers. It organizes domain structure, grants network access, and connects to external domains. It can be managed remotely from multiple locations. Active Directory Domain Services, or ADDS, are the core services behind Active Directory. ADDS stores centralized data and manages communication and search, authenticates users so they can access encrypted content, manages single sign-on user authentication, and limits content access via encryption. Network drives are installed on a network and shared with selected users. They offer the same data storage and services as a standard disk drive. Network drives can be located anywhere. They can be in the same room as a network user or thousands of miles away. Network drives appear alongside local drives. Network drives can be installed on computers, servers, NAS units, or portable devices. File and printer sharing is part of the Microsoft Network service. It allows computers on the network to access shared files and printers. Network drives appear alongside local drives or are accessed via a web browser. Network printers appear in the Printer Options pop-up. In this video, you learned that Storage as a Service, or SaaS, allows users to benefit from a robust network infrastructure without having to first build and maintain it. Software developers use repositories to store and collaborate on code and have all drafts saved in case they need to revert to an earlier version. Active Directory organizes domain and network elements and manages access to content. And network file and print sharing provides common central resources to users on a network. Welcome to Network Storage Types. After watching this video, you will be able to explain what a SAN does, explain what a NAS does, and list the differences between NAS and SAN. Network storage is digital storage that all users on a network can access. Small networks might rely on a single device for the storage needs of 1 to 5 people. Large networks, like the Internet, must rely on hundreds of data centers full of servers. A storage area network, or SAN, combines servers, storage systems, switches, software, and services to provide secure, robust data transfers. SANs have better application performance, are central and consolidated, are off-site so data is protected and ready for recovery, and include simple, centralized management of connections and settings. A network-attached storage, or NAS device, is a local file server. It acts as a hard drive for all devices on a local network. NAS devices provide convenient sharing across network devices, better performance through RAID configuration, remote access, and they work when the Internet is down. A NAS is a connected storage device that is local to the network it serves. A SAN is a storage system that involves many devices and connections across multiple sites. NAS devices are attached to a single site, less expensive, easier to manage, they appear as a network-attached drive, use Ethernet, do not scale, and have a single point of failure. SANs can span multiple sites, are more expensive, harder to manage, they appear as a local drive, use fiber, are easily scalable, and are fault-tolerant. In this video, you learned that NAS is a local device that acts as a file server for all devices on a local network. A SAN is a complete networking system that enables efficient and secure storage. And NAS and SAN are different because NAS is local to its network, while a SAN is a storage system that spans multiple offsite locations and involves many devices, servers, and connections. Welcome to cloud-based storage devices. After watching this video, you will be able to explain how file, block, and object storage differ, identify the 3 types of storage gateways, and list which storage is best for large backups. Cloud storage is when files and applications are stored and engaged with via the Internet. Cloud companies manage data centers around the world to keep applications functioning properly and user data stored securely. Multiple cloud offerings have different features depending on each user's needs. The public cloud provides off-site storage for Internet users. The private cloud provides collaboration and access to private network users. and the hybrid cloud is a mix of both. It provides public sharing and restricted private areas via cloud storage and cloud-hosted apps. Cloud companies use multiple data storage types depending on how often they need to access different data and the volume of that data. File storage saves all data in a single file and is organized by a hierarchical path of folders and subfolders. File storage uses app extensions like .jpeg or .doc or .mp3. File storage is familiar and easy for most users, has user-level customization, is expensive, and is hard to manage at larger scales. Block storage splits data into fixed blocks and stores them with unique identifiers. Blocks can be stored in different environments, like one block in Linux and the rest in Windows. When a block is retrieved, it's reassembled with associated blocks to recreate the original data. Block storage is the default storage for data that is frequently updated, is fast, reliable, and easy to change, has no metadata, is not searchable, and is expensive, and it's often used in databases and email servers. Object storage divides data into self-contained units stored at the same level. There are no subdirectories like in file storage. Object storage uses metadata for fast searching. Each object has a unique number. It requires an API to access and manage objects. Is a good choice for large amounts of unstructured data, and is an important storage option for AI, machine learning, and big data analytics. A storage gateway is a service that connects on-premises devices with cloud storage. There are 3 types of storage gateways. A file gateway is a file server in the cloud that stores data files using the S3, NFS, and SMB protocols. S3, or Simple Storage Service Protocol, enables the storage of block data in categories called buckets. NFS, or Network File System Protocol, enables server-to-server file sharing. And SMB, or Server Message Block, enables file and print sharing for network users. A tape gateway is a backup server in the cloud. It uses the S3, Glacier, and Glacier Deep Archive protocols to store virtual tape backups. Glacier and Glacier Deep Archive protocols enable secure and durable cloud archive storage at a lower cost than other storage solutions. Glacier features instant archive retrieval, where Glacier Deep Archive features 12 to 48-hour data retrieval. A volume gateway uses the Internet Small Computer System Interface, or iSCSI protocol, which enables on-premises applications to transfer block data to cloud storage over TCP/IP networks. Volume gateways have 2 modes, cached and stored. Stored mode creates S3 backups of all locally stored content for recovery purposes. Cached mode is just like stored mode, except it only keeps frequently used data on premises, which requires much less infrastructure. Archival storage moves data out of regular production file areas into long-term storage. Archival storage can be easily accessed and brought back into regular use. It can be done with tape drives, which are best for large backups, flash storage, hard drives, and cloud solutions. It is low cost and high capacity. Backups are copies of files, operating systems, settings, and more that are stored in a separate location in case of disk failure or data loss. Snapshots do the same thing as backups, but are usually used in storage arrays, or SANs, at an enterprise level and are more focused on capturing a point in time. All snapshots start off with a full backup. A full backup or snapshot copies everything on a disk selected for backup. A differential backup or snapshot copies only the files that changed since the last full backup. An incremental backup or snapshot copies only the files that changed since any backup. They can be automated or manual. If you delete the original instance of the data, only manual backups are retained. With important data, it is best to keep 3 backups or snapshots saved locally and in the cloud. Sometimes data can get corrupted. Backups and snapshots should be tested periodically to ensure they are still able to restore the data. In this video, you learned that object storage is used in AI and machine learning because it's good for large amounts of unstructured data. Block storage is used in databases and email servers because it's fast, reliable, and easy to change. The three types of storage gateway are file, tape, and volume. Tape drives are best for large data backups. And the three types of backups are full, differential, and incremental.
Welcome to the IBM Technical Support Professional Certificate. Did you know that industries worldwide depend more on technology now than ever before? That's because more people are using technology in their everyday lives, including working remotely, taking online classes, and even having health checkups with a doctor via webcam. With a worldwide increase in demand for technology comes an increase in need for user support for all technology-related needs. Who will provide technical support to individuals, companies, and organizations? Professionals who are knowledgeable in the fundamentals of computer hardware, operating systems, software, networking, storage, cybersecurity, and cloud computing. According to the most recent U.S. Bureau of Labor Statistics report, about 70,400 computer support jobs are posted annually in the U.S. alone, and job growth in the computer support industry is projected to increase 9% through 2030. At the time of this course publication, the median U.S. computer support specialist salary is $57,910 US annually, and per hour pay is almost $28 US. Technical support jobs are also a great way to start on your path to a high-paying career in information technology. This certificate consists of several engaging and informative courses designed to introduce you to the fundamentals of technical support as well as information technology fundamentals. Additionally, this professional certificate can help you prepare for the CompTIA IT Fundamentals Certification exam. This is a beginner-level certificate, which means that anyone, even if you're new to IT, can take this course. You don't need prior experience in IT or technical support. No college degree is required. All you need to get started with this certificate is a willingness to learn and a basic computer literacy to take online courses through your web browser or mobile app. The courses in this certificate will introduce you to the essential parts of IT. You will learn about hardware, software, networking and cybersecurity, cloud computing, ticketing systems, and careers and pathways in IT. Throughout the courses, you'll hear from IT insiders as they share their experiences and what they've learned as they've progressed through their careers. Some of the experts you'll hear from are Aditya Pundir, an IT manager, Michelle Sanchez, an instructional designer who started in help desk, Mike Schwartz, who works in IT support, and Amy Taylor, an enterprise support technician. You will learn in this course through guided instructional videos that walk you through key concepts with essential need-to-know facts. Interactive exercises will reinforce what you've learned in videos. Insider viewpoints allow you to learn from professionals working in many fields of IT. And practice assessments and graded assessments will help you gauge your knowledge and prove what you've learned. Upon completing all of the courses, you'll earn a shareable badge and the IBM Technical Support Professional Certificate. Why do you need a professional certificate? A professional certificate is beneficial for you because it's proof of your knowledge and accomplishments. The IBM Technical Support Professional Certificate has been specifically created to focus on the core knowledge you will need to possess to succeed in technical support and beyond. The courses work together to familiarize you with the elements of IT, introduce you to hardware and software, help you build your IT skills, and provide you with hands-on labs to practice using what you've learned in the course. When you've completed the courses in the certificate, you will receive a professional certificate so that you can share your hard work and accomplishment with potential employers and your professional network. One of the many benefits of the IBM Technical Support Professional Certificate is that all of the courses are online and ready to start when you're ready to take them. The courses have flexible schedules, meaning you can complete the course at whatever time is most convenient for you and at your own pace, even if you have only 2 to 3 hours a week to spare. Or you could even complete the entire professional certificate in as little as 3 months if you've spent 5 or more hours per week on the courses. Financial aid is available for those who qualify. So, if you are not sure this program is right for you, you can try a free 7-day trial or you can audit the courses. These options give you the opportunity to sample the content and determine if the courses are right for you. And remember that we're here for your success. If you have any questions about the courses or the professional certificate, just ask. So, what are you waiting for? Let's get started. Welcome to the IBM Technical Support Professional Certificate Overview of Courses. This certificate includes introductory courses on technical support, hardware and operating systems, software, programming and databases, networking and storage, cybersecurity essentials, and cloud computing. The certificate also includes the final course, Technical Support Case Studies and Capstone, to apply your knowledge and skills. The course, Introduction to Technical Support, describes many support essentials, including the roles and responsibilities of technical support professionals, career pathways and progressions in information technology or IT, support tools, ticketing systems, technical skills, and soft skills, all of which are needed to succeed in IT support. In Introduction to Hardware and Operating Systems, you'll learn about internal hardware computer components, including motherboard components, central processing units or CPUs, hard drives, and expansion slots. You'll also learn the essentials of basic workstation setup, commonly used operating system settings, screen capture commands, and effective troubleshooting practices. In the Introduction to Software Programming and Databases course, you'll learn about software, web browsers, software development, programming languages, and database management. In Introduction to Networking and Storage, you'll learn how to diagnose and repair basic networking and security problems. You'll also learn about network types and standards, wired and wireless connections, and common network storage and network sharing options. In Introduction to Cybersecurity Essentials, you'll learn about the fundamentals of cybersecurity. You'll also learn how to recognize common security threats and risks, examine the characteristics of cyber attacks, and explore methods for securing and managing confidential information. In the course Introduction to Cloud Computing, you'll discover the many elements of cloud computing and how cloud computing is changing the world of technology. You will identify various cloud service models, deployment models, and key components of cloud infrastructure. You'll also learn about cloud security, monitoring, emerging trends, and job roles in the cloud industry. And finally, in the Technical Support Case Studies and Capstone, you will apply your knowledge and skills to practical IT support scenarios. You will also complete a final exam designed to prepare you for the CompTIA IT Fundamentals Certification exam. Are you ready to begin your journey toward becoming a technical support professional? Start on your first course today.
Welcome to Security Threats, Confidentiality, Integrity, and Availability. After watching this video, you will be able to explain what the CIA triad is, list concerns related to the CIA triad, and define common regulatory standards and penalties. A comprehensive security program must include confidentiality, integrity, and availability. These are known as the CIA triad. Confidentiality means that data is protected from unauthorized access. Integrity means that data is protected from unauthorized changes. And availability means that you have access to your data whenever you need it. When confidential data is exposed beyond the intended audience, it causes risk. Confidential information is kept secret to prevent identity theft, compromised accounts and systems, legal concerns, damage to reputation, and other severe consequences. To determine if data should be confidential, ask, who is authorized? Do confidentiality regulations apply? Are there conditions for when data can be accessed? What would the impact of disclosure be? Is the data valuable? Cybercriminals are always after sensitive information or personal data. To keep confidential data secure, control data access and use security tools like encryption and multi-factor authentication, or MFA. Data is one of the most valuable assets a company can have, but it is not static. It can be transferred to other systems, altered, and updated multiple times. Data integrity guarantees that data is accurate, complete, and consistent. It covers data in storage, during processing, and in transit. Without data integrity, loss, corruption, or compromise can cause significant damage and financial loss for both businesses and customers. The two main types of data integrity are physical and logical. Physical data integrity is the collection of actions and fail-safes that protect the physical systems that store and process the data. Logical data integrity are the checks and protocols that protect data from human error and hackers. These confirm that data is correct and accurate as it is used in different ways within an organization. Data availability means that authorized users have immediate and reliable access to their data. This includes granting access to authorized users with passwords and security questions. Some of the most fundamental threats to availability are non-malicious, including hardware failures, unscheduled software downtime, and network bandwidth issues. Malicious attacks against availability include various forms of sabotage intended to cause harm to an organization by denying users access to the information system. One such example would be a DOS, or denial of service attack, where a website or server is targeted with so much traffic that it overwhelms that system, degrading performance until the server is unable to respond. To protect against these threats, systems that require high availability, 99.999% uptime, have network monitoring, redundant hardware, and backup servers ready to take over. If the primary system is compromised, business continuity and customer access can be maintained. There are regulatory standards, contracts, and local laws that companies and organizations must follow to secure and maintain data. The Health Insurance Portability and Accountability Act, or HIPAA, regulates the use and disclosure of protected health information in America, and the General Data Protection Regulation, or GDPR, regulates digital privacy for all countries in the European Union. Fines and penalties for non-compliance help companies keep data safe, secure, accurate, and private. In this video, you learned that the CIA triad is confidentiality, integrity, and availability. Breaches and data loss can result in financial losses for both consumers and companies. Regulations like HIPAA and GDPR help to keep data safe, secure, accurate, and private. And non-compliance or repeated violations of privacy regulations can result in hefty fines and penalties. Welcome to Security Threats, Security and Information Privacy. After watching this video, you will be able to define intellectual property, explain how to turn data into information, and list the different types of confidential information. An information asset is information or data that is of value. Examples include patient records, customer information, and intellectual property. Information assets can exist physically on paper, disks, or other media, or they can exist electronically in databases and files. Data analytics is when raw data, like values or facts, are used to create meaningful information. Data is the raw values and facts, usually collected by automated systems. For example, page visits, link clicks, monthly sales. Information is a summary of the raw data. For example, positive or negative results that happen after some specific change. Insights are conclusions based on the results of information analysis. Meaningful business decisions are based on insights. For example, if a positive trend occurs after store hours are changed, the right business decision would be to maintain those new hours. Intellectual property, or IP, refers to creations of the mind and generally are not tangible. It's protected by copyright, trademark, and patent law. Industrial designs, trade secrets, and research discoveries are all examples of IP. Even some employee knowledge is considered intellectual property. Companies use a legally binding document called a non-disclosure agreement, or an NDA, to prevent the sharing of sensitive information. Digital products are non-tangible assets a company owns. Examples include software, online music, online courses, ebooks or audiobooks, and web elements like WordPress or Shopify themes. A company must protect digital products from piracy and reverse engineering. Source codes, licenses, and activation keys also need protection from hackers and insider threats. Digital Rights Management, or DRM, is code added directly to files that helps prevent digital assets from being copied or pirated, but there are tools that can remove DRM code. The Digital Millennium Copyright Act, or DMCA, makes it illegal to bypass copy protections or to develop technology that helps bypass copy protections. Data-driven business decisions help companies respond to real events. For example, sales and marketing data helps identify trends and customer interests, and production and fulfillment data helps identify productivity issues in areas like manufacturing, billing systems, transportation, and more. Getting the right information is key to data-driven business decisions. Data capture is the collection of data from multiple sources and the secure storage of it in relational databases, or more commonly, semi-structured data warehouses. Data may be captured by server logs showing where customers browse, IoT sensors in home appliances and business technology, and customer and employee surveys or rating systems. Data correlation is when raw data points are analyzed to find connections or links. For example, Netflix uses tools that compare searches, views, and ratings so they can predict which movies and shows will be successful on their platform. AI and machine learning algorithms automate parts of the analysis. Meaningful reporting is the presentation of analyzed information in ways that help people further analyze and interpret. Reporting tools use captured and correlated data to provide charts, keyword search, and graphs that help companies achieve business insights. Confidential information is information that must be kept secret. Employees are trained to recognize and deal with confidential information so that it remains secure. Companies rank information and files by how sensitive each one is. Each company ranks their information differently, but there are 4 main types of confidential information that should be universally protected. Personally identifiable information, or PII, is any information that can be used to identify someone, like government ID numbers, birth dates, addresses, and phone numbers. Company confidential information is any information that is used to run a company, like intellectual property, product designs, procedures, plans, employee records, and financial data. Customer confidential information is information customers or partners provide to companies, which includes PII, and also things like purchase histories and credit card information. Protected health information, or PHI, is any information added to a person's medical record during diagnosis or treatment that can be used to identify them, like PII, medical history, prescription lists, photos, and more. Examples of careless data handling include things like entering a customer's credit card information into an unencrypted database, leaving a patient's medical file unattended at the front desk, or letting a work friend borrow your password to download files because they forgot theirs. Properly handling confidentiality means restricting access to only those who need the information, not allowing unauthorized views or copies, storing information securely with encryption, firewalls, permissions, and more, destroying any file copies that are no longer needed, not just discarding them, getting explicit consent before processing or storing information, including a disclosure about how long it will be kept, and ensuring employees create strong passwords that they do not write down or share, and that they change those passwords regularly. In this video, you learned that when raw data is refined, it becomes information. Intellectual property, or IP, includes designs, trade secrets, research discoveries, and even employee knowledge. Digital products are non-tangible assets that a company owns, like software, ebooks, or web elements. Data-driven business decisions are based on capturing data, correlating it, and then using it to create meaningful reports. And the classes of data that companies and organizations must protect are personally identifiable information, or PII, company confidential information, customer confidential information, and protected health information, or PHI. Welcome to Security Threats, Threats and Breaches. After watching this video, you will be able to identify the different types of security threats, list examples of security threats, and explain the difference between a worm and a Trojan. Weak security policies can lead to physical threats, tampering, or the theft of hardware. Only trusted, authorized personnel should have physical access to information systems, and only for the specific systems they are responsible for. It's much easier to steal data directly from a laptop or server than it is to remotely hack into a complex network. To keep hardware safe from physical threats, tampering, and theft, lock it in a secure area with card readers on doors to limit access. Use robust surveillance on the inside and outside of the premises, and keep these maintained, updated, and tested. Hardware failure or destruction can occur during power outages, fires, and natural disasters like earthquakes, floods, tornadoes, hurricanes, and electrical storms. Environmental conditions such as humidity and mold also pose risks. Keep hardware safe with a well-maintained infrastructure that includes fire suppression systems, backup power, and a properly functioning HVAC system to prevent humidity and mold. Ultimately, none of these strategies will work without a detailed plan for what to do if disaster strikes or a system is breached. Regular planning and run-throughs of mock disaster and attack scenarios will help refine the process and identify security weaknesses. Unpatched systems, misconfigured firewalls, weak cybersecurity, and weak physical security are just a few ways that data threats occur. Data leaks are the accidental exposure of confidential or sensitive data through a security vulnerability. Data breaches are when a data leak is caused intentionally by a cybercriminal. These occur when social engineering or phishing attacks trick employees into leaking sensitive credentials or information. Data dumps are when cybercriminals dump stolen data onto the dark web for monetary gain. A data dump might include PII, PHI, bank account numbers, PINs, social security numbers, and more. Other cybercriminals buy and use data dumps for things like identity theft and password attacks. Dumpster diving is the act of physically searching through a literal dumpster to find something valuable. A company's trash might contain lists of customer names, phone numbers, contact information, business plans, product designs, or an access code written on a Post-it note. Tech companies require document shredding and device destruction as a normal part of business because these can be stolen from the trash to harvest data that can be used for identity theft and data breaches. Or the data could be sold to hackers or a company's competitors. Software threats include theft, exploits, and malware. Software or license theft is the unauthorized copy or use of copyright-protected software. This includes pirating software and counterfeiting activation codes. Exploits are pieces of code that use vulnerabilities in hardware or software to get into a system. Malware-infected websites use exploits to automatically download malware to a system. This is called a drive-by download. Malware is a general term for software designed to compromise computer systems. Malware can cause system slowdowns, odd requests, browser misdirection, and pop-up ads. It can also steal data, record everything you do with or near your device, spam your contacts with infected links, and connect your computer to a network of hijacked computers that are remotely controlled, known as a botnet. Malware can come from attachments, sketchy websites, file downloads, infected USB drives, or links in emails, ads, social media, torrents, and even text messages. Phishing and remote desktop protocol attacks, or RDP attacks, are the most popular attack vectors for ransomware since they result in a higher success rate. To avoid malware, keep software updated, don't open strange attachments or links, back up your data, use strong antivirus software, and use strong, frequently updated passwords. Malware types include viruses, worms, trojans, exploits, spyware, adware, and ransomware. Computer viruses are programs designed to spread from host to host, just like real viruses. An infected app or file has to be started by a user for a virus to activate. Viruses can turn on a webcam, record keystrokes and site visits, steal data, corrupt files, and hijack email accounts. Let's look at some different types. Program viruses are bits of code that insert themselves into another program. Macroviruses affect Microsoft Office files via the macros they use to automate tasks. Stealth viruses copy themselves to different locations to avoid antivirus scans. Polymorphic viruses change their characteristics to get around cybersecurity defenses. 97% of all malware uses polymorphic viruses. Worms are viruses that start themselves after identifying system weaknesses. They don't rely on apps or files. And unlike viruses, worms can be controlled remotely. And Trojans trick you into installing legitimate-seeming software that includes harmful malware. Spyware collects personal data, login credentials, credit card information, and online activity, and can record using a device's camera or microphone. Adware is software coded into online ads that records your personal data, website visits, and keystrokes to send you personalized ads. Both adware and spyware can be legitimate or malicious. Ransomware locks a system, encrypts its files, and displays a ransom demand. To get the encryption key, you must pay the ransom, or you can regain access by doing a full system restore from a backup. In this video, you learned that hardware must be kept safe from physical damage, tampering, and theft. Hardware is vulnerable to natural disasters, fires, mold, and power outages. Software threats include theft, exploits, and malware. Malware includes viruses, spyware, adware, and ransomware. And 97% of all malware includes polymorphic viruses. Welcome to Security Threats, Threat Types. After watching this video, you will be able to list the types of impersonation, explain password cracking, and identify a DOS attack. Impersonation is when a hacker sets up a public Wi-Fi network that seems legitimate. Once a user connects, login credentials, session information, and PII can be intercepted. Another type of impersonation is when a hacker sets up a fake website that looks and feels exactly like a real website, such as a well-known bank or other high-profile site. They may send fake email or text links, known as phishing, to trick you into visiting the fake site so they can steal your credentials to the real site and install malware on your device. A third type of impersonation is when a hacker pretends to be someone else so they can steal data or take over systems. This is also called social engineering. Impersonation attacks can be used individually or in combination with each other. Hackers use snooping attacks to intercept data between devices. These attacks can reveal logins, credit card numbers, intellectual property, and more. Snooping attack types include eavesdropping, man-in-the-middle, and replay. Some hackers can even use a computer monitor's electromagnetic fields to reconstruct what it displays. Snooping is common on open, unsecured networks and can be difficult to trace. Eavesdropping, or packet sniffing attacks, occur on wireless, wired, and phone connections. A packet sniffer is a tool that intercepts everything transmitted on a network. Anything your device sends on an unencrypted network can be viewed with a packet sniffer. This allows hackers an opportunity to intercept, alter, or delete data transmitted between devices. If a network is encrypted, packet sniffers will only be able to see things like the origin and destination of a packet, but not the data inside it. Staying off public Wi-Fi or using encryption with a VPN or cellular connection helps prevent eavesdropping attacks. A man-in-the-middle attack is a form of eavesdropping. It has a victim, a receipt point, and an attacker. The victim and receipt point are unaware the attacker is listening in. Man-in-the-middle attacks can be physical or logical. In a physical man-in-the-middle attack, the attacker is physically near the victim, like the same public Wi-Fi network or a network they set up themselves as a trap. The attacker sniffs the unencrypted network traffic to gain access to everything the victim is doing online so they can steal information. In a logical man-in-the-middle attack, the attacker sends emails or texts with fake links that direct victims to sites that steal their data and install malware. If a fake email warned about a bank account problem, the victim might click the link and try to log in. This gives the attacker control of their bank account and installs malware on the victim's computer. Other man-in-the-middle attacks include spoofing, hijacking, and theft of browser cookies. A replay attack is a type of man-in-the-middle attack, which intercepts and retransmits data. Replay attacks are also known as repeat or playback attacks. Replay attacks involve trusted entities and require an access token. Trusted entities are users or websites that get an access token or security key after verifying that they are who they say they are. For example, connecting to your bank or your work network on a network-registered device. Hackers get access tokens by sniffing network traffic between trusted entities. Once they find an access token, they can hijack the session and use the token to impersonate the trusted entities. After that, the hacker can intercept and modify any information sent, or access private accounts as if they were the account holder. Password cracking is getting a correct password in an unauthorized way. Brute force attacks submit as many passwords as possible, hoping one will work. Dictionary attacks use words pulled from dictionaries or newspapers to crack passwords. And rainbow attacks use words from an original password hash to generate all other possible passwords. Hashing is when an algorithm transforms an input string, like your password, into a smaller fixed-length output string, or hash, that is saved to a file. A hash is like a digital fingerprint. Passwords are hashed with a scrambling algorithm. If a password hash is determined, attackers can use it to determine other passwords that were scrambled in the same way. That can be over 90% of unknown passwords in some cases. Unauthorized information alteration threatens the integrity of any process or outcome based on that information, including financial records, vote totals, health records, news stories, and more. Tools that fight unauthorized information alteration include File Integrity Monitoring, or FIM, which audits sensitive files and folders to ensure all activity is authorized, and Relational Database Management Systems, or RDBMSs. An RDBMS is a database that records user access and data changes. RDBMS is safer than a spreadsheet program. To preserve data integrity, security plans must prevent unauthorized user access, prevent unauthorized data changes by authorized users, and use error checking and data validation. A denial of service, or DOS attack, floods a network with so much traffic that it crashes. DOS attack victims are typically high profile, like government sites, banks, or social media sites. Sometimes, DOS attacks are used to distract from other attacks happening at the same time. Common DOS attack types include buffer overflow, when a website gets more internet traffic than it can handle; ICMP flood, when diagnostic pings are sent to every computer on a network. Each computer pings every other computer, and so on until the network crashes; and SYN flood, when a rapid series of incomplete connection requests floods a website until the server crashes. A distributed denial of service, or DDoS attack, is when a DOS attack is made with a large collection of compromised, malware-infected computers, known as a botnet. DDoS attacks give attackers the following advantages. It's harder to identify a DDoS attack's origin, which makes it harder to shut down. And DDoS attacks are far more devastating than DOS attacks, since hundreds or thousands of computers are used instead of just one. There are methods available to defend against DOS and DDoS, but they continue to be a real threat. In this video, you learned that impersonation includes public Wi-Fi traps, fake sites, and social engineering. Eavesdropping is also called packet sniffing. Man-in-the-middle attacks can be physical or logical. Replay attacks require trusted entity access tokens. A hash is a smaller saved code that is used to store scrambled passwords. To preserve data integrity, security plans must prevent unauthorized access and changes. And DOS and DDoS attacks flood a network with so much traffic that it crashes. Welcome to Security Threats, Password Management Techniques. After watching this video, you will be able to explore password management best practices, identify strong and weak passwords, and explain the difference between SFA, 2FA, and MFA. Strong passwords and an effective password strategy are essential to online security. People tend to use the same passwords across personal and business accounts, but weak or stolen passwords account for more than 80% of company data breaches. Each online account should have a unique password, especially corporate accounts. And employee training should exist to explain why password management and data security is so important. A password policy is a set of rules that provide guidance on using strong passwords. Password policies should require a minimum length of 12 characters, a mix of upper and lowercase letters, numbers, and special characters, a unique password for each account or device, including personal devices used for work, a mandatory password change every 6 to 12 months, employee training on cyber attacks, and notification to employees that the company will never ask for passwords. Password policies should insist that employees should never reuse or recycle passwords, never share passwords, not even with the CEO, never write passwords down, and never store passwords in a digital file. Hackers can guess 1 trillion passwords per second. Passwords often have quotes from movies, songs, or books. But hackers already have online databases full of these quotes and lists of dictionary words, encyclopedia entries, and more. For stronger security, use 12 characters minimum. Avoid names, places, dictionary words, or PII. Use upper and lowercase letters, numbers, and special characters. Avoid using LEET, or symbols for letters. Hackers already know about it. For example, writing the word password using the number 4 instead of the letter A, or the $ instead of the letter S. Use random characters, and use a passphrase, which is 12 or more random words. Here's what strong passwords look like. Organizations should never ask customers or employees for their passwords. When employees know that their company would never ask for passwords, they are less likely to fall for impersonation and phishing attacks. Don't share your password with anyone, not even your boss or the IT department. IT staff have admin rights. Any work they do can be done on their own logins. Companies must teach employees the risks of password reuse and take steps to stop it. Password reuse means using the same username and password for all your accounts. Using common passwords like 12345 or the word password. Using the same password but with a different username. Hackers can easily link previously used passwords to people, and they can spray common passwords at online accounts. Password expiration is when a password is set to expire after a specific amount of time. In the past, employees typically had to change their passwords every 90 days. But this inspired weak and reused passwords. Longer intervals help employees use less risky behavior. Password expiration does make sense, but not once it starts to negatively affect security. Single-factor authentication, or SFA, is when you enter one credential to log in. Username and password is the most common form. Single-factor authentication is not safe from keystroke loggers, malware that captures everything typed on a device, phishing, or data breach information sold on the dark web. With single-factor authentication, anyone who has your username and password can do whatever they want to with your account or data. Two-factor authentication, or 2FA, is when you enter two credentials to log in. Two-factor authentication is usually hardware-based, with the most common form being a security key that plugs into a USB port. 2FA devices are the best defense you can have against phishing and hijacking and are very easy to set up. Newer versions use NFC, so the key only has to be near the device instead of plugged in. Multi-factor authentication, or MFA, is quickly becoming the industry standard for effective security. It's an extra layer of protection that companies and organizations are using to keep cybercriminals out of their systems. When you're trying to access a resource or device that's using MFA, you need to provide more than just the correct password to get in. MFA offers the following extra protection over SFA. Risk of a breach occurring is significantly reduced. MFA factors can't be captured by keystroke loggers. You're in full control over which factors you provide: phone, email, text, security questions, or some combination of all of them. And significantly reduced risk from phishing. It's important to understand that multi-factor authentication is not 100% fail-proof. As hackers realize that the number of organizations using MFA is steadily on the rise, they continue to look for ways to circumvent it or to exploit the vulnerabilities which inevitably exist in these types of solutions. Identification factors are pieces of information that only you and an authentication service know. They are something you know, like your password or PIN, answers to security questions, or a one-time password or OTP code. Something you have, like a phone or email to receive OTP codes, a phone app that can generate OTP codes, or a device plugged into your phone or computer. And something about you, like your fingerprints, retinas, face, or voice. Biometric scans use these to authenticate you online or unlock a door to a secured area. Single sign-on, or SSO, verifies users for connected accounts or apps so they only have to log in once. Businesses use SSO to simplify and speed up access to resources. IT departments set up single sign-on with vendors like Office 365 or Salesforce.com, so employees are automatically logged in when they sign into their work networks. This lets employees continue working without having to remember multiple passwords. Password managers generate strong, unique passwords for every online account you create and remember each of them for you. They can analyze your stored passwords and warn you if any are too weak or if any have been reused on other sites. They use powerful encryption on all stored passwords to keep them safe. Once set up, you have to remember the one password for the password manager. In this video, you learned that 2FA is when a physical device must be plugged in before login. MFA is when multiple authentication methods are used to log in. SSO verifies a user across connected accounts. Password managers create strong, unique passwords and remember them for you. And strong passwords are long, random, secret, and never reused. Welcome to Security Threats, Access Control, Authorization, and Authentication. After watching this video, you will be able to define each authentication factor, explain how digital accounting is used, and identify the 4 methods of non-repudiation. There are 3 processes involved in logging into a network or account: access control, limiting or granting access to different areas based on user status; authorization, giving permission to access a computer, network, app, or account; and authentication, proving it's you with a password or other credentials. Access control prevents unauthorized viewing, modification, or copying of data. IT staff use access control to restrict what users can do, which resources they have access to, and what functions they are allowed to perform. Access is granted using the rule of least privilege, where access is only granted to resources that a user needs to fulfill their role. Role-based access control, or RBAC, follows a company's org chart. Different customer and employee roles are set up as groups on a network, and then those groups are granted certain permissions. When a new user joins the network, they are assigned to the group that fits their role. They will have the lowest level of permissions they need to do their job. Authorization is when you have permission to access a location or do an action. Before you can access an account or system, you need authorization. Access control must be set up before any authorization is granted to maintain data security. And authorization must be set up for your user account before you're able to log in. Once you are authorized, you can then use authentication to log in. Authentication is the act of confirming the identity of a user. Authentication involves 2 steps: entering the correct login information and confirming that it is really you. Authentication factors used to confirm identity include something you know, like a username, password, PIN, or answers to security questions; something you have, like a mobile device, security key, or security badge; and something you are, biometrics like facial recognition or a fingerprint, iris, or voice scan. Authentication methods include single-factor, or SFA, two-factor, or 2FA, multi-factor, or MFA, and single sign-on, or SSO. SSO lets you log into multiple applications and platforms with one login. 2FA and MFA are the most secure ways to log in because they require at least 2 authentication factors. Access control sets boundaries, authorization gives access, and authentication confirms identity. In the security field, it's important to know the right balance between the 3 A's. Strictly applying role-based permissions groups won't secure data if those groups all have the same authorization levels. The same is true if groups have properly set permissions but are not properly applied by administrators. Using strong passwords and MFA won't secure data if all groups have the same permissions. The same problem exists if groups have properly set permissions but passwords are weak. Using strong passwords and MFA won't secure data if all users are assigned to the same group. The same problem exists if administrators assign users to the proper groups but passwords are weak. Best practice should require strong authentication, strong authorization, and strong access control. Digital accounting is used in troubleshooting, security analysis, forensics, and hacking. Logs. Most software and systems generate audit logs. Audit logs capture log file events, which can show who did what and how the system behaved. Tracking. Websites can track your OS, browser version, installed extensions, screen resolution, installed fonts, time zone, language, and how long you spent on a site and what you did there. Cookies. A cookie is code used to track, personalize, and save information about your browsing session. Cookies can also be used to ban you from a website if you've violated any of its conditions for use. Browsing history is a list of recently visited websites. Anyone with access to your device can see what sites you visited. Attackers use browsing history to learn where they might impersonate their victims, and companies use it to see which sites you go to on your work computer. Non-repudiation is when you can't deny being in a specific location. It guarantees that a message sent between two parties is genuine, like a digital signature. It includes video, clear recordings of a person entering, leaving, or occupying a space. Biometrics. Fingerprint or iris scans can confirm whether a person physically accessed a device, network, or area. Signature. When a signature is used in conjunction with a hardware token, it becomes a digital signature. This authenticates the signer. And receipt. A digital receipt proves that a message was sent from one party to another. In this video, you learned that role-based access control, or RBAC, uses network groups with different permissions levels. The methods of authentication are single-factor, two-factor, and multi-factor. Authentication factors are something you know, something you have, something you are, and somewhere you are. Logs, tracking, cookies, and browsing history are used to troubleshoot and to uncover user activity on devices. And non-repudiation uses video, biometrics, signature, and receipt. Welcome to Security Threats, Hardening Devices. After watching this video, you will be able to evaluate methods to secure and harden devices, identify device and system vulnerabilities, and determine best practices for common security threats. Hardening is the process of securing a device to minimize vulnerabilities. You can harden devices by disabling unneeded device features, regularly updating device firmware, OS, and software, and using firewalls, VPN, and anti-malware. The more layers of security you use, the safer your data and devices will be. To protect your applications and OSs, turn on auto updates for PCs, phones, tablets, and routers. Outdated systems are huge targets for hackers. In business, updates are tested first. If they pass, they are pushed to production servers. To make sure your apps, OSs, and drivers are secure, only install from app stores, authorized resellers, and manufacturers, and check software for a digital signature from its manufacturer. Patches are updates to apps and OSs that fix security weaknesses. Companies regularly release patches alongside system improvement updates to make sure that their customers are safe from new threats. But patches are a response to known threats, meaning the threat has already happened to someone. To prevent unknown threats, also use multi-factor authentication, virtual private networks, and strong passwords. Firmware is software that tells hardware how to behave. Security firmware protects devices and data from malware and tampering. BIOS passwords, also firmware passwords. BIOS, or Basic Input-Output System, is firmware that boots up Windows and Linux PCs, runs hardware checks, and starts the OS. The OS won't start without the password, or if the checks find a problem. Secure Boot, UEFI, or Unified Extensible Firmware Interface, is newer and a more advanced boot firmware than BIOS. Secure Boot is a feature of UEFI, It confirms an OS manufacturer's digital signature, which prevents malware from taking control during boot-up. TPM. TPM, or Trusted Platform Module, is a chip that stores and manages encryption keys. TPM chips won't start a device or unencrypt data if tampering is detected. Drive encryption. Drive encryption scrambles a drive's data so it's unreadable. Outdated firmware leaves devices vulnerable. Make sure your PCs, phones, networking hardware, and even your cars have firmware that is up to date. Encryption is one of the most powerful tools you can use to harden a device. It uses algorithms to encode plain text into unreadable ciphertext. Only the encryption key can decode it. Encryption is used at the network layer for data traveling across networks. It can also be done locally to hard drives, phones, and even thumb drives so that lost device data remains unreadable. Device lock adds device security. For example, heavy, bolted-in hardware is physically difficult to take, especially if it's behind a locked door. Laptops are harder to take when they're bound to a desk with a steel cable and padlock. And even though mobile devices are easy to lose, digital locks keep their data inaccessible. Disabling features and ports when not in use reduces the ways a hacker can gain access. For example, Auto Run allows inserted drives and disks to run or play automatically. An infected drive could install malware automatically. Bluetooth allows connections and data transfers between devices. If a hacker gains access, they can use it to steal data and install malware. NFC transfers data across devices with a tap or a bump. It's usually used for payments or sharing contacts. It has a much shorter range than Bluetooth and has zero security protections aside from its limited range. Disabling unused computer ports also reduces the ways a hacker can gain access. However, some of the most vulnerable ports have to be opened to ensure functionality and connectivity. For example, Port 443 manages secure web traffic. Port 22 is used for secure server connections. And Port 80 manages standard web traffic. When features and ports are not being used, disabling them hardens them against attack. Apps that harden are affordable, reliable, and provide helpful configuration suggestions. Examples include antivirus, anti-malware, anti-spyware, software firewalls, and VPNs. Maintaining these apps, especially on smartphones, helps keep attackers out of your devices. Firewalls harden devices by keeping unwanted visitors out of your system and off your network. There are software firewalls and hardware firewalls. They monitor connections and block harmful traffic based on preset rules. For example, schools and businesses use firewalls to block social media sites, age-inappropriate content, and certain types of downloads. VPNs encrypt the traffic coming out of your device. Even if a hacker is capturing your data, they won't be able to read it or decrypt it. VPNs and firewalls range in cost. Some are free. Public Wi-Fi is convenient, but it's unencrypted and doesn't require passwords. Hackers can easily intercept and steal your identity, drain your accounts, and scam your contacts. Secured Wi-Fi, provided by your ISP or the network at your job, is much safer to use. These have very strong encryption. If you can't avoid public Wi-Fi, use a VPN on all your devices. Only visit HTTPS sites that are well known. Use your phone as a hotspot, as cellular networks are encrypted. Disable automatic Wi-Fi connection settings. And don't access personal or financial information on public Wi-Fi. Default usernames and passwords are essential to tech support, software installation, and device configuration. They also pose serious risks. They're easily found online in help guides or user manuals. They have admin-level privileges, they hide who's using them, and they're usually left unchanged. It's common for hackers to use them to break into apps, devices, OSs, databases, and BIOS. To close security loopholes, Disable built-in accounts if possible. Change all default passwords. Use strong passwords. And check documentation for default, backdoor, and hidden accounts. In this video, you learned that apps and OSs should be regularly updated. Patches protect against known threats. Outdated firmware leaves devices vulnerable. Encryption encodes plain text into ciphertext. Disabling features and ports reduces attacks. Firewalls block traffic. VPNs encrypt traffic. Anyone can see what you do on public Wi-Fi. And hacking a device is easy with default passwords. Welcome to Security Threats, Validation, and Device Usage. After watching this video, you will be able to explore device use best practices, identify reputable driver and firmware sources, and list the do's and don'ts of keeping your devices safe. To reduce security risks, always be sure to get your software, cloud services, device drivers, and firmware updates from legitimate sources, like vendor app stores, like the Windows Store and Google Play Store, authorized resellers, like Best Buy and Costco, original equipment manufacturers, or OEMs, like Dell and Samsung, and software manufacturers, like Adobe and Microsoft. If you're downloading purchased software from a website, check the URL to ensure it begins with HTTPS. Click the lock icon in the URL bar to see if the certificate is still current and who owns it. Avoid pirated software torrents. They're loaded with malware. Avoid software from untrusted sources. And avoid jailbreaking or rooting your phone. Non-approved apps are untested and could contain malware. Original equipment manufacturers, or OEMs, provide drivers and firmware updates on their websites. Dell, HP, Samsung, Nikon, NVIDIA, and more all provide downloads for device drivers and firmware updates for the products they build and sell. Avoid third-party sites that claim to host drivers for the latest devices. These may be malware traps. There are some third-party sites that host legitimate obsolete drivers for obsolete hardware that a manufacturer no longer supports. But use these sites with care. Research them and check forum reviews to ensure they aren't malicious. Device driver software should also be digitally signed by the vendor, and the vendor's certificate should be trusted by your computer. Uninstall software that you don't use or don't want. New devices may come preloaded with unwanted trial software, commonly referred to as bloatware. Aging bloatware is soon outdated and may have vulnerabilities. The same is true for software you no longer use. If you need an app in the future, download it from the software manufacturer's website to ensure it is legitimate and up to date. Then enable automatic updates to keep the application safe. New attacks and malware are released onto the internet daily. This makes anti-malware and VPN services a must for all your devices. Microsoft's Windows Defender protects your computer against viruses and malware free of charge. It also integrates with the built-in firewall that comes with the Windows operating system and is enabled by default. However, Windows Defender does not perform VPN functions. Some third-party antivirus software, such as McAfee, Bitdefender, or Norton, can be purchased for a reasonable cost if that is your preference. They may disable Windows Defender and Windows Firewall during their installation process, which is completely normal. Many reputable antivirus companies provide malicious software removal tools for free, including Microsoft. They always have the latest virus signatures and are very effective. Just pick the one you like, download, and scan. It will automatically remove any malware it finds. If the tool doesn't resolve your issues, you may need a PC technician who can assist you further. Prevent malware infection with safe computer usage and browsing techniques. Don't visit questionable websites or HTTP sites. Don't download from file sharing sites as they have loads of viruses. Don't insert used or unknown disks, storage, or USB devices into your computer. And don't click links or file attachments from emails or messages, even if you know the sender. Do use good anti-malware software on all of your devices and keep them up to date. Do use up-to-date firewall and VPN software on any devices you go online with. Do visit encrypted HTTPS sites. Do use OEM or authorized reseller sites when downloading software. And do reduce accounts that have elevated privileges, like admin, superuser, or root roles. In this video, you learned that apps, device drivers, and firmware should come from reputable sources. Rooting or jailbreaking makes devices vulnerable. Apps from file-sharing sites are loaded with malware. Old apps and bloatware leave devices vulnerable. Malicious file removal tools are available for free from reputable antivirus companies. And automatic updates in antivirus, firewall, and VPN software keep devices safe. Welcome to Security Threats, Encryption Concepts. After watching this video, you will be able to explore encryption and its common uses, list use cases for symmetric and asymmetric encryption, and explain how cryptographic hashing works. Encryption is the act of taking readable text and scrambling it so it can only be read by a recipient that has the decryption key. Data that has not been encrypted is called plain text because it's readable. Algorithms used to scramble plain text are called ciphers. Encrypted plain text is called ciphertext. An encryption key is a series of random, unique numbers combined with very powerful algorithms that are used to encrypt or scramble your data before you send it. The person on the receiving end has a decryption key that's used to decrypt or unscramble the data so it's in a readable or usable format. In some industries, data encryption is a mandatory requirement. This includes student records, medical records, and consumer data. Many OSs have encryption built in. For those that don't, third-party encryption software is available. Data at rest refers to data that resides on a storage device. The files aren't open or being transmitted anywhere. Data at rest can be encrypted at the file level, storage device level, and cloud level. Encryption at the file level lets you encrypt all your files on a storage device, or just a select few. Disks and drives can be encrypted in two ways: using software to perform the encryption, or enabling hardware-based encryption like BitLocker. Data at rest is less vulnerable, but it's not immune from attacks. Using updated firewalls, VPNs, and anti-malware helps keep your data safe. Data in motion, or data in transit, refers to data that is actively moving between two devices, meaning two computers, a mobile device and a mail server, or your computer and your bank's online website. Any website that uses HTTPS in its prefix is using encryption. However, hackers can compromise encrypted sites with social engineering, man-in-the-middle attacks, and password cracking, and they can create their own encrypted HTTPS sites that install malware. Data in motion is especially at risk for interception attacks, like man-in-the-middle. Using end-to-end encryption means that the data being transmitted and received is safe, even if it's intercepted by a hacker. They won't be able to decrypt your data. Data traversing through a virtual private network, or a VPN, is automatically encrypted, but is not always end-to-end. Symmetric encryption, also called single key or private key encryption, is when a single key is used between parties to encrypt and decrypt data. With only one key, symmetric encryption uses less memory, which is great for quickly and securely processing larger amounts of data. That's why it is often used to protect the main data exchange in a session. But it's harder to keep a single key secret, especially if it needs to be broadly distributed. If this key is intercepted by a hacker, then they can decrypt your messages, hack your account, and steal or tamper with your data. 3DES and CAST are examples of symmetric encryption technologies. Asymmetric encryption, also called public key cryptography, uses a public key and a private key. Asymmetric encryption takes longer because it is more complex. It is used for smaller amounts of data. It is safe to widely share the public key for encryption or decryption because only the secret key can undo the public key's action. Uses include authentication, digital certificates, digital signatures, and key exchange, where a symmetric encryption key is shared only to the intended recipients. The RSA cipher is used in most asymmetric encryption. Public key infrastructure, or PKI, is when a user is validated with a digital certificate by a certificate authority, or CA. The digital certificate has a public encryption key that encrypts data. If the data recipient trusts the CA that issued the digital certificate, they use a private key to decrypt the data. Digital certificates are used in smart card authentication. The smart card has a public-private key pair. It presents a digital certificate, including the public key, to the server it's trying to access. If the server trusts the CA that issued the digital certificate, it will use the public key to send an encrypted request. Only the smart card's private key can decrypt the request, which means only the smart card owner can send the correct response. For digital signatures, the process is reversed. The sender sends an encrypted signature and a public decryption key to a recipient. If the recipient can decrypt the signature with the public key, that proves the sender signed it because they must have performed the encryption with the private key. A cryptographic hash is a short string of numbers and letters created by running a password or file through an algorithm. A single password and a full library will have different cryptographic hashes, but each will have the same number of characters. If any data is altered or removed from a password or file, its cryptographic hash will be different. If the cryptographic hash of a secure email is different after being sent across a network, the recipient knows the message has been tampered with. When you create a password, it's converted into a cryptographic hash. On your next login, it's converted again. If the stored hash and the new hash match, the system lets you in. Cryptographic hashes save space, authenticate data, and keep information secure. In this video, you learned that encryption scrambles plain text into ciphertext so the data cannot be read. Encryption needs keys to encrypt and decrypt data. Data at rest is data that resides in storage. Data in motion is data that is actively being transmitted and received. Symmetric encryption uses the same key to encrypt and decrypt data. And asymmetric encryption encrypts with a public key and decrypts with a private key. Welcome to Security Threats, Managing Email and Spam. After watching this video, you will be able to define spam, identify phishing scams, and list ways to reduce spam. Email management is classifying email messages and deciding whether they should be saved or deleted. It can help you prioritize emails, save you time, and increase your productivity. For well-managed email, keep your inbox clean. Use folders and subfolders to organize your email by category. Use rules or filters to automatically move certain emails into folders. Unsubscribe from email lists. And turn off email notifications on your computer to keep distractions at a minimum. But what about spam or junk mail? Most email apps and servers block spam and junk mail, but some still gets through. You can configure your email settings to include additional filters. Mail routed to the junk folder is automatically deleted after a set number of days. Spam is email that's unwanted and often unsolicited. Some spam is harmless, but it can be dangerous when scammers use it to commit phishing attacks or fraud against you. Your company and web-based email services filter out spam at the email server level and block domains known for sending spam. But there is more you can do on your own to help reduce it. Don't give out your email address. Use throwaway accounts. Configure your phone and PC OS settings to block spam. And use a full-featured desktop mail app like Microsoft Outlook. It lets you block email from a sender or domain and create rules to delete spam automatically. Note that you can unsubscribe from mailing lists, but this just validates your email address, which may result in more spam. Hackers use email and messaging to commit fraud. They steal usernames and passwords, bank account information, social security numbers, and more. This is called phishing. Phishing attacks are common because they work. Rule number 1 in phishing attacks is don't click any links and never open attachments. Phishing attackers do their best to make it look like the email or message came from a friend or family member or someone official like your bank, the government, or a large company. The story is always the same. They want you to feel fear, greed, or a sense of urgency so you're more likely to make a rush decision. For example, they are alerting you to suspicious activities or logins on your account. They say there's some problems with your account information or your payment hasn't been received and provide a link for you to click and update your payment information. They say your account has been breached and offer a link for you to reset your username and password. They say you're entitled to a refund. You simply click the link they provide and enter your personal information. They offer prizes or other free items, but you must respond ASAP to get the deal. Or they demand you pay a fake invoice to avoid fines or jail time. Phishing emails usually have typos and grammatical errors. Make sure to inspect the text, logos, and URLs to see if they look wrong or are misspelled. Close the email, then visit the genuine website of the impersonated company. Manually enter the URL so you get to the right site. Let them know about the phishing attack so they can report it to the fraud department. In this video, you learned that spam is email that is unwanted, unsolicited, and comes from people you do not know. Hackers use phishing attacks because they're highly effective. Phishing uses feelings of fear or urgency to trick you into giving up your personal information. Phishing emails have lots of typos and fake links. And links or attachments may install malware. Welcome to Safe Browsing Practices, Application Ecosystem Security. After watching this video, you will be able to identify app and software security concerns, explain how apps and software are compromised, and list the types of data hackers look for. Mobile apps are designed to be functional and easy to use, but they are not always the most secure. Weak passwords, malware, or poorly designed apps can compromise a device, letting hackers access texts, contact lists, personal and business files, and other valuable information. For better security, use strong passwords, only install App Store-approved apps, and use multi-factor authentication. Multi-factor authentication, or MFA, is a setting that requires you to fill in a code sent to your email or phone to prove that a login attempt came from you. Strong passwords are long, difficult to guess, and have a mix of numbers, letters, symbols, and capitalizations. For example, the phrase, "Johnny Appleseed loves apples," would be a very strong password, especially if it included a mix of numbers and symbols. Some users remove device restrictions so they can make changes and install non-approved apps. This is called rooting on Android phones and jailbreaking on Apple phones. This adds functionality, but also adds vulnerability. It is harder to root or jailbreak newer model phones, and there is less reason for it with updated features and app selections. To ensure a basic level of security, Apple and Google restrict certain device activities and remove apps from their app stores if they don't meet security standards. Desktop software can be used to open any file stored locally or in the cloud. Cybercriminals can access and take over software, files, data, and online accounts via PCs that don't have strong passwords, PCs left in unsecured physical locations, and via unsecured browsing sessions on non-HTTPS websites. IT departments push out security patches and updates on a regular basis to keep operating system and app software secure against known vulnerabilities. But patches and updates alone aren't enough. Here are some steps you can take to be more secure. Use strong passwords, store PCs in a physically secure location, and lock them when not in use. Use good antivirus, anti-malware, and VPN software, and enable automatic updates. And only browse HTTPS websites and keep software properly configured and updated. These habits make devices harder to hack, which keeps your data protected, as cybercriminals will simply move on to easier targets. Business software automates transactions, mines sales data, manages resource and supply chain information, and more. Hackers target businesses with ransomware, zero-day attacks, or other cyber attacks to steal sensitive data so they can sell or exploit it. This can cost millions and be devastating to consumers, businesses, organizations, and governments. In today's remote work world, businesses maintain employee education to ensure security best practices are followed, and they use strong tools to prevent, detect, and respond to vulnerabilities and threats. To protect corporate files, systems, and resources, businesses must limit access. The ability to share files within an organization or business to business is important. When email or USB drives aren't an option, organizations may choose internal network sharing on company-owned hardware for sharing, storage, and collaboration. Or they may turn to the cloud for a solution, like the enterprise versions of Box, OneDrive, or Google Drive. Whichever solution is used, employees must be taught how to properly secure corporate data. A careless worker who clicks on a phishing email or fails to abide by corporate policy can expose a company to unnecessary risk. Company data should only be shared on a need-to-know basis. Insider theft of data and intellectual property is common. Strict access control helps avoid it. But file sharing should be practical. If a company makes it too difficult, employees will find a way around it. For example, consumer-level cloud storage and sharing freeware. Security isn't as robust in those solutions. If there's a breach, hackers can steal passwords and reuse them to gain access to company networks. It's important to remember that you're only as secure as your weakest link. That's why there are so many ways to configure network sharing. Whether it's on-premises, in the cloud, or stored in an unauthorized freeware account, having a plan ahead of time to deal with these potential situations will help companies avoid the worst. In this video, you learned strong passwords, antivirus, malware software, VPN, and updates are used to secure apps and devices. Hackers target apps to mine for sensitive data, intellectual property, trade secrets, and financial data. Businesses use multi-factor authentication to protect data, information, and consumer trust. And multiple layers of security are required to keep devices and their data secure. Welcome to Safe Browsing Practices, Public Browsing Risks. After watching this video, you will be able to list the security concerns of public browsing, identify public browsing risks, and list the types of data hackers steal from public networks. Free and open networks are available in many places. Airports, coffee shops, hotels, and even fast food restaurants will offer their guests access to public Wi-Fi. These networks are not encrypted, Your device may warn you about this when you're trying to connect to one of them. Unsecure networks invite eavesdroppers to view everything you send and receive on that network. They can potentially install malware on your device or hijack your session if your device is not protected. Public connections are free to use, but that doesn't mean there isn't a cost involved. The provider might track everything you do on the Wi-Fi connection, then sell your data to advertisers or other interested parties. If a hacker gets access to your device via public Wi-Fi, they have free reign over everything on it and can even obtain the credentials to your banking or other websites you may have logged into. Travelers may connect to public Wi-Fi to check email, download files, and review work information. Most businesses have security measures to reduce the risk of connecting over Wi-Fi, but there are still risks when using a public connection. Session hijacking is when an attacker intercepts and hijacks your connection. For example, they can take over a connection while you're logged into your bank and transfer funds to an outside account. Shoulder surfing is when an attacker sits strategically in public areas to try to see usernames and passwords, bank account PINs, and other essential information. To stay safe, use a mobile hotspot or cellular connection. If public Wi-Fi is the only option, be sure to use firewalls, strong passwords, antivirus and malware software, and VPNs. Most social network sites operate with secure HTTP or HTTPS, but that doesn't mean they are safe. The best way to protect yourself is to make sure the social networking sites you visit are safe before sharing any information. Learn about their privacy and security settings and use them. Be careful with the type of information you share on social networking sites. Not everyone is friendly, and cybercriminals will do just about anything to get someone's personal information. Avoid clicking suspicious links, emails, tweets, posts, and online advertising. These are often how cybercriminals try to steal your personal information or hijack accounts. If it looks suspicious, delete it. Use strong passwords, as they will make it more difficult to break into your device if it is lost or stolen. And as always, keep your software and devices current. Use the latest security software, web browsers, and operating systems, and encrypt with VPN. Use a mobile hotspot or cellular connection instead of public Wi-Fi. Instant messaging systems are typically not designed with security features in place. Senders are not authenticated, and chats can be hijacked and users impersonated. Information sent over chat is often in plain text. That makes it easy to intercept and exploit, especially over public Wi-Fi connections. Never reveal sensitive data over chat. Files sent by chat are not scanned by computing devices. Avoid file transfers and links, even if they appear to be from someone you know. These are the easiest ways for hackers to plant viruses, spyware, keystroke loggers, phishing scams, spam over instant messaging, or SPIM, and a variety of worms. Instant messaging apps should always have encryption and automatic updates on. A simple search can tell you if an instant messaging app uses encryption and how to access security settings. Websites relying on the HTTP protocol are not secure, especially when visited over public Wi-Fi. Everything that you send and receive is in plain text. It makes you an easy target for cybercriminals. Secure HTTP or HTTPS protocol provides an encrypted connection between you and the sites that use it. Most commercial websites, social networking sites, or sites that offer a customer login use HTTPS. How do you know a website you're visiting is using secure HTTP? The easiest way to tell is to see if the URL starts with HTTP or HTTPS. Or you can look for a lock icon in your browser's URL window. Clicking the lock shows who owns the digital certificate that proves the server is who it says it is, and if any cookies are in use. It can also open browser security settings so that you can make adjustments as needed. It's important to remember that HTTPS only provides a secure connection between you and the web server. A site can use HTTPS and still try to scam users or be compromised in some way. In this video, you learned that your data can be tracked and sold to other parties when using public Wi-Fi. Public Wi-Fi is unencrypted, and your public data can easily be intercepted and read by hackers. Social networking sites and instant messaging are vulnerable to cyber threats. HTTPS sites are identified by their URL prefix and by the lock icon in the URL window. An HTTPS provides an encrypted connection but doesn't guarantee that the site is safe. Welcome to Safe Browsing Practices, Plugins, Extensions, and Toolbars. After watching this video, you will be able to configure a browser for a secure browsing experience, identify secure and insecure websites, and explain how to manage plugins, extensions, and toolbars. In today's remote and cloud-based world, the browser has become an important tool in our daily lives. Google Chrome, Microsoft Edge, Mozilla Firefox, and Apple Safari are the most common. Browsers are often pre-installed, but are not typically set up in the most secure way. The internet has many risks, so it is vital to configure and maintain browser security so you can protect against those risks. Security zones are a feature of older browsers. They block or allow websites and confine them to different zones, such as the local network, internet, or intranet. For each zone, you could apply different security levels. For example, medium, high, or custom. Security zones can also be configured to allow ActiveX and Java for added website interactivity or functionality, but this can introduce risk. Modern browsers do not use zones, but older web apps may require you to enable ActiveX in order to run properly. Browser add-ons have evolved over the years. Toolbars were designed to add functionality to the browser, like spellcheck, autofill, yellow pages, and dictionaries. But most toolbars were considered nuisanceware. Some would show sponsored results instead of what you originally searched for, or they'd impede system performance. Some even installed malware, tracked browsing habits, and collected user data. Toolbars used to be forcibly installed on user devices during software installation processes. Fortunately, toolbars are a thing of the past. Plugins are site-specific browser add-ons that you click on to install. They are not supported in today's modern browsers in favor of extensions. A browser extension is a small piece of source code that adds a function or feature to a browser. Ad blockers and in-browser PDF readers are extensions. Since extensions are given special authorizations within the browser, they are attractive targets for attackers. Cookies are text files with small pieces of data. When you visit a site, the server creates a cookie and saves it on your browser to track you. Cookies let websites remember your logins, shopping carts, and more. This creates an easier, more personalized online experience. Most cookies are safe, but some are designed to track without consent. Even legitimate cookies can be harmful if you get hacked. Let's look at some different types. Session cookies are used only for one session. They are stored in RAM and are automatically deleted when the browsing session ends. Persistent cookies remain on a computer indefinitely, but some have expiration dates. Authentication cookies save logins, usernames, and passwords so you don't have to remember them. Tracking cookies track multiple visits to the same site over time. Online stores use these to see how you shop and send targeted ads. First-party cookies are from the site you are on. These are safer on reputable sites. Third-party cookies are from sites you are not on. These track you across the web. Ads can generate cookies even if you never click on them. Zombie cookies are third-party cookies that don't follow normal cookie protocols. They can store their code directly on your device to recreate themselves even after deletion. They are extremely difficult to remove. Websites may also use zombie cookies to ban specific users. Security certificates, or Secure Sockets Layer, or SSL certificates, authenticate a website's identity and enable an encrypted connection between a web server and a browser. SSL certificates come from organizations called Root Certificate Stores, or Certificates of Authority, commonly called a CA. The major root certificate stores are Apple, Microsoft, Mozilla, and Google. Which CA your device uses depends on the operating system it's running. When you browse a website using HTTPS, you're trusting the CA to validate the information submitted by the business who has requested an SSL certificate. Businesses need SSL security certificates for their websites so they can keep user data secure, verify their ownership of the site, prevent attackers from creating fake versions of their site, and to convey trust to users. They also need them if they want to have an HTTPS web address. When you see a lock icon in the address bar of a URL you visited, then you know that website is using HTTPS. Because browsers are a favorite target for hackers, keeping them updated is very important. Browsers, by default, automatically update themselves. The updates are installed and applied when you restart your browser. If your desktop or laptop is part of a corporate network, your IT department may be managing the configuration and manually applying updates to the browsers installed on your system. On mobile devices, you may enable or disable updates occurring over metered or cellular connections and apply them upon the restart of your browser. Updating over a cellular connection can incur charges. Otherwise, they will update automatically when connected to Wi-Fi. In this video, you learned that hackers target browsers because they are the gateway between your device and the outside world. Updating browsers and properly managing cookies and extensions helps keep your data secure. SSL security certificates and certificates of authority prove a website is who it says it is. An HTTPS can guarantee an encrypted connection, but cannot guarantee that a site is not compromised. Welcome to Security Threats, Safe Browsing Techniques. After watching this video, you will be able to explain what a cache is for, identify safe websites, and list adware risks. Autofill, or autocomplete, remembers and fills in specific information, like passwords or addresses in a web browser. Without it, you'd have to repeatedly fill in passwords and form fields manually. This can get tedious, especially on mobile keyboards. You can configure autofill categories such as passwords, payment data, and addresses in your browser settings. When sharing devices with friends and family, set up guest accounts with different browser settings and configure syncing so that autofill is only applied to the devices and browsers you want. A browser cache is a storage area that holds downloaded web pages you've visited. Cached pages load immediately. If a page has changed since the last cache, it is downloaded, displayed, and cached again. Over time, very large caches cause sluggish performance. A browser history is a list of every page you've visited and for how long. Browser histories help you find sites you visited, but they can also be used against you by family, hackers, or law enforcement. Use browser settings to clear history and cache, and to set cache disk space and expiration dates. Private browsing doesn't save browsing history, cookies, site data, or form data. With private browsing, you appear as a new or unknown user on the sites you visit. Other people who use the device won't see your history. Cookies and site data are remembered while browsing, but deleted when you exit the browser. But private browsing activity isn't hidden from your employer or school or your internet service provider or ISP. The bookmarks you create will be kept. and downloaded files are saved to your Downloads folder, which may be visible to other users. Malicious websites mimic real websites to trick users into entering login or payment data and can install malware that gathers personal information or takes over a device. Their URLs might use a 0 instead of an O, or a capital I instead of a lowercase l. Their site pages often have typos or designs that don't match the legitimate site they are mimicking. If you accidentally visit and enter information into a malicious website, exit the site, run antivirus and anti-malware, change your password, and, if needed, ask your bank for a new card. Identifying safe websites is more important than ever. Let's review some safety tips. Use the Whois lookup tool to see who owns a site. Missing contact information is a red flag. Look for reviews. Reddit and other social forums list scam sites and sites with security risks. Only visit HTTPS sites, or your activity could be visible to online predators. Check the Trust Seal or Security Certificate information. And inspect URLs and site design to avoid malicious websites. Adware is malware that displays unwanted ads. Often bundled with apps, it activates on install. Adware can collect data, track online activity, or link out to malicious websites with viruses. It can also cause sluggish system performance or crashes, changes to your browser's homepage, the appearance of new extensions, toolbars, or software, and web pages not displaying properly. Pop-up ads and the sudden appearance of unfamiliar apps are the most common way to recognize adware. The aim of redirection is to point you towards certain types of advertising or dangerous code. Redirection is usually caused by adware or malware. This includes toolbars or browser extensions that show alternate search results loaded with ads, malware that sabotages searches or typed-in URLs, and hacked website servers that redirect anyone who visits. Any connected device can be exploited, especially mobile phones, since they don't usually have antivirus software and other safeguards. To avoid hijacking software and redirects, set automatic updates for your browser, OS, and security tools, and run regular system scans. Search engines use algorithms to detect harmful sites. Browsers use those results to warn users. These sites may contain malware, malicious code, phishing scams, or be hacked in some other way. If your browser tells you a site is unsafe, avoid that site. In this video, you learned that autofill keeps password, payment, and address data. Caches store downloaded web pages for fast loading. Private browsing deletes cookies, history, and cache. Safe websites use HTTPS, trust seals, and reviews. Adware can collect data, track online activity, link to malicious sites, and slow system performance. And search engine algorithms detect dangerous sites. Welcome to Security Threats, Virtual Private Networks. After watching this video, you will be able to list the different VPN connection types, explain the pros and cons of hardware and software VPNs, and identify network hardware that can be used to create VPNs. A virtual private network, or VPN, is an encrypted tunnel set up between two or more sites. All traffic in the tunnel is unreadable and useless to anyone who might try to intercept the traffic. VPN traffic is encrypted at the originating site and decrypted at the receiving site. VPNs make it much more difficult for hackers to make eavesdropping attacks, man-in-the-middle attacks, and replay attacks. This is especially useful if public Wi-Fi is your only connection option. VPNs can be hardware-based or software-based. Site-to-site VPN is when two sites connect across an existing internet connection with a VPN device. Each site's internal network traffic is unencrypted. Traffic that needs to traverse the internet is encrypted by the origination site's VPN and then decrypted by the receiving site's VPN device, which then routes the traffic to its intended recipient. Host-to-site VPN is when a remote user needs to connect securely to a site. The host device uses VPN software while the site uses a VPN device or software to protect its internal network. Traffic that needs to traverse the internet is encrypted by the sender's VPN and then decrypted by the receiver's VPN, which then receives the traffic if the host is the receiver, or routes it to its intended recipient if the site is the receiver. Host-to-host VPN is when two remote users need to connect securely to each other. This is a user-to-user or device-to-device interaction that doesn't require a complex encryption solution. Both host devices use VPN software. Traffic that needs to traverse the internet is encrypted by the sender's VPN and then decrypted by the receiver's VPN. VPN hardware devices are devices specifically designed to create VPNs, or network devices with added VPN functionality. They include VPN concentrators, routers, and firewalls. Internet Protocol Security, or IPsec, is a suite of network standards and protocols that use cryptography to protect data traveling over the Internet. The core protocols for the IPsec suite are the IPsec Authentication Header, or AH protocol, which authenticates the sender and both IP addresses, and the Encapsulating Security Payload, or ESP protocol, which encrypts data and authenticates data and senders. IPsec has two modes, tunnel mode and transport mode. In tunnel mode, the entire data packet is wrapped in a new packet, encrypted, and given a new header. Tunnel mode is common in site-to-site VPN. In transport mode, the IP header of the original data packet is left unencrypted. Only the content of the data packet is encrypted. Transport mode is common in host-to-site VPN. The IPsec suite uses many components to support data security. These include security associations, or SA, Internet Key Exchange, or IKE, encryption and hashing algorithms, and anti-replay protection. IPsec authenticates data to ensure integrity and encrypts data to ensure confidentiality. It also protects against replay attacks and enables secure encryption key exchanges. In this video, you learned that a VPN is an encrypted tunnel set up between two sites. Site-to-site VPNs connect two sites. Host-to-site VPNs connect a device to a site. Host-to-host VPNs connect two devices. VPN concentrators, routers, and firewalls can provide secure VPN connections. The IPsec suite has two modes, tunnel and transport. And the core IPsec protocols are Authentication Header, or AH, and Encapsulating Security Payload, or ESP.
Welcome to Introduction to Cloud Computing, the first in the series of 4 courses designed to give you the foundational skills you need to be a cloud practitioner. Today, cloud represents a huge market, one that is continuing to grow at an unprecedented scale. Enormous computational power, once considered a prerogative of large enterprises, is now available at the fingertips of even the smallest of businesses and individual developers, thanks to cloud. Moreover, the cloud makes all this computational power highly affordable with pay-as-you-go economics. If you look at some of the key emerging technologies of our times, such as artificial intelligence, the Internet of Things, blockchain, and analytics, all of these technologies work with massive amounts of data and need huge storage space and computational power in order to work, making cloud possibly the only viable platform for these technologies. This course will introduce you to the core concepts of cloud computing, from its essential characteristics to the different service and deployment models, cloud architecture, security and monitoring, emerging technologies supported by the cloud, and career opportunities available in the domain. The course is designed for everyone. It doesn't matter if you have a background in cloud technologies, whether you're an IT person looking to upskill or explore this domain, a fresh graduate looking to make a career in cloud technologies, or an IT decision maker. This course will equip you with what you need to get started. With just the public cloud service market expected to grow to $331.2 billion by 2022, it's a great time to be in the cloud computing industry. Today, there are more open positions in cloud than the number of skilled people available, and the sheer growth of the cloud market makes it an exciting and dependable career prospect for the coming times. So congratulations on embarking on this exciting journey, and good luck! Cloud computing, also referred to as the cloud, is the delivery of on-demand computing resources, everything from applications to data centers, over the internet on a pay-for-use basis. To get a common understanding of cloud computing, let's start with the U.S. National Institute of Standard and Technology, NIST's, definition of cloud computing. NIST defines cloud computing as a model for enabling convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. Examples of computing resources include networks, servers, storage, applications, and services. This cloud model is composed of 5 essential characteristics, 3 deployment models, and 3 service models. Let's start with understanding the 5 essential characteristics of the cloud, which include on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. On-demand self-service, the first characteristic, means that you get access to cloud resources such as the processing power, storage, and network you need using a simple interface without requiring human interaction with each service provider. The second characteristic, broad network access, means that cloud computing resources can be accessed via the network through standard mechanisms and platforms such as mobile phones, tablets, laptops, and workstations. The third characteristic, resource pooling, is what gives cloud providers economies of scale, which they pass on to their customers, making cloud cost-efficient. Using a multi-tenant model, computing resources are pooled to serve multiple consumers. Cloud resources are dynamically assigned and reassigned according to demand, without customers needing to concern themselves with the physical location of these resources. Rapid elasticity, the fourth characteristic, implies that you can access more resources when you need them and scale back when you don't, because resources are elastically provisioned and released. And the fifth characteristic, measured service, means that you only pay for what you use or reserve as you go. If you're not using resources, you're not paying. Resource usage is monitored, measured, and reported transparently based on utilization. As we see, cloud computing is really about utilizing technology as a service, leveraging remote systems on demand over the open internet, scaling up, scaling back, and paying for what you use. It is a revolution in that it has changed the way the world consumes compute services by making them more cost-efficient while also making organizations more agile in responding to changes in their markets. As I mentioned earlier in this talk, the cloud model is composed of 5 essential characteristics, 3 deployment models, and 3 service models. We just went over the 5 essential characteristics. While we will go into greater depth of the deployment and the service models in the later videos, let me leave you with a brief overview of these models. There are 3 types of cloud deployment models: public, private, and hybrid. Public cloud is when you leverage cloud services over the open internet on hardware owned by the cloud provider, but its usage is shared by other companies. private cloud means that the cloud infrastructure is provisioned for exclusive use by a single organization. It could run on-premises, or it could be owned, managed, and operated by a service provider. And when you use a mix of both public and private clouds working together seamlessly, that is classified as the hybrid model. Now, let's look at the three service models that are based on the three layers in a computing stack: infrastructure, platform, and applications. These cloud computing models are aptly referred to as infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. In an infrastructure as a service model, you get access to infrastructure and physical computing resources such as servers, networking, storage, and data center space without the need to manage or operate them. In a platform as a service model, you get access to the platform, that is, hardware and software tools, usually those needed to develop and deploy applications to users over the internet. Software as a service is a software licensing and delivery model in which software and applications are centrally hosted and licensed on a subscription basis, and sometimes also referred to as on-demand software. In the next training, we will go over some of the key evolutions that bring us to what cloud computing is today. Cloud computing is an evolution of technology over time. The concept of cloud computing dates to the 1950s when large-scale mainframes with high-volume processing power became available. In order to make efficient use of the computing power of mainframes, the practice of time-sharing or resource pooling evolved. Using dumb terminals, whose sole purpose was to facilitate access to the mainframes, multiple users were able to access the same data storage layer and CPU power from any terminal. In the 1970s, with the release of an operating system called Virtual Machine, or VM, it became possible for mainframes to have multiple virtual systems, or virtual machines, on a single physical node. The virtual machine operating system evolved the 1950s application of shared access of a mainframe by allowing multiple distinct compute environments to exist on the same physical hardware. Each virtual machine hosted guest operating systems that behaved as though they had their own memory, CPU, and hard drives, even though these were shared resources. Virtualization thus became a technology driver and a huge catalyst for some of the biggest evolutions in communications and computing. Even 20 years ago, physical hardware was quite expensive. With the internet becoming more accessible and the need to make hardware costs more viable, servers were virtualized into sharing hosting environments, virtual private servers, and virtual dedicated servers, using the same types of functionality provided by the virtual machine operating system. So, for example, if a company needed X number of physical systems to run their applications, they could take one physical node and split it into multiple virtual systems. This was enabled by hypervisors. A hypervisor is a small software layer that enables multiple operating systems to run alongside each other, sharing the same physical computing resources. A hypervisor also separates the virtual machines logically, assigning each its own slice of the underlying computing power, memory, and storage, preventing the virtual machines from interfering with each other. If, for example, one operating system suffers a crash or a security compromise, the others can keep working. As technologies and hypervisors improved and were able to share and deliver resources reliably, some companies decided to make the cloud's benefits accessible to users who didn't have an abundance of physical servers to create their own cloud computing infrastructure. Since the servers were already online, the process of spinning up a new instance was instantaneous. Users could now order cloud resources they needed from a larger pool of available resources, and they could pay for them on a per-use basis, also known as pay-as-you-go. This pay-as-you-go, or utility computing model, became one of the key drivers behind cloud computing taking off. The pay-per-use model allowed companies and even individual developers to pay for the computing resources as and when they used them, just like units of electricity. This allowed them to switch to a more cash flow-friendly OpEx model from a CapEx model. This model appealed to all sizes of companies, those who had little or no hardware, and even those that had lots of hardware, because now, instead of making huge capital expenditures in hardware, they could pay for compute resources as and when needed. It also allowed them to scale their workloads during usage peaks and scale down when usage subsided. And this gave rise to modern-day cloud computing. The impact of the evolution of the cloud has been immense. In the next training, we will go over some key considerations for cloud adoption. Every organization's transformation journey is unique, and therefore every organization's cloud adoption strategy is also unique to them. Agility, flexibility, and competitiveness are key drivers for moving to the cloud, provided it is done without creating business disruption or issues related to security, compliance, and performance. Let's look at some key considerations that organizations can use as a guide while working through their cloud strategy. The first consideration is infrastructure and workloads. The cost of building and operating data centers can become astronomical. On the other hand, low initial costs and pay-as-you-go attributes of cloud computing can add up to significant cost savings. Also, a point to consider is that not all workloads may be ready for the cloud as is. The second consideration is around software as a service and development platforms. Organizations need to consider if paying for application access is a more viable option than purchasing off-the-shelf software and subsequently investing in upgrades. Organizations need to consider speed and productivity, what it means for them to get a new application up and running in X hours on the cloud versus a couple of weeks or even months on traditional platforms, and the person-hour cost efficiencies they gain from using cloud dashboards, real-time statistics, and active analytics. Lastly, organizations need to consider the impact of making a wrong decision, their risk exposure. Is it riskier, for example, for them to invest in the hardware and software or rent by the hour? Is it safer for them to work on a 12-month plan to build, write, test, and release the code if they're uncertain about adoption? And is it better for them to try something new, paying as you go, rather than making long-term decisions based on little or no trial or adoption? Let's look at some of the benefits of cloud adoption, categorized broadly into flexibility, efficiency, and strategic value. Cloud gives us flexibility. Users can scale back or scale up services to fit their needs, customize applications, and access cloud services from anywhere with an internet connection. Cloud infrastructure scales on demand to support fluctuating workloads. Organizations can determine their level of control with as-a-service options. Users can select from a menu of pre-built tools and features to build a solution that fits their specific needs. And virtual private clouds, encryption, and API keys help keep data secure. Cloud also brings great efficiency. Enterprise users can get applications to market quickly without worrying about underlying infrastructure costs or its maintenance. Cloud-based applications and data are accessible from virtually any internet-connected device. Hardware failures do not result in data loss because of networked backups. Cloud computing uses remote resources, saving organizations the cost of servers and other equipment and paying on-use basis. Cloud services gives enterprises a competitive advantage by providing the most innovative technologies available while managing the underlying infrastructure, thus enabling organizations to focus on their priorities. While cloud brings great opportunity, it also introduces challenges for business leaders and IT departments. Some of these perceived risks include data security, associated with loss or unavailability of data, causing businesses disruption, governance and sovereignty issues, legal, regulatory, and compliance issues, lack of standardization in how the constantly evolving technologies integrate and interoperate, choosing the right deployment and service models to serve specific needs, partnering with the right cloud service providers, concerns related to business continuity and disaster recovery. Organizations can no longer think of cloud adoption as something that is to be looked at in the future. With the right cloud adoption strategies, technologies, services, and service providers, these risks can be mitigated. In the next training, we're going to look at some of the key cloud service providers of our times and the services they offer.
Let's look at some numbers and predictions that help us see the scale cloud is predicted to achieve in the coming years. Gartner predicts the worldwide public cloud service market to grow from $182.4 billion in 2018 to $331.2 billion in 2022, attaining a compound annual growth rate, or CAGR, of 12.6%. Spending on infrastructure as a service to increase from $30.5 billion in 2018 to $76.6 billion in 2022, growing 27.5% in a year. Platform as a service spending to grow from $15.6 billion in 2018 to $31.8 billion in 2022, growing 21.8% in a year. With software investments shifting from cloud first to cloud only, spending on software as a service is expected to grow from $80 billion in 2018 to $143.7 billion in 2022. What is clear is that cloud is accelerating faster than predicted, adoption is high, and revenues are soaring. The question for businesses today is no longer if they need to adopt the cloud, rather what their cloud adoption strategy should be to best serve their businesses and customers. Keeping up with this technological wave and driving it forward are the cloud service providers with a wide range of services. We will now talk about some of the major cloud service providers in an alphabetical order. Alibaba Cloud, also known as Aliyun, while relatively new, is the largest Chinese cloud computing service provider. Aliyun provides a comprehensive suite of global cloud computing services to power not just their customers' online businesses, but also the Alibaba Group's own e-commerce ecosystem. It offers a host of products and services such as compute, network, storage, security, monitoring and managing, communication, analytics, IoT, application development, data migration, web hosting, and more. One of the first to enter the cloud computing race, Amazon Web Services, or AWS Cloud, offers an extensive range of infrastructure and platform services to individuals, companies, and governments on a metered pay-as-you-go basis. The Amazon Cloud provides a wide range of products, services, and solutions ranging from compute, DevOps, data, analytics, IoT, machine learning, networking, content delivery, robotics, serverless computing, and much more. Google Cloud Platform, or GCP, is a suite of cloud computing services providing infrastructure, platform, and serverless computing environments. Google also uses GCP internally for their end-user products such as Google Search and YouTube. Google Cloud includes G Suite with products for communication, productivity, collaboration, storage, and more. The Google App Engine is a platform for developing and hosting web applications in Google-managed data centers, automatically allocating and deallocating resources to handle demand. IBM Cloud is a full-stack cloud platform that spans public, private, and hybrid environments with products and services covering compute, network, storage, management, security, DevOps, and databases. Some of their prominent offerings include their bare metal servers, VMware, cloud packs for application modernization, virtual private cloud, and the suite of emerging technologies such as AI, IoT, blockchain, data, and analytics. With the acquisition of Red Hat, IBM is also positioning itself as the leading hybrid cloud provider of our times. Microsoft Azure is a flexible cloud platform for building, testing, deploying, and managing applications and services through Microsoft-managed data centers. With its data centers spread out in many regions, Azure provides a global reach with a local presence. It provides software, platform, and infrastructure services supporting Microsoft-specific and third-party languages, tools, and frameworks. Oracle Cloud is primarily known for software as a service and database as a service, also known as the Oracle Data Cloud. Oracle's software as a service offering includes wide-ranging applications such as ERP, SCM, HCM, marketing, sales, and CX running in the cloud. And the Oracle Data Cloud provides one of the largest cloud-based data management platforms, helping customers personalize their online, offline, and mobile marketing campaigns for targeted audiences. Oracle Cloud also provides some cloud infrastructure and platform services. Salesforce specializes in their software as a service offering that focuses on customer relationship management, supporting businesses to better connect with their customers, partners, and potential customers. Salesforce offers multiple cloud services such as Sales Cloud, Service Cloud, and Marketing Cloud, helping customers track analytics in real time, customer success and support, customer complaints, even listening in to customers across social platforms to automatically route them to appropriate agents for resolution. SAP is known for enterprise software and applications such as ERP, CRM, HR, and finance running in the cloud. There is also a SAP Cloud Platform for building and extending business applications with rapid innovation cycles in a secure cloud computing environment managed by SAP. In the next video, we're going to look at the business case for cloud computing.
Cloud adoption is no longer a thing of the future. From a single individual to a global multi-billion-dollar enterprise, anybody can access the computing capacity they need on the cloud. The lag time from decision to value is no longer a journey of years with high upfront capital. Cloud makes it possible for businesses to experiment, fail, and learn much faster than ever before with low-risk exposure. Businesses today have greater freedom to change course than to live with the consequences of expensive decisions taken in the past. According to an IBM Institute for Business Value study, more than 3/4 of enterprises today are using cloud computing to expand into new industries. 74% have adopted cloud to improve customer experience, and 71% use cloud to create enhanced products and services while simultaneously downsizing legacy systems and reducing costs. To remain competitive, businesses need to be able to respond quickly to marketplace changes, use analytics to understand customer experience, and apply that understanding to adapt their products and services based on what they learn. Product life cycles have shortened and barriers to entry have become lower. Cognitively enabled workflows, applied exponential technologies such as AI, automation, IoT, and blockchain, applications that span new and legacy solutions, and open, hybrid, and secure multi-cloud infrastructures are today's enablers for growth, agility, and innovation. The power, scalability, flexibility, and pay-as-you-go economics of cloud has made it the underpinning foundation for digital transformation. The International Data Corporation, IDC, predicts that by 2025, the total amount of digital data created worldwide will rise to 163 zettabytes, where 1 zettabyte is equivalent to 1 trillion gigabytes. And 30% of this data will be real-time information. Considering the unprecedented amounts of data being produced daily and the ability to make data-driven decisions crucial to any business, cloud computing becomes essential for businesses to succeed, sustain, and compete in today's markets. A cloud strategy, more than just an IT strategy, is the core component of any business strategy today. Businesses that haven't already or are not currently integrating cloud into their business strategy run the risk of lacking the speed, agility, innovation,
and decision-making capacities needed to be competitive,
as also their ability to respond to digital disruption. In the next video, we'll look at some case studies that demonstrate the impact businesses have created by adopting cloud.
In this video, we will look at how some of the leading businesses have transformed the way they work to provide better customer service, remove barriers to innovation, achieve enterprise scale, and accelerate growth using cloud technologies. Although the case studies we'll look at are curated from IBM Cloud, similar stories with dramatic impact to business can be found across the spectrum of companies utilizing other cloud service providers as well. Better customer service. In the highly competitive airline industry, customer experience is a major point of differentiation, and digital channels are increasingly important. To become more responsive to customer needs, American Airlines needed a new technology platform and a new approach to development that would help it deliver digital self-service tools and customer value more rapidly across its enterprise. The airline recognized the opportunity to remove the constraints of their existing customer-facing applications based on monolithic code into cloud-native-based microservices architecture on the cloud. The results? Faster development and release of new apps, improved operational reliability, productivity, and end customer response times. Cost savings by avoiding existing upgrade costs via migration to the IBM Cloud. Removing barriers to innovation. As a lean organization with a self-imposed limit on headcount, UBank excels at finding innovative ways to meet demands. Continually challenged to find more efficient ways to operate, UBank's IT team explored a platform as a service, or PaaS, cloud development model. Their need was to give more control to their developers, reduce the need for additional resources, faster speed to market, and removing barriers in going from an idea to production. UBank launched new initiatives in an IBM Cloud Platform environment, including a virtual assistant that incorporates IBM Watson technology to support the bank's online home loan application. The results? Faster time to market made possible through the Cloud Platform framework that streamlines development and empowers product teams. Foster greater innovation with cloud-based development resources that are quick, easy, and cost-effective to deploy. More efficient operations. Demand for enterprise scale. Since its inception in 2008, Bitly has journeyed from a startup that offered intelligent link shortening technology adopted by users to compress lengthy URLs for social media posts to an enterprise product. Seeking an agile, cost-effective IT infrastructure to support this transition, Bitly started planning for cloud migration. Their need was to have a cloud-based model with pay-as-you-go pricing, the ability to scale up and down, a more global presence, and the ability to geo-distribute into more POPs. And they wanted it to be low risk. Bitly migrated to an IBM Cloud environment, establishing a scalable hosting platform for low-latency delivery to enterprise customers around the world. The results? 25 billion data-infused links migrated from one hosting site to cloud infrastructure with data center locations worldwide. 1 billion user interaction dataset stored, and managed in a flexible, cost-effective cloud object storage environment. Transformed IT operations to scale for growth, control costs, and focus valuable resources on new product development. Accelerating growth. Financial traders demand extreme speed and availability from trading systems. Profitability depends on split-second decisions. As a leading online broker for Forex, commodities, equities, cryptocurrencies, indices, and other financial instruments, Active Trades enables investors to buy and sell on numerous financial markets. Investors need reliable access to accurate market information, combined with the ability to move rapidly to execute trades. As its client base grew, Active Trades wanted to cut latency, accelerate execution, and streamline the delivery of new functions. Active Trades migrated 3 major trading systems from on-premise infrastructure to IBM Cloud for VMware solutions, backed by data storage, networking, and security offerings on the IBM Cloud. The results: up to 3 times performance boost, helping clients seize fleeting opportunities for profit. Security-rich cloud platform with ultra-high availability protects client investments. Hours, not days, to fire up new resources for faster response to emerging requirements. In the next video, we'll look at some of the emerging technologies that are available on the cloud and the opportunities they bring to businesses.
In this new era, technologies such as Internet of Things, big data, artificial intelligence, and blockchain are disrupting existing business models and industries while creating unprecedented opportunities for businesses to differentiate themselves and create value for their clients. The power, scale, dynamic nature, and economics of the cloud resources make cloud computing a key enabler for adoption and evolution of these emerging technologies. In this video, we will look at how the Internet of Things, or IoT, powered by cloud, is making a big difference for businesses today. The Internet of Things, or IoT, is a giant network of connected things and people that have changed much of how we live our daily lives, from the way we drive to how we make purchases, monitoring our personal health, and even how we get energy for our homes. Smart devices and sensors are continuously tracking and collecting data. For example, a smart building could have thousands of sensors measuring all kinds of data related to thermal, optical, structural, and environmental stimuli. An unprecedented amount of data is being generated, putting a tremendous strain on the internet. That is where the cloud comes in. By connecting the IoT device user to the cloud, be it for device registration, device identity, storing data, or accessing enterprise data. Data collected through IoT devices is stored and processed on the cloud. Since IoT devices can be in a state of motion, the cloud serves as a collection point in closest proximity, minimizing the latency in reporting up the data points and providing a response back to the IoT application. So, from IoT platforms running entirely on the cloud, to the interfaces used by customers to interact with these devices, to the back-end analytics platforms, cloud computing supports and enables IoT. Cloud service providers also offer specialized IoT services designed to help speed up the development of IoT solutions. Let's look at a case study that demonstrates the use of the IoT on the cloud to combat the poaching of endangered rhinos at Welgevonden by making poaching predictable.
The rhino has become one of the key species that is becoming endangered due to poaching throughout Africa, but now especially in South Africa. Up until now, poachers have been increasing in numbers and they've become more militarized with weapons. And so, of course, we've had to do the same. This is not sustainable. The only way to do this better is to bring in technology and things that they do not have.
This endangered species is getting help from some unexpected friends. The zebra and antelope. They're wearing IoT sensors connected to the IBM cloud. When poachers enter the area, the animals run for it, which alerts rangers who can track their motions and help stop them before any harm is done. It's a smart way to help increase the rhino population and turn the poachers into the endangered species.
In the next video, we're going to look at how artificial intelligence on the cloud is impacting businesses.
Making sense of the endless streams of data is where artificial intelligence, or AI, comes in. Many of the applications where we apply AI today simply wouldn't have been possible without the scalable, on-demand computing offered by the cloud. There is a three-way relationship between AI, IoT, and cloud. Just as AI consumes the data produced by IoT devices, the IoT device's behavior can be dictated based on responses from AI. For example, smart assistants. A common type of IoT device continues to learn about the user's preferences as usage grows, such as songs they like, their home temperature settings, preferred meal times, and over time, they anticipate their actions based on the user's past history. So what we see is a symbiotic relationship between IoT, AI, and cloud. IoT delivers the data, AI powers the insights, and both these emerging technologies leverage cloud scalability and processing power to provide value to individuals and businesses alike. Let's look at how the United States Tennis Association, USTA, is using AI on the cloud to deliver unique digital experiences to millions of fans around the world.
For 2 weeks at the end of every summer, tennis fans around the world turn their eyes to New York City and the US Open.
Hundreds of thousands on site and millions more online. But where you see tennis, IBM sees data. The scores and statistics, the sights, the sounds. IBM integrates and analyzes the data flowing from the court and delivers unique digital experiences to more than 10 million tennis fans around the world. And we do it all in the IBM Cloud.
The IBM Cloud is the digital foundation of the US Open. It scales rapidly to meet a 5,000% increase in web traffic, and it delivers a consistent experience to our fans all around the globe. And with Watson on the IBM Cloud, we can engage fans in unique ways, year after year.
Slam Tracker analyzes more than 26 million historical data points. It gives fans deep insight into featured matches, and it can see the momentum of a match shifting in real time.
AI Highlights uses Watson to process thousands of hours of US Open video. It can hear the cheers of the crowd. It can see a player celebrating, and it knows what makes a great tennis highlight.
And this year, we're putting the power of AI Highlights into the hands of US players and coaches. Watson is analyzing match video so coaches can quickly find the footage they need to guide the development of their players. And if you need to know where to park, find a good burger, or grab the latest US Open gear, you can find the answers with the guest information feature in the US Open app and mobile web using Watson.
We work with IBM because they keep us on the cutting edge of the fan experience. They help us to adopt the latest technology, like cloud and AI. And they bring data to life in a way that's accessible and engaging for our fans.
In the next video, we're going to look at how blockchain and analytics on the cloud are impacting businesses. Blockchain is a secure, distributed, open technology that can help speed up processes, lower costs, and build transparency and traceability in transactional applications. It is an immutable network allowing members to view only those transactions that are relevant to them. The more open, diverse, and distributed the network, the stronger the trust and transparency in the data and transactions. 85% of businesses today rely on multiple clouds to meet their IT needs, with more than 70% using more than 3. These businesses need to be able to move applications and data across multiple clouds easily and securely, leading to the emerging demand to build and manage business applications such as blockchain for the multi-cloud environment. Blockchain and AI, much like IoT and AI, powered by the cloud, also have a three-way relationship, where blockchain technology provides the trusted, decentralized source of truth. AI powers the analytics and decision-making from the data collected, and cloud provides globally distributed, scalable, and cost-efficient computing resources to support both the unprecedented amounts of data being collected and the processing power required to draw insights from this data. Blockchain serves to make AI more understandable by recording the data and variables that go into a decision made in an AI algorithm, leading to greater trust and transparency in the conclusions and decisions made by these algorithms. Let's look at how blockchain on the cloud is helping farmers reduce waste at times of recall by building traceability and transparency in the food supply chain.
For farmers here, this is our life's work. 60% of the nation's lettuce is grown right here in Salinas. When it comes down to how plants are looked at, I really relate back to how humans are raised and nurtured. I want to make sure that everything is safe before it leaves the ranch. But when a recall happens, perfectly good food goes to waste. You have to take all product off your shelf, no matter what age, no matter where it came from.
And it takes resources to grow those things.
Then now we're actually eating into our future food supply. But we've got a way around that. Blockchain technology on the IBM cloud,
We're able to track our product within seconds, giving the consumers instant access where the product came from in case there's any recall.
so we don't have to take all the food off the shelves. Having that instant access allows you to reduce the waste.
There's a lot of starving people in this world.
A nice wedge. I want to be the generation that fixes that.
Daddy's lettuce? Yeah, it is.
Analytics technologies on the cloud leverage the flexibility, scalability, and computing resources available on the cloud. From tracking trends on social media to predict future events, to analyzing data to build machine learning models that can be deployed in cognitive applications, cloud provides the integrated environment that is required to leverage data for continuous improvement and accelerated business growth. Let's look at how Kone has invested in cloud and IoT technologies to power a data analytics and predictive maintenance solution for city infrastructure used by more than 1 billion people daily.
At Kone, we manufacture elevators, escalators, auto walks, and doors. All of these devices are streams of data that we are collecting. In order to process those streams, we need a scalable way of handle the amount of data that is coming in. And that's where Cloud Function fits in perfectly. We handle that data with event-driven architecture. We use functions to persist that data and to generate further events on that data that are then utilized and consumed by applications and our customers and users. In our analytics platform, we analyze the set of data and we generate value, predictive in a sense that we can predict the failure rate to a certain percentage that is about to happen in the future for our equipment. And this allows us to perform predictive maintenance. And this is kind of the whole concept that we have behind our 24/7 connected services, which is a promise to our customers that the equipment is connected to the cloud and we are monitoring it, and that's where we generate the real value for our customers from a maintenance perspective. At the moment, we use almost all aspects of the IBM cloud. We use storage from the cloud, we use Cloud Functions, we use messaging services, we use IoT services. So a number of services are already in use in platform, and that use will only grow as our digital footprint in the industry grows.
In our introductory cloud video, we briefly talked about the 3 service models available on the cloud: infrastructure as a service, platform as a service, and software as a service. Before we dive into the details of each of these service models in the subsequent videos, let's get started with a quick overview of these models.
Hi, I'm Tessa Rhodes, and I'm a designer on IBM Cloud. So let's start with the foundation here with IaaS. IaaS is a set of compute, networking, and storage resources that have been virtualized by a vendor so that a user can access and configure them any way they want. In design, we have a concept of talking about users called personas, and the persona for IaaS is a system admin or an IT admin. Let's jump up to the top with software as a service. That's the easy one. Software as a service is just software that you don't have to install on your machine and you don't have to manually update. And so the user for software as a service could be anyone. In fact, if you're watching this on YouTube right now, then you're a user of software as a service. It's usually charged on a subscription model rather than a one-time license fee. Then that brings us to platform as a service. PaaS takes advantage of all the virtualized resources from IaaS and then just abstracts them away so the user doesn't have to worry about managing any of those virtualized resources. The user for PaaS is not a system admin, usually. It's usually a dev. In IBM, we call this dev Jane. That's the name of our persona. And so this whole metaphor, the pyramid metaphor, is meant to indicate that as you move down, you're increasing complexity in terms of your knowledge and management of infrastructure resources, and you're increasing the ease of use. Another metaphor I use when I'm talking to the designers on my team about PaaS is having to do with a car. So in this metaphor, IaaS is like leasing a car. So if you've ever leased a car, you probably did a lot of research and you care about the specs of the car and their performance. You care about the color of the car, what kind of car it is, and you're the one driving and you're paying for it. You're also paying for the gas and any tolls or maintenance. With platform as a service, in this metaphor, that's more like renting a car. So say you're on vacation and you just got off the airport and you're going to pick up your rental car. You don't really care what color it is. You don't really even care about the specs of it, but you're still driving and you're paying for the gas and any tolls you go through. Software as a service is, again, the easiest one. That one's more like getting a taxi or an Uber. So with a taxi or an Uber, you don't care at all about what kind of car it is, what color it is, and in fact, you're not even the one driving or paying for gas or any tolls, because that's baked into the price.
So, let's see what it means in terms of cloud computing and its 3 service models. With IaaS, the cloud provider manages the physical resources, data centers, cooling, power, network and security, as well as computing resources that include servers and storage. With PaaS, the provider, in addition to the computing resources, also manages the platform infrastructure, which includes the operating systems, development tools, databases, and business analytics. In the SaaS model, in addition to the infrastructure and the platform resources, the provider also hosts and manages the applications and data. In the next video, we'll take a closer look at infrastructure as a service, its features, benefits, and some use cases. In this video, we will discuss the infrastructure as a service model in more detail. Infrastructure as a service, commonly referred to as IaaS or simply IaaS, is a form of cloud computing that delivers fundamental compute, network, and storage resources to consumers on demand over the internet on a pay-as-you-go basis. The cloud provider hosts the infrastructure components traditionally present in an on-premises data center, as well as the virtualization or hypervisor layer. In an IaaS cloud environment, customers can create or provision virtual machines, or VMs, in their choice of region and zone available from the cloud provider. These VMs typically come pre-installed the customer's choice of operating system. The customers can then deploy middleware, install applications, and run workloads on these VMs. They can also create storage for their workloads and backups. Cloud providers often provide customers the ability to track and monitor the performance and usage of their cloud services and manage disaster recovery. Let's look at the key components of cloud infrastructure. Physical data centers. IaaS providers manage large data centers that contain the physical machines required to power the various layers of abstraction on top of them. In most IaaS models, end users do not interact directly with the physical infrastructure, but experience it as a service provided to them. Compute. IaaS providers manage the hypervisors, and end users programmatically provision virtual instances with desired amounts of compute, memory, and storage resources. Cloud compute typically comes with supporting services like auto-scaling and load balancing that provide scalability and high performance. Network. Users get access to networking resources on the cloud through virtualization or programmatically through APIs. Storage. There are 3 types of cloud data storage: object, file, and block storage. Object storage is the most common mode of storage in the cloud, given that it is highly distributed and resilient. IaaS supports a wide array of use cases. We'll look at some typical use cases here. Organizations today are using cloud infrastructure services to enable their teams to set up test and development environments faster, helping create new applications more quickly. By abstracting the low-level components, cloud infrastructure is helping developers focus more on business logic than infrastructure management. Business continuity and disaster recovery require a significant amount of technology and staff investments. IaaS is helping organizations reduce this cost and make applications and data accessible as usual during a disaster or outage. Organizations are using cloud infrastructure to deploy their web applications faster and also scale infrastructure up and down as demand fluctuates. Organizations are leveraging the high-performance computing capabilities of cloud infrastructure to solve complex problems involving millions of variables and calculations, such as climate and weather predictions and financial modeling. Mining massive data sets to locate valuable patterns, trends, and associations requires a huge amount of processing power. Cloud infrastructure not only provides the required high-performance computing, but also makes it economically viable. While there are some concerns regarding the lack of transparency in the cloud infrastructure's configuration and management, and dependency on a third party for workload availability and performance, infrastructure as a service is the fastest growing cloud model today. In the next video, we will look at platform as a service model, its features, benefits, and some use cases. Platform as a Service, commonly referred to as PaaS or simply PaaS, is a cloud computing model that provides customers a complete platform to develop, deploy, manage, and run applications created by them or acquired from a third party. The PaaS provider hosts everything: servers, networks, storage, operating system, application runtimes, APIs, middleware, databases, and other tools at their data center. The provider also takes responsibility for the installation, configuration, and operation of the application infrastructure, leaving the user responsible for only the application code and its maintenance. Customers pay for this service on a usage basis and purchase resources on demand. With IaaS, the cloud provider offers access to raw computing resources, such as servers, storage, and networking, while the user is responsible for the platform and application software. With PaaS, or PaaS, the cloud service provider delivers and manages the entire platform infrastructure, abstracting users from the lower-level details of the environment. Let's look at some essential characteristics of Platform as a Service, or PaaS. PaaS clouds are distinguished by the high level of abstraction they provide to the users, eliminating the complexity of deploying applications, configuring infrastructure, and provisioning and configuring supporting technologies like load balancers and databases. PaaS clouds provide services and APIs that help simplify the job of developers in delivering elastically scalable and highly available cloud applications. These services typically include a variety of capabilities, such as APIs for distributed caching, queuing, and messaging, file and data storage, workload management, user identity, and analytics, thus eliminating the need to integrate disparate components. The PaaS runtime environment executes end-user code according to policies set by the application owner and cloud provider. Many of the PaaS offerings provide developers with rapid deployment mechanisms, or push-and-run mechanism, for deploying and running applications. PaaS offerings support a range of application infrastructure or middleware capabilities, such as application servers, database management systems, business analytics servers, mobile backend services, integration services, business process management systems, rules engines, and complex event processing systems. Such an application infrastructure assists developers by reducing the amount of code that must be written while expanding the application's functional capabilities. The most important use case for PaaS is strategic. Build, test, deploy, enhance, and scale applications rapidly and cost-effectively. Let's look at some more use cases for PaaS. API development and management. Organizations are using PaaS to develop, run, manage, and secure APIs and microservices, which are loosely coupled, independently deployable components and services. Internet of Things, or IoT. PaaS clouds support a broad range of application environments, programming languages, and tools used for IoT deployments. Business analytics or intelligence. PaaS tools allow organizations to analyze their data to find business insights that enable more informed business decisions and predictions. Business process management, or BPM. Organizations are using the PaaS cloud to access BPM platform delivered as a service. Master data management, or MDM. Organizations are leveraging the PaaS cloud to provide a single point of reference for critical business data, such as information about customer transactions and analytical data to support decision-making. Let's look at some advantages of using PaaS. Scalability, made possible because of the rapid allocation and deallocation of resources with a pay-as-you-use model offered by PaaS. The APIs, support services, and middleware capabilities that PaaS clouds provide assist developers in focusing their efforts on application development and testing, resulting in faster time to market for their products and services. Middleware capabilities also reduce the amount of code that need to be written while expanding the application's functional capabilities. Greater agility and innovation, because using PaaS platforms means that you can experiment with multiple operating systems, languages, and tools without having to invest in these resources. You can evaluate and prototype ideas with very low risk exposure, resulting in faster, easier, less risky adoption of a wider range of resources.
Some of the key PaaS offerings available in the market today include AWS Elastic Beanstalk, Cloud Foundry, IBM Cloud Paks, Windows Azure, Red Hat OpenShift, Magento Commerce Cloud, Force.com, and Apache Stratos.
PaaS clouds do come with some risks. risks that all cloud offerings have in general, such as information security threats and dependency on the service provider's infrastructure. Services can get impacted when a service provider's infrastructure experiences downtime. Customers also don't have any direct control over the changes that may take place when a provider makes changes in its strategy, service offerings, or tools. But the benefits can far outweigh these risks. PaaS continues to experience strong growth and is predicted to become the prevailing platform delivery model moving forward. In the next video, we will look at software as a service model, its features, benefits, and some use cases. Software as a Service, or SaaS, is a cloud offering that provides users with access to a service provider's cloud-based software. SaaS providers maintain the servers, databases, and code that constitute an application. They also manage access to the application, including security, availability, and performance. Applications reside on a remote cloud network, and users use these applications without having to maintain and update the infrastructure. Core business processes supported by SaaS today include email and collaboration via offerings such as Microsoft's Office 365 and Google's Gmail, customer relationship management via services such as NetSuite CRM and Salesforce, human resource management via services from Workday and SAP SuccessFactors, financial management, billing collaboration, and many more. According to Forrester Research, SaaS has overtaken on-premises solutions in categories such as human capital management, HCM, customer relationship management, CRM, and collaboration. Solutions once available with several different deployment options are now SaaS only. Let's look at key characteristics of software as a service. SaaS clouds have a multi-tenant architecture. Infrastructure and code are maintained centrally and accessed by all users. SaaS makes it easy for users to manage privileges, monitor data use, and ensure everyone sees the same information at the same time. Security, compliance, and maintenance are all part of the offering. Users can customize applications to fit their business processes with point-and-click ease. Users can customize the UI to work with their branding guidelines. They can modify data fields and enable or disable features within the business process. These customizations are preserved through upgrades. Users pay for the use of the service via a subscription model. The use of resources can be scaled easily depending on service needs. Key benefits of adopting SaaS: businesses can directly procure solutions without upfront capital and assistance from IT, greatly reducing the time from decision to value from months to days. SaaS greatly increases workforce productivity and efficiency. Users can access code business apps from wherever they are. They can also buy and deploy apps in minutes, reducing the typical obstacles enterprises have to test the products they might use. Using SaaS applications, individuals and small enterprises can spread out their software costs over time. Let's look at some use cases for SaaS. Organizations are moving to SaaS for their core business needs as part of their strategic transformation to reduce on-premises IT infrastructure and reduce capital expenditure. Organizations are leveraging SaaS to avoid the need for ongoing upgrades, maintenance, and patching done traditionally by internal IT resources. Applications run reliably with minimal input, for example, email servers and office collaboration and productivity tools. Organizations are increasingly opting for SaaS e-commerce platforms to manage their websites, marketing, sales, and operations. With SaaS, organizations are able to take advantage of the resilience and business continuity of the cloud provider. Enterprises are now developing SaaS integration platforms, or SIPs, for building additional SaaS applications. moving SaaS beyond standalone software functionality to a platform for mission-critical applications. SaaS does evoke some concerns as well, primary among them being data ownership and data safety. Security is an important consideration when you're allowing a third party to maintain business-critical data. And application access relies on a good internet connection. If you're not connected, you cannot access the apps. But the benefits far outweigh the concerns, with SaaS making up the largest segment of the cloud market today. In our introductory cloud video, we briefly mentioned the 3 deployment models for cloud. In this video, we will discuss the public cloud deployment model in more detail. Deployment models indicate where the infrastructure resides, who owns and manages it, and how cloud resources and services are made available to users. The 3 cloud deployment models include public cloud, private cloud, and hybrid cloud. In a public cloud model, users get access to servers, storage, network, security, and applications as services delivered by cloud service providers over the internet. Using web consoles and APIs, users can provision the resources and services they need. The cloud provider owns, manages, provisions, and maintains the infrastructure, renting it out to the customers either for subscription charge or usage-based fee. Users don't own the servers their applications run on, or storage their data consumes, or manage the operations of the servers, or even determine how the platforms are maintained. In very much the same way that we consume and pay for utilities, such as water, electricity, or gas in our everyday lives, we don't own any of these cloud resources. We make an agreement with the service provider, use the resources, and pay for what we use within a certain period. Public clouds offer significant cost savings as the provider bears all the capital, operational, and maintenance expenses for the infrastructure and the facilities they are hosted in. It makes scalability as easy as requesting more capacity. However, with a public cloud, the user does not have any control over the computing environment and is subject to the performance and security of the cloud provider's infrastructure. There are several public cloud providers in the market today, such as Amazon Web Services, Microsoft Azure, IBM Cloud, Google Cloud Platform, and Alibaba Cloud. While all providers include a common set of core services, such as servers, storage, network, security, and databases, they also offer a wide spectrum of niche services with varied payment options. Let's talk about some of the characteristics of a public cloud. A public cloud is a virtualized multi-tenant architecture enabling tenants or users to share computing resources, residing outside their firewalls. The cloud provider's pool of resources, including infrastructure, platforms, and software, are not dedicated for use by a single tenant or organization. Resources are distributed on an as-needed basis, offered through a variety of subscription and pay-as-you-go models. Public clouds have significant benefits. We'll go over some of these benefits here. Vast, on-demand resources are available, allowing applications to respond seamlessly to fluctuations in demand. Considering the large number of users that share the centralized cloud resources on demand, the public cloud offers the most significant economies of scale. The sheer number of server and network resources available on the public cloud means that a public cloud is highly reliable. If one physical component fails, the service still runs unaffected on the remaining available components. It's also important to note some concerns users have regarding public clouds, key among them being security and data sovereignty compliance. Security issues such as data breaches, data loss, account hijacking, insufficient due diligence, and system and application vulnerability seem to be some of the fears users continue to have concerning security in the public cloud. With data being stored in different locations and accessed across national borders, it has become increasingly critical for companies to be compliant with data sovereignty regulations governing the storage, transfer, and security of data.
A service provider's ability to not just keep up with the regulations, but also the interpretation of these regulations is a concern shared by many businesses. Let's look at some common use cases for public cloud. Organizations are increasingly opting to access cloud-based applications and platforms so their teams can focus on building and testing applications and reducing time to market for their products and services. Businesses with fluctuating capacity and resourcing needs are opting for the public cloud. Organizations are using public cloud computing resources to build secondary infrastructures for disaster recovery, data protection, and business continuity. More and more organizations are using cloud storage and data management services for greater accessibility, easy distribution, and backing up of their data. IT departments are outsourcing the management of less critical and standardized business platforms and applications to public cloud providers. In the next video, we will look at the private cloud model, its features, benefits, and some use cases. The National Institute of Standards and Technology defines private cloud as cloud infrastructure provisioned for exclusive use by a single organization comprising multiple consumers, such as the business units within the organization. It may be owned, managed, and operated by the organization, a third party, or some combination of them, and it may exist on or off premises. Private cloud platforms can be implemented internally or externally. When the platform is provisioned over an organization's internal infrastructure, it runs on-premises and is owned, managed, and operated by the organization. When it is provisioned over a cloud provider's infrastructure, it is owned, managed, and operated by the service provider. This external private cloud offering that resides on a cloud service provider's infrastructure is called a virtual private cloud, or VPC. A VPC is a public cloud offering that lets an organization establish its own private and secure cloud-like computing environment in a logically isolated part of a shared public cloud. Using a VPC, organizations can leverage the dynamic scalability, high availability, and lower cost of ownership of a public cloud while having the infrastructure and security tailored to the organization's unique needs. Virtual private clouds are offered by most public cloud providers, such as IBM and Amazon. A private cloud is a virtualized environment modeled to bring in the benefits of a public cloud platform without the perceived disadvantages of an open and shared public platform. Users of a private cloud, such as developers and business units in an organization, still get to leverage benefits such as economies of scale, granular scale, operational efficiencies, and user self-service, while exercising full control over access, security, and compliances specific to their organization and business. Private clouds provide you with 1. The ability to leverage the value of cloud computing using systems that are directly managed or under perceived control of the organization's internal IT. 2. The ability to better utilize internal computing resources, such as the organization's existing investments in hardware and software, thereby reducing costs. 3. Better scalability through virtualization and cloud bursting. That is, leveraging public cloud instances for a period of time but returning to the private cloud when the surge is met. 4. Controlled access and greater security measures customized to specific organizational needs. 5. The ability to expand and provision things in a relatively short amount of time, providing greater agility. Organizations may choose to opt for private cloud because of various reasons. Because their applications provide a unique competitive advantage, there are security and regulatory concerns, or because their data is highly sensitive and subject to strict industry or governmental regulations. Let's look at some common use cases for a private cloud. 1. A private cloud is an opportunity for organizations to modernize and unify their in-house and legacy applications. Moving these applications from their dedicated hardware to the cloud also allows them to leverage the power of the compute resources and multiple services available on the cloud. 2022. Using the private cloud, organizations are integrating data and application services from their existing applications with public cloud services. This allows them to leverage their private cloud's compute capability for the larger jobs while pulling data into an application on a private cloud to leverage public cloud services, essentially opening their data centers to work with cloud services. 3. Application portability is a key feature of cloud platforms. Using the private cloud gives organizations the ability to build applications anywhere and move them anywhere without having to compromise security and compliance in the process. 4. Some of the key reasons that may prevent an organization from moving to a public cloud include security and regulatory concerns and data sensitivity. A private cloud offers these organizations the benefits of on-demand enterprise resources while exercising full control over critical security and compliance issues from within the environment of their dedicated cloud. In the next video, we will look at the hybrid cloud model, its features, benefits, and some use cases. Hybrid cloud is a computing environment that connects an organization's on-premise private cloud and third-party public cloud into a single, flexible infrastructure for running the organization's applications and workloads. The mix of public and private cloud resources gives organizations the flexibility to choose the optimal cloud for each application or workload. Workloads move freely between the two clouds as needs change. Organizations can choose to run the sensitive, highly regulated, and mission-critical applications or workloads with reasonably constant performance and capacity requirements on private cloud infrastructure, while deploying the less sensitive and more dynamic workloads on the public cloud. With proper integration and orchestration between the public and private clouds, you can leverage both clouds for the same workload. For example, you can leverage additional public cloud capacity to accommodate a spike in demand for a private cloud application, also known as cloud bursting. The key tenets of a hybrid cloud are interoperability, scalability, and portability. Hybrid cloud is interoperable, which means that the public and private cloud services can understand each other's APIs, configuration, data formats, and forms of authentication and authorization. When there is a spike in demand, a workload running on the private cloud can leverage the additional public cloud capacity, making it scalable. A hybrid cloud is also portable. Since you're no longer locked in with a specific vendor, you can move applications and data not just between on-premise and cloud systems, but also between cloud service providers. Hybrid is about taking the best of both worlds. There are two common types of hybrid clouds: hybrid monocloud and hybrid multi-cloud. A hybrid monocloud is a hybrid cloud with one cloud provider, while a hybrid multi-cloud is an open standards-based stack that can be deployed on any public cloud infrastructure. The difference lies in the flexibility that the hybrid multi-cloud offers organizations to move workloads and environments from one vendor to another. There is also a variant of hybrid multi-cloud called the composite multi-cloud, which makes this flexibility even more granular as it distributes single applications across multiple providers, allowing you to move application components across cloud services and vendors as needed. Hybrid cloud offers significant benefits in areas of security and compliance, scalability and resilience, resource optimization, and cost saving. A hybrid cloud lets organizations deploy highly regulated or sensitive workloads in a private cloud while running the less sensitive workloads on a public cloud. Using a hybrid cloud, you can scale up quickly, inexpensively, and even automatically using the public cloud infrastructure, all without impacting the other workloads running on your private cloud. Because you're not locked in with a specific vendor, and also don't have to make either-or decisions between the different cloud models, you can make the most cost-efficient use of your infrastructure budget. You can maintain workloads where they are most efficient,
spin up environments using pay-as-you-go in public cloud, and rapidly adopt new tools as you need them. A typical organization will have a range of applications and workloads spread across private, public, and traditional IT environments. This represents a range of opportunities for optimization via a hybrid cloud approach. Let's look at some increasingly common hybrid cloud use cases. Software as a service integration. Through hybrid integration, organizations are connecting software as a service applications available in the public cloud to their existing public cloud, private cloud, and traditional IT applications to deliver new solutions. Data and AI integration. Organizations today are creating richer and more personal experiences by combining new data sources on the public cloud, such as weather, social, the Internet of Things, CRM, and ERP, with existing data and analytics, machine learning, and AI capabilities. Enhancing legacy apps. An increasing number of organizations are using public cloud services to upgrade their user experience of their on-premises applications and deploy them globally to new devices, while incrementally modernizing their core business systems. VMware migration. More and more organizations are lifting and shifting their on-premises virtualized workloads to a public cloud without conversion or modification to reduce their on-premises data center footprint and position themselves to scale without added capital expense.
Hybrid cloud is a concept that's been around for quite some time, but we're finding that it's becoming increasingly used to architect and modernize existing or legacy applications. According to research, we've found that 75% of non-cloud applications will be moving to the cloud in the next 3 years. This goes to say that if you're not already thinking about your hybrid cloud strategy, you may be falling behind.
After choosing the cloud service model and the cloud type offered by vendors, customers need to plan the infrastructure architecture. The infrastructure layer is the foundation of the cloud. This layer consists of physical resources that are housed by regions, zones, and data centers. A cloud provider's IT environment is typically distributed across regions around the world. A cloud region is a geographic area or location where a cloud provider's infrastructure is clustered and may have names like NA South or US East. The cloud regions are isolated from each other so that if one region was impacted by a natural disaster, like an earthquake, the cloud operations in other regions would keep running. Each cloud region can have multiple zones, or availability zones, or AZ for short, which are typically distinct data centers with their own power, cooling, and networking resources.
These zones can have names like DAL09 or US East 1.
The isolation of zones improves the cloud's overall fault tolerance, decreases latency, and avoids creating a single shared point of failure. The availability zones and data centers within them are connected to other AZs and regions, private data centers, and the internet using very high bandwidth network connectivity. A cloud data center is a huge room or warehouse containing cloud infrastructure. These data centers contain pods and racks or standardized containers of computing resources, such as servers, as well as storage and networking equipment, virtually everything that a physical IT environment has. Computing resources. Cloud providers offer several compute options: virtual servers, bare metal servers, and serverless computing resources. Most of the servers in a cloud data center run hypervisors to create virtual servers or virtual machines, also called VMs for short, that are software-based computers based on virtualization technologies. Other servers in the racks are bare metal servers that are physical servers that aren't virtualized. Customers can provision VMs and bare metal servers as and when they need them and run their workloads on them. Cloud users can also run their workloads on serverless computing resources, which are an abstraction layer on top of virtual machines. We will talk about all three compute options in greater detail in subsequent videos.
Storage. Information and data can consist of files, code, documents, images, videos, backups, snapshots, and databases, and can be stored in many different types of storage options on the cloud.
Bare metal servers and virtual servers are provisioned with default storage in local drives. Since these cloud servers can be provisioned and decommissioned by customers on demand and freed up for use by other users, any information stored in a local drive can be lost when you delete or decommission a cloud server. However, there are other storage options available on the cloud to persist data that you can choose depending on factors like how important your data is, how quickly you want to be able to access it, how often you access it, and how secure you need it to be. These additional storage options include block storage, file storage, and object storage. Block and file storage modes are commonly used in traditional data centers, but often struggle with scale, performance, and distributed characteristics of cloud. Object storage is the most common mode of storage in the cloud, as it's both highly distributed and resilient. We will examine object storage and the other storage options in more detail in later videos. Networking. Networking infrastructure in a cloud data center includes traditional networking hardware like routers and switches, but more importantly, for users in the cloud providers have software-defined networking, or SDN, options where certain networking resources are virtualized or made available programmatically through APIs. This allows for easier networking provisioning, configuration, and management on the cloud. When servers in the cloud are provisioned, you need to set up their public and private network interfaces. The public network interfaces, as the name suggests, connect the servers to the public internet, where the private ones provide connectivity to your other cloud resources and help keep them secure. As in the physical IT world, network interfaces in the cloud need to have IP addresses and subnets either assigned automatically or configured. In a cloud environment, it is even more important to configure which network traffic and users can access your resources, which can be done by setting up security groups and access control lists, or ACLs. For further security and isolation of your resources in the cloud, most cloud providers provide virtual local area networks, or VLANs, virtual private clouds, VPCs, and virtual private networks, VPNs. Some of the traditional hardware appliances, such as firewalls, load balancers, gateways, and traffic analyzers, can also be virtualized and made available as services in the cloud. Another networking capability provided by the cloud providers is content delivery networks, or CDNs, that distribute content to multiple points throughout the world so users accessing the content can access it more quickly by getting it from a point nearest to them. We will learn more about some of these cloud networking options and terminology in subsequent videos. Cloud infrastructure is constantly advancing and improving. In the next video, we will explain virtualization and virtual machines.
Hi, my name is Kaylee Bovey with the IBM Cloud team, and today we're going to be talking about virtualization. As you know, virtualization is a fairly old technology, but it's still super relevant to building your cloud computing strategy today. So first off, what is virtualization? Simply put, virtualization is the process of creating a software-based or virtual version of something, whether that be compute, storage, networking, servers, or applications. And what makes virtualization feasible is something called the hypervisor. So we're going to write that here. And what a hypervisor is it's simply a piece of software that runs above the physical server or host. And there are a couple different types of hypervisors out there. And what they do is essentially pull the resources from the physical server and allocate them to your virtual environments. There are two main types of hypervisors out there, one being type 1, very simple to remember, and 2, you guessed it, type 2. So let's start with type 1. A type 1 hypervisor is a hypervisor that is installed directly on top of the physical server. They're also called bare metal hypervisors, so we'll write that up here, just so you can remember. These are the most frequently typed of used hypervisors, and they're most secure, they lower the latency, and these are the ones that you'll see in the market the most. Some examples would be VMware ESXi, or Microsoft Hyper-V, or even open source KVM. The other type of hypervisor is a type 2 hypervisor over here. And what makes these different is that there is a layer of host OS that sits between the physical server and the hypervisor. So, by that nature, they are also called hosted. These are a lot less frequent. They're mostly used for end-user virtualization, and you might see some in the market that are called like Oracle VirtualBox or VMware Workstation. Again, they're a lot less frequent. They're a bit more, they have a higher latency than a type 1 hypervisor. So once you have your hypervisor installed, you can build virtual environments or virtual machines, or simply put, VMs. So let's spin up some environments. So what makes a VM a VM? A VM is simply a software-based computer. They run like a physical computer, they have an operating system and applications, and they're completely independent of one another, but you can run multiple of them on a hypervisor. And the hypervisor manages the resources that are allocated to these virtual environments from the physical server. So, because they're independent, you can run different operating systems on different virtual machines. So you could run Windows here, or Linux here, or Unix here, for example. And because they're independent, they're also extremely portable. You can move a virtual machine from one hypervisor to another hypervisor on a completely different machine almost instantaneously, which gives you a lot of flexibility and a lot of portability within your environment. So looking at all of this, this is the core of virtualization as a process. So let's talk about a couple key benefits that you want to take away from this. One, cost savings. When you think about this, and the fact that you can run multiple virtual environments from one piece of infrastructure means that you can drastically reduce your physical infrastructure footprint. This is consolidation at its core, and the fact that you don't have to maintain nearly as many servers, run as much electricity, save on maintenance costs, means that you save on your bottom line at the end of the day. Number 2 would be agility and speed. So like I said, spinning up a virtual machine is relatively easy and quick. A lot more simple than provisioning an entire new environment for your developers if they say they want to spin up a new environment so that they can run a dev test scenario, whatever it might be. Virtualization makes that process a lot simpler and quicker. And 3, lowers your downtime. So let's say that this host goes out unexpectedly. The fact that you can move virtual machines from one hypervisor to another on a different physical server means that you have a great backup plan in place, right? So if this host goes down, you can simply move your VMs very quickly to another hypervisor on a machine that is working.
Virtualization and VMs are at the center of cloud computing and provide many benefits. In the next video, we will discuss the types of virtual machines. Virtual machines, or VMs, are also known as virtual servers, or virtual instances, or simply instances, depending on the cloud provider. The various cloud providers make VMs available in a variety of configurations and deployment options to serve different use cases. When you create a virtual server in the cloud, you specify the region and zone, or data center, you want the server to be provisioned in, and the operating system you want on it. You can choose between shared, that is, a multi-tenant VMs,
or dedicated, that is, a single tenant VMs. You can also choose between hourly or monthly billing and select storage and networking options for the virtual server. Now let's look at a few different types of VMs that can be provisioned in the cloud. Shared or public cloud VMs are provider-managed multi-tenant deployments that can be provisioned on demand with predefined sizes. Being multi-tenant means that the underlying physical server is virtualized and is shared across other tenants or users. To satisfy different workloads, cloud providers offer predefined sizes and configurations ranging from a single virtual core and a small amount of RAM to multiple virtual cores and much larger amounts of RAM. For example, there can be configurations for compute-intensive workloads, memory-intensive workloads, or high-performance I/O. Rather than pick from only predefined sizes, some providers also offer custom configurations that allow users to define the number of cores and RAM and local storage characteristics. Public VMs are usually priced by the hour, or in some cases, even seconds, and configurations start as low as pennies per hour. Some providers also let you get monthly VMs, which can result in some cost savings if you know you will run the VM for at least a month. But if you decide to decommission the VM in the middle of the month, you will still be charged for the full month. Transient or spot VMs take advantage of unused capacity in a cloud data center. Cloud providers make this unused capacity available to users at a much lower cost than regular VMs of similar sizes. Although the transient VMs are available at a huge discount, the cloud provider can choose to deprovision them at any time and reclaim the resources for provisioning regular, higher-priced VMs. Because you run the risk of losing these VMs when capacity in the data center decreases, these VMs are great for non-production workloads such as testing and developing applications. They are also useful for running stateless workloads, testing scalability, or running big data and high-performance computing workloads at a low cost. Reserved virtual server instances allow you to reserve capacity and guarantee resources for future deployments. You reserve desired amount of virtual server capacity, provision instances from that capacity when you need them, and choose a term, such as 1 year or 3 years, for your reserved capacity. You're guaranteed this capacity within the data center of your choice for the life of the contract term. By committing to a longer term, you can also lower your costs compared to hourly or monthly instances. This can be useful when you know you require at least a certain level of cloud capacity for a specific duration. If you exceed your reserved capacity, you can always choose to supplement your unplanned usage and capacity requirements with hourly or monthly VMs. Note, however, that not all predefined VM families or configurations may be available as reserved. Dedicated hosts offer single-tenant isolation. This means that only your VMs run on a given host, so they can make exclusive use of full capacity and resources of the underlying hardware. When provisioning a dedicated host, you need to specify the data center and pod in which you want your host placed. You then assign instances or virtual machines to a specific host. This allows for maximum control over workload placement. Dedicated hosts are typically used for meeting compliance and regulatory requirements or meet specific licensing terms. Virtualization and VMs are at the center of cloud computing and provide many benefits. In the next video, we will discuss bare metal servers, what they are, and what they provide.
A bare metal server is a single-tenant, dedicated physical server. In other words, it's dedicated to a single customer. The cloud provider actually takes the physical server and plugs it into a rack in a data center for customers. The cloud provider manages the server up to the operating system, or OS, which means if anything goes wrong with the hardware or rack connection, they will fix or replace it and then reboot the server. The customer is responsible for administering and managing everything else on the server. Bare metal servers are either pre-configured by the cloud provider to meet workload packages, or they can be custom configured as per customer specifications. This includes the processors, RAM, hard drives, specialized components, and the OS. Customers can also install their own OS and can install certain hypervisors that aren't available from the cloud provider, and thus create their own virtual machines and farms. With bare metal servers, you can also add GPUs, which are designed for accelerating scientific computation, data analytics, and rendering professional-grade virtualized graphics. Because bare metal servers are physical machines, they take longer to provision than virtual servers. Pre-configured builds of bare metal can take 20 to 40 minutes to provision, and custom builds can take around 3 or 4 hours. But these provisioning times can vary by cloud provider.
As bare metal servers are dedicated for use by a single client at any given time, they tend to be more expensive than similarly sized virtual machines.
Also note that unlike virtual servers, not all cloud providers provide bare metal servers. Since bare metal servers are fully customizable, they can do what a customer wants in the most demanding environments. Bare metal servers are dedicated and intended for long-term, high-performance use in highly secure and isolated environments. Clients have full access and control of bare metal servers because there's no hypervisor required. As there is no sharing underlying server hardware with other customers, bare metal servers fulfill the demanding needs of high-performance computing, or HPC, and data-intense applications that require minimal latency-related delays. These servers also excel in big data analytics applications and GPU-intensive solutions. Some workload examples that bare metal servers satisfy are ERP, CRM, AI, deep learning, and virtualization. If you use any applications that require high degrees of security control or apps that you've typically run in an on-premises environment, then a bare metal server is a good alternative in the cloud. When comparing bare metal servers to virtual servers, some of the most important considerations are found in customer need. Bare metal servers work best for CPU and I/O-intensive workloads, excel with highest performance and security, satisfy strict compliance requirements, and offer complete flexibility, control, and transparency, but come with added management and operational overhead. Whereas virtual servers are rapidly provisioned, provide an elastic and scalable environment, and are low cost to use. However, since they share underlying hardware with other virtual servers, they can be limited in throughput and performance.
As cloud environments gain greater adoption and digital data invites rapidly increasing cybersecurity threats, building secure networks on the cloud is crucial. Let's look at how we can build a secure cloud networking presence. As one might expect, the notion of building a cloud network is not much different from deploying a network in an on-premises data center. The main difference stems from the fact that in the cloud, we use logical instances of networking elements as opposed to physical devices.
For example, network interface controllers, or NICs, would be represented by vNICs in cloud environments.
In the cloud, networking functions are delivered as a service rather than in the form of rack-mounted devices. To create a network in the cloud, one starts by defining the size of the network or the IP address range that establishes the boundaries or the cloud network. Cloud networks are deployed in networking spaces that are logically separated segments of the networks using options, including virtual private cloud, or VPC, that in turn can be divided into smaller segments called subnets. Logically segmented cloud networks are private carve-out of the cloud that offer customers the security of private clouds and the scalability of public clouds.
Cloud resources, such as VMs or virtual server instances, VSIs, storage, network connectivity, and load balancers are deployed into subnets. Using subnets allows users to deploy enterprise applications using the same multi-tier concepts used in on-premises environments. Subnets are also the main area where security is implemented in the cloud. Every subnet is protected by access control lists, or ACLs, that serve as a subnet-level firewall. Within the subnet, one could create security groups that provide security at the instance level, such as VSIs. Once you build a subnet, then it is time to add some VSIs and storage to it so that you could run your applications. Let's say you have a 3-tier application that requires web access VSIs, application tier VSIs, and back-end database VSIs. In this case, we would place the web-facing VSIs into one security group, the application VSIs in a second security group, while the database VSIs in a third security group. It goes without saying that the web-facing VSIs need internet access. A public gateway instance is added to the network to enable users access to the application in the internet tier. While public gateways are great for internet access to the cloud, enterprises are interested in extending their own on-premises resources to the cloud by securely connecting them using virtual private networks, or VPNs. When building many subnets and deploying several workloads, it becomes necessary to ensure that applications continue to be responsive. That is achieved with load balancers that ensure availability of bandwidth for the different applications. Enterprises with hybrid cloud environment find using dedicated high-speed connections between clouds and on-premise resources is a more secured and more efficient way than public connectivity solutions. Some cloud service providers offer such connectivity, such as IBM Cloud and its direct link solution that enables extending on-premises resources to the cloud as needed. Building a cloud network entails creating a set of logical constructs that deliver networking functionality that is akin to the data center networks that all IT professionals have come to rely on for securing their environments and ensuring high-performing business applications. In the next video, we'll look at containerization technology and why containers have become a de facto element of cloud-native computing. Containers are an executable unit of software in which application code is packaged, along with its libraries and dependencies, in common ways so that it can be run anywhere, whether it be on desktop, traditional IT, or the cloud. Containers are small, fast, and portable, and unlike virtual machines, they do not need to include a guest OS in every instance, and can instead simply leverage the features and resources of the host OS. In the rest of this video, we will see how container-based technology really works.
Hi everyone, my name is Cy Venom, and I'm a developer advocate with IBM. Today, I want to talk about containerization. Whenever I mention containers, most people tend to default to something like Docker or even Kubernetes these days. But container technology has actually been around for quite some time. It's actually back in 2008 that the Linux kernel introduced C groups or control groups that basically paved the way for all of the different container technologies we see today. So that includes Docker, but also things like Cloud Foundry, as well as Rocket and other container runtimes out there. Let's get started with an example, and we'll say that I'm a developer and I've created a Node.js application and I want to push it into production. We'll take two different form factors to kind of explain the advantages of containerization. So let's say that first we'll talk about VMs and then we'll talk about containers. So first things first, let's introduce some of the things that we've got here. So we've got the hardware itself, just a big box. We've got the guest, or rather the host operating system, as well as the hypervisor. The hypervisor is actually what allows us to spin up VMs. Already, let's take a look at this shared pool of resources with the host OS and the hypervisor. We can assume that some of these resources have already been consumed. Next, let's go ahead and take this JS application and push it in. And to do that, I need a Linux VM. So let's go ahead and sketch out that Linux VM. And in this VM, there's a few things to note here. So we've got another operating system in addition to the host OS. It's going to be the guest OS, as well as some binaries and libraries. So that's one of the things about Linux VMs, that even though we're working with a really lightweight application, to create that Linux VM, we have to put that guest OS in there and a set of binaries and libraries. And so that really bloats it out. In fact, I think the smallest Node.js VM that I've seen out there is 400 plus megabytes, whereas the Node.js runtime and app itself would be under 15. So we've got that. We go ahead and let's push that JS application into it. And just by doing that alone, we're going to consume a set of resources. Next, let's think about scaling this out, right? So we'll create 2 additional copies of it. And you'll notice that even though it's the exact same application, we have to use and deploy that separate guest OS and libraries every time. And so we'll do that 3 times. And by doing that, essentially we can assume that for this particular hardware, we've consumed all of the resources. And there's another thing that I haven't mentioned here, but this JS application, I developed it on my MacBook. So when I pushed it into production to get it going on the VM, I noticed that there were some issues and incompatibilities. This is the kind of foundation of this big he said, she said issue where things might be working on your local machine and work great, but when you try to push it into production, things start to break. And this really gets in the way of doing agile DevOps and continuous integration and delivery. That's solved when you use something like containers. It's a 3-step process when kind of doing anything container related and pushing or creating containers. And it almost always starts with first some sort of a manifest. So something that describes the container itself. So in the Docker world, this would be something like a Docker file. In Cloud Foundry, this would be a manifest YAML. Next, what you'll do is create the actual image itself. So for the image, if you're working with something like Docker, that could be something, that'll be a Docker image. If you're working with Rocket, it would be an ACI or application container image. So regardless of the different containerization technologies, this process stays the same. And the last thing you end up with is an actual container itself, that contains all of the runtimes and libraries and binaries needed to run an application. That application runs on a very similar setup to the VMs, but what we've got on this side is, again, a host operating system. But the difference here, instead of a hypervisor, we're going to have something like a runtime engine. So if you're using Docker, this would be the Docker engine. And different containerization technologies would have a different engine. Regardless, it's something that runs those containers. Again, we've got this shared pool of resources, so we can assume that that alone consumes some set of resources. Next, let's think about actually containerizing this technology. So we talked about the 3-step process. We create some, a Docker file, we build out the image, we push it to a registry, and we have our container, and we can start pushing this out as containers. The great thing is these are going to be much more lightweight. So deploying out multiple containers, since you don't have to worry about a guest OS this time, you really just have the libraries as well as the application itself. So we've scaled that out 3 times, and because we don't have to duplicate all of those operating system dependencies and create bloated VMs, we actually will use less resources. So choose a different color here, and scaling that out 3 times, we still have a good amount of resources left. Next, let's say that my coworker decides, hey, for this JS application, let's take advantage of a third-party, let's say a cognitive API to do something like image recognition. So, let's say that we've got our third-party service, and we want to access that using maybe a Python application. So he's created that service that accesses that third-party APIs, and with our Node.js application, we want to access that Python app to then access that service. If we wanted to do this in VMs, I'm really tempted to basically create a VM out of both the JS application and the Python application, because essentially that would allow me to continue to use the VMs that I have. But that's not truly cloud native, right? Because if I wanted to scale out the JS but not the Python app, I wouldn't be able to if they were running in the same VM. So to do it in a truly cloud native way, essentially I would have to free up some of these resources, basically get rid of one of these VMs, and then deploy the Python application in it instead. And that's not ideal. But with the container-based approach, what we can do is simply say, since we're modulars, we can say, okay, just deploy one copy of the Python application. So we'll go ahead and do that. There's a different color here. And that consumes a little bit more resources. And then, with those remaining resources, the great thing about container technology, that actually becomes shared between all the processes running. In fact, another advantage, if these container processes aren't actually utilizing the CPU or memory, all of those shared resources become accessible for the other containers running within that hardware. So with container-based technology, we can truly take advantage of cloud-native-based architectures. So we talked about things like portability of the containers. We talked about how it's easier to scale them out. And then overall, with this kind of three-step process and the way we push containers, it allows for more agile DevOps and continuous integration and delivery.
Containers streamline development and deployment of cloud-native applications. In the next lesson, we will cover cloud storage. Cloud storage is where you save data and files in the cloud. Certain storage must be attached to a compute node before the storage can be accessed, whereas other storage types can be directly accessed either through the public internet or a dedicated private network connection. Cloud providers host, secure, manage, and maintain the cloud storage and associated infrastructure to ensure you have access to your data when you need it. Cloud storage services allow you to scale your capacity as you need, so you only pay for what you provision, usually on a per gigabyte basis. The cost of storage will vary by type, but in general, the faster the read-write speed of the storage, the higher the per gigabyte cost. Cloud storage is available in 4 main types: direct attached, file storage, block storage, and object storage. Direct attached storage, sometimes referred to as local storage, is storage which is presented directly to a cloud-based server and is effectively either within the host server chassis or within the same rack. This storage is fast and normally only used to store a server's operating system, although it can have other use cases. The main 2 reasons why direct attached storage is not so great for other uses besides to store the operating system is that it's typically ephemeral, meaning that it only lasts as long as the compute resource it's attached to. It cannot be shared with other nodes, and while you can use RAID techniques, it's not as resilient to failure as other types of storage. File storage is typically presented to compute nodes as NFS storage. NFS stands for Network File System and means that the storage is connected to compute nodes over a standard Ethernet network. NFS-mounted storage is commonplace, but it tends to be slower than either direct attached storage or block storage because the data travels over an Ethernet network. It also tends to be lower cost than either direct attached or block storage. One advantage of file storage is that it can be mounted or used on multiple servers at once. File-based storage is a simple, straightforward approach to data storage and works well for organizing data in a hierarchical folder structure that desktop users are familiar with. Block storage is presented to compute nodes using high-speed fiber connections, which means that read and write speeds are typically much faster and reliable than with file storage, making block storage suitable for use with databases and other applications where disk speed is important. You typically provision block storage in volumes, which can then be mounted onto a compute node, which it then effectively sees as another hard drive. Volumes can normally only be mounted onto one compute node at a time. With both file and block storage, you may also hear the term IOPS or IOPS. IOPS stands for Input-Output Operations per Second and relates to the speed of the storage, or to put it another way, how quickly data can be read from or written to the storage. We'll cover this in a little more detail in a later video. Persistence is a term that is used when provisioning file or block storage and relates to what happens to the storage once the compute node it is attached to is terminated. If the storage is set to persist, then it will not be deleted along with the compute node, meaning that it and its data are preserved and available to mount onto another compute node, though you will continue to pay for the storage. You can also, in some cases, set the storage so that it is automatically deleted with the compute node that it is mounted onto. In this case, as we know, it becomes ephemeral storage. Here, you will also stop paying for the storage, but you will lose any data unless it is backed up somewhere. There are several ways to back up data in the cloud, but one way to back up both file and block storage is to take a snapshot. As the term implies, this is a point-in-time image of the storage. Snapshots are usually fast to create. They don't actually write any data, rather they create metadata, don't require downtime, and subsequent snapshots record only changes to the data. They are great for returning storage to the way it was at a particular snapshot, though note they cannot be used to recover individual files. The fourth kind of storage is object storage. This is a different type of storage in so much as it's not attached to a compute node, rather it is accessed via an API. Of all the storage types, object storage is by far the cheapest and also the slowest in terms of read and write speeds, but it is infinite in size to the end user. Unlike file and block storage, where you provision a certain storage capacity and it fills up over time, with object storage, you can keep adding files to it and it never fills up. You just pay for what you use. This makes object storage a fantastic repository for all sorts of unstructured data types, large and small, including documents, videos, logs, backups, data from IoT, application binaries, and virtual machine images. In the following videos, there will be more detailed information on the different types of storage.
In this video, we're going to talk about file storage in greater detail. Like direct attached storage, file storage must be attached to a compute node before it can be accessed and have data stored on it. However, file storage can be less expensive, more resilient to failure, and involve lesser disk management and maintenance for you as the user to do, as compared to direct attached storage. You can also provision much larger amounts of file storage and present it as a disk to a server. File storage is mounted from remote storage appliances. That is, the physical disks are contained in a separate specialized piece of hardware, and they are then connected to the compute node via the underlying infrastructure in the data center. These storage appliances are not only extremely resilient to failure, the data is also far more secure in them, as these storage appliances offer services such as encryption in transit and encryption at rest. These appliances are all managed by the service provider. File storage is mounted to compute nodes via an Ethernet network, the same kind of network that you might receive email or browse the internet over, although this Ethernet network is normally dedicated to the task. This means it can sometimes be referred to as network attached storage, network file storage, or simply NFS. One of the issues with Ethernet networks is that their speed can vary. The more loaded an Ethernet network is, the more likely it becomes that its speed or bandwidth will be affected. Of course, cloud providers build their storage networks to handle very high volumes of traffic, but even so, consistent speed cannot be guaranteed. Therefore, file storage tends to be used for workloads where consistently high network speeds are not a requirement. In terms of workloads, file storage can typically be mounted onto more than one compute node at a time, where the mounted disk or volume looks just like another drive on the compute node. The ability for file storage to be mounted to multiple compute nodes at a time make it an ideal solution where some sort of common storage is required. For example, a departmental file share, a landing zone for incoming files that need to be processed by an application, or a repository of files that a web service might access. In these applications, the potential variance in the speed of the connecting network is not really an issue. Of course, where cost is an issue, you can use file storage for other applications, such as databases, but the trade-off is speed. When you provision file storage, one consideration you need to take into account is the IOPS capacity of the storage. IOPS stands for Input-Output Operations per Second and refers to the speed at which the disks can write and read data. Note, this is not the speed of the network between the storage and the compute node. The higher the IOPS value, the faster the speed of the underlying disk. A higher IOPS will also normally cost more. Understanding IOPS is important because if the IOPS value is too low for your application, the storage can become a bottleneck and cause your application to run slowly. Alternately, if the IOPS is too high, you will probably be paying more than you need to for your storage. For example, a file share may be mounted on 30 different compute nodes, and an application writes and requests data to and from that share 60 times per minute. You can average that out to 1 operation per second. With this simple example, you can see that each application has different IOPS requirements. In the next video, we're going to talk about block storage and how it compares with file storage and when you would typically use one over the other. In this video, we will discuss block storage and how it compares to file storage in the cloud. Block storage breaks files into chunks or blocks of data and stores each block separately under a unique address. Like direct attached storage and file storage, block storage also must be attached to a compute node before it can be utilized for your workloads. Block storage, like file storage, can be mounted from remote storage appliances, making it extremely resilient to failure and keeping data far more secure in them on account of encryption in transit and encryption at rest services available on these appliances. Block storage is mounted as a volume to compute nodes using a dedicated network of fibers through which signals move at the speed of light. These fiber optic networks are more expensive to build than the Ethernet ones which deliver file storage, which is one reason why block storage tends to have a higher price point. However, since the traffic is moving faster and with speed consistency, they are perfect for workloads that need low latency storage to work effectively. In terms of workloads, it is important to note that unlike file storage, which can be mounted onto 80 compute nodes or more, block storage is normally mounted onto only one compute node at a time. Since these disks run at a consistent high speed, they are perfect for workloads that need consistently fast storage, such as databases and mail servers. Block storage is not suitable for workloads where there needs to be some level of disk sharing between compute nodes. For block storage, as it is for file storage, you need to take the IOPS capacity of the storage into account. Most cloud providers will allow you to specify IOPS characteristics when you provision storage, and in some cases, adjust the IOPS of your storage as you need. So if the requirements or usage behavior of an application changes, you can adjust accordingly. So, to summarize the commonalities and differences between these two storage types, block and file storage is taken from appliances which are maintained by the service provider. Both are normally highly available and resilient and will often include data encryption at rest and in transit. File storage is attached to a compute node using an Ethernet network, so it is sometimes called network attached or NFS storage. File storage is very reliable, but the speed of the connecting network can vary based on load. Block storage is attached via a high-speed fiber network, which is very reliable and consistent. File storage can be attached to multiple compute nodes at once. Block storage can only be attached to one node at a time.
File storage is a good choice where file shares are required, where workloads do not require lightning-fast connectivity to storage, or where cost is a factor. Block storage is a good choice when supporting an application that needs consistent fast access to disk, such as databases. Remember to consider the IOPS requirements of the application when provisioning either file or block storage. In the next video, we'll start to look at object storage. In this video, we're going to start to understand what object storage is, how data is stored in object storage, and how it differs from the more traditional storage types such as file and block storage. The first thing to note about object storage is that you do not connect it to a particular compute node in order to use it. Instead, you provision an object storage service instance and use an API, or Application Program Interface, to upload, download, and manage your data. This means you can directly use object storage with anything that you can call an API, and you don't need an underlying compute node. The second thing to note about object storage is that it's less expensive than other cloud storage options. Its per gigabyte cost is typically a couple of US cents per month, and in some cases, even less, depending on the storage tier used. More on storage tiers later. The third and possibly most important thing to note about object storage is that it's effectively infinite. With file and block storage, you specify the size of the storage you want in gigabytes or terabytes, and then pay a fee based on the size you provisioned. With object storage, you just consume the storage you need and pay per gigabyte cost for what you use. You can keep uploading files and the storage will never run out. So when would you use object storage? Well, object storage is great for storing large amounts of unstructured data. By unstructured, this means that the data is not stored in any kind of hierarchical folder or directory structure. Object storage uses buckets, and objects are stored within these buckets in a structurally flat way. A bucket is a bit like a folder, in the sense that you can give them meaningful names, and of course have different buckets for different object types, but you cannot place a bucket within a bucket. When an object is placed in a bucket, it also has some metadata, data about the data, added to it, such as an object ID. This metadata helps applications to both locate and access the object, as well as provide information on the time that the data was stored or last accessed. When you create a bucket, you don't need to provide or define any sizing information. The bucket will just hold the data that you place inside it, and the service provider ensures that there is sufficient storage capacity available. Buckets can hold as little as a few bytes of data, right up to multiple petabytes, and you can build up the amount of data stored as slowly or quickly as you like, as well as shrink it back down again. The service provider also takes care of resilience and making sure that the object storage solution is highly available. Some cloud providers offer different types of buckets within different levels of resilience. For example, they offer buckets which are resilient, but the data is only stored in one data center. This is a good option where data needs to reside in a particular geographical location, or in situations where high availability is less of an issue. They will then offer buckets which are highly available across regions, where the data is stored multiple times in different data centers or zones in the same region or even in multiple regions. These options usually cost more, but they provide both the highest level of resilience as well as availability for your data. Object storage has a very flat storage structure, which we'll explain in the next lesson. This data can be anything from text files to audio files and video files, from IoT data to virtual machine images, from backup files to data archives. Pretty much any data which is static and where fast read and write speeds are not necessary would make a good fit for object storage. Object storage would, however, not be suitable for running operating systems, nor applications such as databases or anything else where the contents of the files changes. So, to summarize what we have learned in this lesson, object storage is used to store files, or objects, which are static. The data that you can store using object storage can be anything from text files to audio and video files, from IoT data to virtual machine images, from backup files to data archives. You cannot run operating systems or other applications, such as databases, using object storage. Objects are stored in buckets. You can have multiple buckets, but you cannot place buckets within buckets. You do not need to specify a size for a bucket. You can just use as little or as much space as you need. Many providers offer different types of buckets with different charges for each. Some are based on resilience and availability, while others are based on the frequency at which the objects inside are accessed. In the next video, we'll be diving into object storage data tiers and object storage APIs. In this video, we're going to look more closely at object storage data tiers and object storage APIs. Object storage buckets also have storage tiers, or classes, associated with them, and these tiers are based on how frequently the data is accessed. A standard tier bucket is where you would store objects that are frequently accessed. This tier tends to have the highest per gigabyte cost associated with it. A vault or archive tier is where you might store documents that are only accessed perhaps only once or twice a month or less, and this will be offered at a lower storage cost, whereas there may also be cold vault tier where you would store data that is typically accessed only once or twice a year. This storage often costs just a fraction of a US cent per gigabyte per month. Often, you can also set up automatic archiving rules for your data, meaning that if an object isn't accessed for a period of time, it will automatically be moved to a cheaper storage tier. The rule uses some of the object's metadata to determine when it should be archived. Note that object storage does not come with IOPS options. Object storage tends to be very slow in comparison with file or block storage, where downloads typically take seconds, if not longer, to complete. Where providers offer cold vault buckets, data retrieval from these tiers can sometimes even take hours because the storage is kept offline. If your application needs fast access to files, then object storage may not be a good option. We've mentioned that object storage is priced per gigabyte used, but there can also be other costs related to retrieval of the data. These costs are similarly low, but access charges can be higher for data that is in a vault or cold vault tiers, so it is important to ensure that the data is in the correct tier based on its frequency of access. Object storage does not need to be attached to a compute node for you to access it. Rather, you access object storage through an Application Program Interface, or API. The most common API for object storage is called the S3 API, which is a standard based on the S3 object storage offered by AWS. Many providers offer APIs to their object storage, which is S3 compatible, which is useful because it means developers can write code which is able to access multiple vendors' object storage. The API itself is an HTTP-based RESTful API or RESTful web service. The API call allows applications to manage object storage and buckets as well as put, upload, or get, download objects to and from them. Object storage is not just for new applications, but can be used to meet requirements for existing ones. It can also be used as an effective solution for backup and disaster recovery as a replacement for off-site tape-based solutions, reducing the time to restore data. Many backup packages now include the ability to back up data up into the cloud using object storage. Object storage is more efficient than tape backup solutions, which require tapes that need to be physically loaded into and removed from tape drives and moved off-site for geographical redundancy. So, to summarize what we have learned in this lesson, object storage has different tiers, with different charges for each. Some are based on the frequency at which the objects inside are accessed. Object storage is priced per gigabyte of storage used per month, plus some charges for data retrieval. Object storage is much cheaper than file or block storage. Object storage is very slow in comparison with file and block storage. You can often create rules which allow the automatic archiving of objects to cheaper tiers when they are infrequently accessed. Object storage is accessed using an API. Many object storage providers have an S3 compatible API, which means developers can create code that will work against multiple vendor object storage solutions. Object storage in the cloud offers an effective backup and disaster recovery solution.
In the next video, we will be covering Content Delivery Network, or CDN, which is driven by object storage.
A Content Delivery Network, or CDN, is a distributed server network that delivers temporarily stored or cached copies of website content to users based on the user's geographic location. A CDN stores this content in distributed locations and reduces the distance between your website visitors and your website server. In the rest of the video, we'll learn more about content delivery networks.
Hi, I'm Ryan Sumner. I'm a Chief Network Architect with IBM Cloud, and today I'm going to help you answer what is a content delivery network. So in short, a content delivery network, or CDN, is a service that accelerates internet content delivery. So in other words, the main benefit of a CDN is that it makes your website faster. So before I get into describing to you how it accomplishes that and some of the other benefits, first, I want to talk to you about some of the challenges that we have where we have users all around the world, but we don't have servers all around the world, and the experience that those users have due to that dynamic. So I've got a simple diagram here showing a server hosted down in Dallas. This is my website. And then I have users all around the world. So in Sydney, I might have 5. In London, I've got 5. New York, I might have 10. LA, I might have 10. I've got 30 users around the world that are accessing my server and my website down in Dallas. So let's kind of follow a set of these users in their journey. Let's look at the users down in Sydney. They make a request to the website. They've got an 8,600-mile hike to Dallas and then an 8,600-mile hike back. The amount of time that takes is usually measured in milliseconds, and just that round trip might be about 170 milliseconds. For our users up in London, that might be about 100 milliseconds. Our users in New York City can probably experience about a 40 millisecond round trip time, and over in LA, about 30. So as you can see, the further you're away, the longer it takes, ultimately, the slower the website will be for you. So this is where the CDN comes into play, and this is how it actually accomplishes the increase in speed, which is by reducing the amount of distance between the user and the content, or the server providing the content. So what it does by doing that is it places these content delivery network endpoints in as many locations around the world as possible, and in our case, we're going to assume we've got one in just about every location where our users exist. So now when the user in Sydney or London or New York City or LA tries to access some content, it's first retrieved by the Content Delivery Network service and then distributed around the world. So we have a single request down to the Dallas server. It's now then distributed all around the world, and our users in London now, instead of going all the way to Dallas, they're able to retrieve that content directly from their closest geographical location, drastically reducing the amount of time that it takes to retrieve that content. So as you can see here, it's very basic how a CDN is able to provide the benefits of to the end user by reducing the amount of time that it takes to deliver the service. But what you're not seeing here is an indirect benefit, is the reduction in the amount of traffic that actually hits the Dallas server. So the indirect benefit is that you actually see a reduction in the load, or a reduction in the amount of capacity that you need in Dallas to serve all these users. So Another indirect benefit, because of there's this much less validity and so much less stuff happening in Dallas, because all these users aren't having to make these trips, and I'm also not having to communicate with users so far away, the Dallas environment may also see an increase in uptime. And then lastly, because the users are not really directly communicating with the servers down in Dallas, you have the indirect benefit of an increase in security through obscurity. So it's pretty basic to understand how a CDN works, in the end, to provide a better benefit to the end user.
Hybrid cloud, as we covered in the previous lesson, is a computing environment that connects an organization's on-premise private cloud and third-party public cloud into a single infrastructure for running the organization's applications. Multi-cloud is a cloud adoption strategy that embraces a mix of cloud models from different service providers, public, private, and managed, across infrastructure, platform, or software services. For example, a business may consume email as a service from one provider, a CRM application from another, and infrastructure from yet another provider. So essentially, a hybrid multi-cloud implies you are able to leverage the best of cloud models and services across different service providers, and have your applications and workloads working seamlessly across multiple different clouds. In this video, we will look at some use cases for why a business may want to use a hybrid multi-cloud approach.
In this video, I want to touch on a few of those use cases for why a business may want to use hybrid or multi-cloud. Let's start with the basic one, cloud scaling. Now, most of us are probably familiar with this. It's one of the main reasons for adopting the cloud. Now, let's say we have a flower delivery service that is able to hit a certain bottom line of users. They have on-premise infrastructure, and it can hit a certain amount of user load. So visualizing this here throughout a calendar year, you can imagine that their load maybe goes up and down in response to specific holidays. Now, to hit those peaks, they could scale up their on-premise architecture, but that's met with upfront costs and costs of upkeep. Now instead, what they'll instead do is take advantage of cloud. That allows them to scale up in response to that load and then automatically deprovision resources when they no longer need them. Now, this concept is kind of general to cloud computing, not just hybrid or multi-cloud. But that brings me to my next topic. And here we're going to be talking about how it can be used to build a composite cloud. So essentially, this is going to be applications that are spread across multiple cloud environments. So back to the flower delivery service, let's say they have on-premise architecture that allows them to run 3 major components of their app. So let's say they have the web UI, they have some billing APIs, as well as a rewards framework. Now, let's say that this service is actually based in EU, and their European customers are happy. But for their North American or American customers, specifically around Veterans Day or Thanksgiving, they're noticing that the system is bogging down. And so they decide to take advantage of a hybrid cloud or multi-cloud architecture by composing their application across multiple cloud environments. So they'll take advantage of data centers in America, and essentially they've identified that although the rewards framework can stay on-prem in their European side, they want to move the billing and the UI capabilities over. So they'll move just those two to a cloud platform of their choice in a North American or American data center. This kind of allows them to scale up portions in response to, say, American holidays, while keeping their EU portions individually scaled. So in this example, the flower delivery service is able to take advantage of scaling at a global level by using the hybrid or multi-cloud architecture. Next, let's talk about the airline or travel industry. So we can first start with an example of modernization. Now, in the past, we've seen that reservation systems may have been difficult to work with, or you might have had to call in, but almost all the airline companies now have a mobile application. So most of the time, and we've actually found that it's about, in general, not just in the travel industry, but 80% of all enterprise applications are actually still on-prem. And that's likely the case in this industry as well. So in this specific example, let's say they have a reservation system that's running on-prem. But to create new experiences for their end users, let's say they've created a mobile application. That mobile app, of course, has a mobile backend that's maybe running in a public cloud. And that in turn works with the reservation service. So again, the mobile app can hit the mobile backend, and that in turn works with the reservation capabilities. So in this case, they've modernized and new user experiences are possible. But let's take that a step further. Now, a source for a lot of dissatisfaction for users is whenever their flights are delayed. So when a flight is delayed, they may have to rebook new flights. The solution is almost always the same. The traveler wants to get to his destination in the easiest way possible. So what airline industries have been doing is take advantage of the cloud to create maybe a recommendation feature. So it allows them to book new flights as soon as a delay is recommended or as soon as a delay is incurred, and that's going to connect up to that mobile backend service, allowing users to be able to book flights through their phone the second a flight is delayed. This not only improves the bottom line for the airline industry, but leads to happier users. So that's one way the modernization has been done. Next, let's take it even a step further and talk about data and AI. For data and AI, the airline industry has been taking advantage of lots of historical data. So over the decades that a company has been around, let's say they have historical data of when unplanned maintenance has happened on their airline. In fact, 30% of all delay time in the airline industry is actually when unplanned maintenance happens. So by taking advantage of, let's say, machine learning or AI capabilities, they could hook into all of the legacy data that they have, large volumes, and connect them up to machine learning and AI capabilities. This allows airline industries to take advantage of predictive analytics and get insights before errors or before the unplanned maintenance ever occurs. This again improves their bottom line, leading to happier users and a more efficient airline industry. Now, today we talked about 4 major use cases for hybrid and multi-cloud platforms. So cloud scaling and composite cloud in the Flower delivery service, as well as modernize and data and AI for the airline industry.
Another reason for adopting hybrid multi-cloud strategy is to prevent lock-in to a specific vendor's cloud platform and having flexibility of being able to move workloads from one cloud platform to another as the need arises. In the next video, we will understand what a microservices architecture is, its features, benefits, and use cases. Microservices architecture is an approach in which a single application is composed of many loosely coupled and independently deployable smaller components or services. These services typically have their own stack running on their own containers. They communicate with one another over a combination of APIs, event streaming, and message brokers. For a business, what this means is that application components can be developed and updated more efficiently by multiple developers working independently. Teams can use different stacks and runtime environments for different components. Components facing too much load can be scaled independently, reducing the waste and cost associated with having to scale entire applications. In this video, we'll look at how microservices have shaped application development and also look at a use case that illustrates microservices in action.
The way developers work to build applications is changing. In the past, software was built as large monolithic applications, where a team of developers would take months to construct a large application built on a common code base. These developers would write every part of the application from start to finish. Now, after decades of software development, there are vast amounts of code already out there that developers can use as the base of an application, meaning they no longer have to create every line of code from scratch. Cloud development platforms provide developers with an ecosystem of code that can be easily and securely integrated into applications. Now, instead of building one huge application on one team, developers break into small, independent teams where they write smaller amounts of code called microservices. Microservices break down large applications into their core functions. For example, search, recommendations, customer ratings, or product catalogs. Each is developed independently of one another, yet work together on the cloud development platform to create a functioning application. A container is the distribution method for each microservice, meaning it delivers the code where it needs to go. Containers are plug and play, so if one microservice isn't working for an application, developers can take it out and put in a different one without disrupting how the rest of the app functions. Check out microservices in action with Ron. Ron is a soccer fan who uses an online streaming media service called Dream Game. Last night, he missed watching his team play their crucial semi-final match. Luckily, he can watch the match tonight on Dream Game. When he logs in, he sees the most popular content among all Dream Game users. After some searching, he finds the match he's looking for. What he would really like is to find his game with one click. Luckily, the Dream Game development team is using microservices to develop a better user experience for viewers like Ron. The first microservice is a content catalog, housing the millions of games that Dream Game offers. The small team of developers organizes each piece of content with metadata that describes them. This metadata feeds into a second microservice, the search function, which ensures that Ron's search results are captured and compared to the Dream Game catalog. The third microservice, recommendations, captures data about the most popular content among all Dream Game users. This is what generates the homepage that Ron saw when he first logged in. These three microservices are all in their separate containers, ready to join the application. But before they can work together, they have to find one another. They do this by using something called service discovery, which creates a roadmap for these and many other microservices to communicate. When microservices find each other, they communicate using an application programming interface, or an API. So when Ron searches for his favorite soccer team, the search microservice is communicating to the content catalog, in an API, about what Ron is looking for. Now back to the goal at hand, to get Ron to his soccer game with just one click. The development team working on the recommendations microservice is updating the code, adding an analytics algorithm. Using analytics, the recommendations microservice will compare Ron's viewing history and preferences to popular content among other users, including soccer fans and viewers in Ron's geographical region and demographic. Since the developers didn't need to create the code from scratch, they are able to deploy this new functionality in a matter of days. These updates happen behind the scenes as the rest of the microservice containers function normally. The next time Ron checks Dream Game, instead of just seeing the most popular or newest content, he sees a personalized playlist that will continue to refine itself as the system learns more about his viewing habits and preferences. The result? Ron finds his favorite team's latest game right away. The microservice approach lets developers quickly innovate applications in parallel and lets users like Ron focus on the things that really interest them. And when those interests are changing and growing faster every day, microservices help businesses keep up and grow with their customers.
In the next video, we will talk about serverless computing, its features, benefits, and some use cases. Serverless is an approach to computing that offloads responsibility for common infrastructure management tasks, such as scaling, scheduling, patching, and provisioning application stacks to cloud providers, allowing developers to focus their time and effort on the code and business logic specific to their applications or process. Serverless doesn't mean there are no servers, only that the management of the underlying physical or virtual servers
is removed from their users. The serverless computing environment allocates resources as needed for the applications. Let's look at some key attributes that distinguish serverless computing from other compute models. The serverless model requires no provisioning of servers, installation of application stacks and software, or operation of the infrastructure by the developer. Serverless computing runs code only on demand on a per-request basis, scaling transparently with the number of requests being served. Serverless enables end users to pay only for resources being used, never paying for idle capacity, which is unlike virtual servers on the cloud, where end users pay for VMs as long as they are running, even if idle. Effectively, serverless abstracts the infrastructure away from developers. Code is executed as individual functions, where each function runs inside a stateless container. No prior execution context is required to serve a request, and with each new request, a new instance of the function is invoked. Let's look at a scenario. You could, for example, have a serverless platform between the front end of your website and your storage layer running individual functions. The serverless app could be translating text files and storing it in a cloud-based storage service. Using the front end of your website, you send text files to a serverless app. The app creates translations in different languages and then stores these translated files in a cloud storage and sends you their links back to you. Some of the key serverless computing services today include IBM Cloud Functions, which is based on Apache OpenWhisk, AWS Lambda, and Microsoft Azure Functions. It is important to note that serverless may not be the best fit for all applications or scenarios. You need to evaluate application characteristics and ensure that the application is aligned to serverless architecture patterns. Applications that qualify for a serverless architecture include some of the following characteristics: short-running stateless functions, seconds or minutes; seasonal workloads with varying off-peak and peaks; production volumetric data that shows too much idle time; event-based processing or asynchronous request processing for implementing use cases; microservices that can be built as functions that are stateless. Serverless architectures are well suited for use cases around data and event processing, IoT, microservices, and mobile backends. Given its inherent and automatic scaling, rapid provisioning, and a pricing model that does not change for idle time, supporting microservices architecture has become one of the most common use cases of serverless computing today. Serverless is well suited to working with structured text, audio, image, and video data around tasks such as data enrichment, transformation, validation and cleansing, PDF processing, audio normalization, thumbnail generation, and video transcoding. Parallel tasks such as data search and processing and genome processing are also well suited to be run on a serverless runtime. Serverless is also well suited for working with all sorts of data stream ingestions, including business data streams, IoT sensor data, log data, and financial market data. And finally, let's look at some challenges worth considering about serverless. Serverless workloads are designed to scale up and down in response to workload. But for workloads characterized by long-running processes, managing a traditional server environment might be simpler and more cost-effective. The serverless application architecture can be vendor-dependent, and so there is a potential for vendor lock-in, particularly involving platform capabilities such as authentication, scaling, monitoring, or configuration management. Because serverless architectures scale up and down in response to workload, they also sometimes need to start up from zero to serve a new request. For certain applications, this delay isn't much of an impact, but for something like a low-latency financial application, this delay wouldn't be acceptable. Simply put, a cloud-native application is an application developed from the outset to work only in the cloud environment, or an existing app that has been refactored and reconfigured with cloud-native principles. A cloud-native application consists of microservices working together as a whole to comprise an application, yet each can be independently scaled and iterated through automation and orchestration processes. These microservices are often packaged in containers, which are executable units of software in which the application code is packaged along with its libraries and dependencies so that it can be run from anywhere. The independence enables frequent iterative improvement of cloud-native applications without disrupting the experience of end users. Cloud-native applications are unlike traditional or monolithic applications that are built out of one huge piece of software. Applications that tightly couple the user interface, business logic layer, and data layer. Let's take the example of how a cloud-native application might be used on a travel website. Each topic covered by the site, flights, hotels, cars, specials, is its own microservice. Each microservice may roll out new features independent of the other microservices. Specials and discounts can also scale out independently. While the travel site is presented to customers as a whole, each microservice remains independent and can be scaled or updated as needed without affecting other services. Whether creating a new cloud-native application or modernizing an existing application, developers adhere to a consistent set of development principles. Follow the microservices architecture approach by breaking applications down to single-function microservices. Rely on containers for maximum flexibility, scalability, and portability. Adopt agile methods that speed the creation and improvement process through quick iterative updates based on user feedback. In this video, we'll take a closer look at the key concepts of cloud native, its benefits, and use cases.
Hi, I'm Andrea Crawford and I'm with IBM Cloud. So today we're going to talk about cloud native apps. In the heritage world, we have our lumpy, monolithic apps. And in the new world, we have our microservices living on the cloud. If we take a look at this diagram here, we see we have cloud infrastructure. This is your private, your public, and your enterprise infrastructure. Cloud native apps apply to hybrid and multi-cloud situations. We also have our scheduling and orchestration layer. This layer is all about control planes like our Kubernetes. We also have our application and data services layer. This layer is all about backing services and being able to integrate our application code with existing services that may be available on other clouds or even on-premise. We have our application runtimes. These are what were traditionally or conventionally known as middleware. And over here, well, that's where we have our cloud native apps. This is the sweet spot right up here. So our application code is actually designed, built, and delivered very differently for cloud native than it would be for conventional monolithic lumpy apps over here. So let's talk a little bit about why cloud native apps can actually leverage benefits like enabling innovation, business agility, and most importantly, from a technology perspective, the commoditization of this solution stack over here. So as time has progressed and technologies have matured and emerged, a lot of the services are actually being refactored lower down in this stack. This means that core services are starting to have a lower center of gravity, freeing up innovation at this level over here. So what are our use cases for when to build a cloud native app? Star everything. Everything that lives in the cloud should have a cloud-native app design and approach. This means our application code needs to be instrumented with things like standardized logging, standardized events, and being able to match those logging and events to a standard catalog that multiple microservices and cloud-native apps can use. The last thing we want to do is have our development squads have to figure out what their log and event messages should be. Let's standardize that because we want to be able to commoditize that as well. We also need to have things like distributed tracing. When we get over into the microservices world over here, we have a lot of moving parts. This means we're going to need to leverage services core to the system like load balancing, service discovery, and routing. These are the kinds of things that are commoditized in this layer here with things like Istio and with the emergence of newer projects like Knative. And so, if we were to recognize the benefits for cloud-native apps and to sum it all up, we are all about enterprise and engineering at scale.
In the next video, we'll take a look at DevOps. Development teams need to design, develop, deliver, and run software as reliably and efficiently as possible. Operations teams need to identify and resolve problems as soon as possible by monitoring, predicting failure, managing the environment, and fixing issues. Combining development and operations with the ability to monitor and analyze and optimize bottlenecks gives us DevOps, a collaborative approach where business owners and the development, operations, and quality assurance teams collaborate to continuously deliver software. A DevOps approach applies agile and lean thinking principles to all stakeholders in an organization who develop, operate, or benefit from the business's software systems, including customers, suppliers, partners. By extending lean principles across the software supply chain, DevOps capabilities improve productivity through accelerated customer feedback cycles, unified measurements and collaboration across an enterprise, and reduced overhead, duplication, and rework. Using the DevOps approach, developers can produce software in short iterations on a continuous delivery schedule of new features and bug fixes in rapid cycles. And businesses can seize market opportunities and reduce time to include customer feedback in their products. The DevOps process involves continuous delivery, which is about delivering small, well-designed, high-quality increments of software to customers. Continuous integration, creating packaged builds of the code changes released as immutable images, where immutable implies that when modifications are needed, the entire component is replaced with an upgraded version. Continuous deployment, which involves progressing each new packaged build through the deployment lifecycle as rapidly as possible. Continuous monitoring, with tools that help developers understand the performance and availability of their applications even before they are deployed to production. Delivery pipeline, which is an automated sequence of steps that involves the stages of ideation, coding, building, deploying, managing, and continuous improvement, which loops back to the ideation phase in the delivery pipeline. While DevOps can apply to applications anywhere, there is especially a compelling case for DevOps when it comes to cloud-ready and cloud-native applications. With its near limitless compute power and available data and application services, cloud computing platforms come with their own risks and challenges. DevOps tools, practices, and processes are helping tackle some of the complexities and challenges posed by the cloud and allowing solutions to be delivered quickly and reliably. Let's look at some core capabilities that DevOps provides to help building and running applications in the cloud a lot more manageable. DevOps best practices make it possible to programmatically provision servers, build middleware, install application code, and fully automate the installation process in a way that is documented, repeatable, verifiable, and traceable.
application deployments often involve considerable complexity. The DevOps practices of continuous integration and continuous deployment help create a fully automated deployment pipeline, which is important all through the application development lifecycle. Cloud-native applications form a complex, distributed system with multiple moving parts, independent tech stacks, and rapid release cycles. DevOps principles are essential to define how people work together to build, deploy, and manage applications in a cloud-native approach. With the DevOps best practices of automated provisioning and continuous deployment, developers, quality professionals, and other stakeholders can test in low-cost, production-like test environments that were previously not available, enhancing both productivity and quality. When systems are compromised or struggling to recover from natural disasters, DevOps best practices make it possible to rebuild these systems quickly and reliably. DevOps provides a powerful set of principles, practices, and tools to realize the full potential of cloud-native computing, as well as for modernizing existing applications to leverage cloud benefits. In the next video, we'll learn about application modernization. Many organizations have huge investments in existing applications that are often siloed in legacy systems and are very difficult and expensive to update and maintain. Modernizing these applications can unlock great benefits for these organizations, such as accelerating their digital transformations, enabling them to take advantage of new technologies and services, and becoming more responsive to their customers' needs and changing market dynamics. Cloud computing is one of the three main ingredients in application modernization. In the rest of this video, we will see how and what else application modernization entails.
Hi, I'm Eric Minnick with IBM Cloud, and I want to talk about application modernization and three huge transformations that have been going on together. So we've got three things going on, they're interrelated, and this is what we're seeing, this change in how we're doing architecture, infrastructure, and our ways of working, how we deliver. And if we go back in time a little bit, we saw applications that were very monolithic, they were running on physical servers, and we used waterfall style development where we'd have long plans and we'd say, okay, this is going to be our planning phase, our development phase, our testing phase, and we could plan out a year as a project. And that's really what we've gone away from. So if we look at how most organizations are working today, architecturally, they've got some sort of distributed architecture. It's usually related to like a service-oriented architecture, the big buzzwords a few years ago. But it's some sort of distributed architecture. We have a bunch of web services, they're talking to each other, we got some databases on the back end, and then some front ends that kind of go through all that. On an infrastructure level, they're running on some sort of a virtual machine, right? So we said, we could probably do better than having to order a new server every time we have a new service. Let's virtualize this stuff. And we need a little more density along the way. And from a way of working, agile development, pretty normal. And then trying to figure out a little bit of what happens downstream. So this kind of takes us up to where a lot of teams are today, but not really where they're going. And so if we look at kind of that next phase, we're taking another pass at this service-oriented architecture and really shrinking the sizes of the services, taking advantage of the more dynamic infrastructure we have. And we're calling these now microservices, right? Microservices. So we got a microservice architecture. So very small, very focused services, moving away from a lot of the heavyweight XML-based communication we saw in SOA, towards more REST-based communication, things like that. But same idea, let's keep breaking into smaller and smaller pieces. We have more independence of what we ship, more rigor in saying this service needs to be independent from another service so I can change these things by themselves. On the infrastructure side, cloud. Cloud's pretty popular. And this could be public cloud, this could also be private cloud. I'm painting with a very broad brush when I say cloud here. And then from a delivery and a way of working, we could say that DevOps is really key. And I would include in this approaches like site reliability engineering, SRE. More the ways of working we have today. Now, that's fine and interesting, but what do these things have to do with each other? And I'd argue that what we're really seeing is modernization in how the applications are delivered and how they're built, what they are. And while you could walk into any large enterprise today and you'll find someone who says, we are going through a cloud transformation. And you'll often find someone who says, yes, I'm in charge of leading the DevOps transformation. And you'll walk into enterprise architecture and they'll say, yes, we are pushing microservice architectures. Individuals think that they're going through 3 separate transformations, but they're really tied, right? If I'm doing microservices, right, and I have new microservices all the time, and in order to get a new microservice up and running, I'm over here and I have to order a new physical server and then rack and stack it a couple months later. I'm not going to get any time to market benefits. The resilience benefits that I'm going to normally look for from microservices are going to be modest at best. Right? Microservices want cloud infrastructure. You want to be able to say, I've got a new microservice. Let me put it in a container and just run that container right now and scale that dynamically. Similarly, cloud really likes running microservices. Right? The benefits of being able to dynamically scale are really cool when you have a lot of small things that you might need few of or a lot of. It's not as interesting when I've got a monolith that isn't even distributed. How do I scale that? I get a bigger cloud server? And then all of this is kind of baking in this idea of speed and resiliency. And DevOps brings that together, right? The developers who have always wanted speed, the operations people who've always wanted that resiliency, they're going to be programming that cloud, right? The programmable infrastructure the cloud provides needs operations people who understand resiliency, but bring some of that development skill in. And to really take advantage of these new infrastructures, the new architectures, you need these new ways of working. And you also are going to say, if this is going to give me time to market benefits, I can't be back here and say, yeah, no, we've got a 1-year project plan that we're just going to execute. I need to be able to be more agile and adapt in my planning and my responsiveness to the business. I need to better wire up my applications so they can be more easily monitored and more resilient. We have to have the application in a way that it knows when one of these services is failing and we can spin up another. So this is really, for me, fascinating, that you walk into these organizations everywhere and they're undergoing these 3 different transformations, but they're always doing them together. And when they don't, it doesn't quite work. So you've got these 3 transformations going on at once. And you'll hear us talk a lot about application modernization, right? See that written across the top here. And when I think of application modernization, I think it's just this. It's this transformation right here. Going from these kind of monoliths or service-oriented architectures to microservices, adopting cloud, modernizing our ways of working towards DevOps and SRE. That's AppMod, right? And it's a really exciting time, and it's really great when you're able to go after it in a holistic fashion.
Hi, I'm Nataraj Nagaratnam, and I'm from IBM Cloud. Traditionally, when you deploy an application, you have the entire data center, the servers that you run, you're responsible for all of it. In the cloud model, that's a shared responsibility between you and the cloud provider. In a shared responsibility model, you need to rethink security on what your responsibility is and what cloud provider's responsibility is. Let's take platform as a service as an example. When you look at PaaS, you're building applications, migrating data to the cloud, and building applications running on the cloud. So you're responsible for securing the applications, the workload, and the data, while the cloud provider is responsible for managing the security of the platform so that it's compliant, it's secured from the perspective of network, the platform on down in terms of managing the containers, the runtime, and the isolation, so that you have your own space within the platform. Whereas if you are adopting and migrating workloads to the cloud and you're using infrastructure as a service, then the cloud provider manages hypervisor on down if you are using virtual servers. Or if you're using bare metal, then you can completely control everything on up, from the operating system, the virtual servers that you run, and the data you bring it on. So it's very important to understand the adoption model, whether you're consuming IaaS or PaaS, or if you're consuming SaaS, where the cloud provider manages all the applications and the security of it, and you worry about the data that you bring in and plan accordingly. So that's a very important thing, because it's part of understanding your responsibility in ultimately managing the risk and compliance of the workloads and the data that you bring to cloud. Now, let's talk about architecture. When you build applications and migrate applications and modernize your apps, let's start with data. With all the risk that you deal with, and the kind of data matters. Is it confidential data? Is it public data or sensitive data that may deal with private information? Consider all those factors and make a secure design around what your data security architecture should be. Make sure you have data at rest encryption so that the data is always encrypted, whether you use a database as a service, object store as a service, or other ways to store data like block storage. Encryption is for amateurs. If you think about key management, that's for professionals. So having more control of your keys provide you the ability in the context of shared responsibility model that you own your data, you have complete control of your data. So as you think about key management, make sure you have an approach to think about if you're bringing confidential data, you want to bring your own keys. Maybe sensitive data, you want to keep your own keys. So that how much control of the keys you have and the hardware security module in which the key processing, the encryption, decryption operations happen, more control you have, more responsibility that you can take on. So encryption at data at rest, data in motion, as it comes from services to data stores or applications, so that as you think about data coming all the way, your requests and API requests coming all the way, data in motion. And in the new world, we need to start thinking about when the application is actually processing the data, there is going to be data in its memory. So you can actually start to protect data using hardware-based technologies where you can protect in-memory data as well. So that when it is in use and in memory by the applications, you can protect it. So take a holistic approach to data protection at rest, in motion, in use, with full control of your keys. It can be bring your own keys, or even better, push the boundary with keep your own keys. The application that serves the data, it's not only about which application needs to have access. Make sure the data access is on only a need-by-need basis. Do not open up your data services to the whole world, be it network access or everybody to access the data. Make sure you exactly know which applications need to access or which users need to access the data to run your cloud applications. From an application viewpoint, make sure there are no vulnerabilities in your application. So scan your applications. So have an AppSec application security approach so that you can do dynamic scanning or static scanning of your application before you deploy it into the production. And in a cloud native environment, you're deploying container images. So you can scan your images. You can scan it for vulnerabilities before you deploy and set your policy so that you only have secured images in production anytime. And if there is any vulnerability in the new world, you don't need to patch these systems. You just spin up a new container and off you go. So that's the beauty of a cloud native approach, where you have security built in every step. So at a container level and the applications that serves the business logic, you can start to protect it. Then when you look at the users coming in, you want to manage access in terms of who the user is and from where they are coming from. So identity, you need to make sure who the user is or which service it is based on the identity of those services or users, so that you can make access control to your application or data. And also from the perspective of network access, you want to make sure only authorized users can get in, and if there are intruders out there, you can make sure you can set it up so that they are prevented from accessing your application and your data in the cloud, be it through web application firewalling, network access control, or denial of service, distributed denial of service protection, and have intelligence built into these network protection as well. So both identity and network. In essence, you are protecting your data. You need to manage access to your apps and the workload and the data that you have deployed on the cloud.
In the next video, we will look at security monitoring and DevOps security.
You need to have a continuous security monitoring so that you know at any point whether you're compliant to your policies. You can watch out for threats that you need to manage. Having an approach and set of tools to manage security and compliance posture is very important. So gaining insights about your posture, compliance, and threats. So from your deployment environment, you can garner information. It can be security events, audit logs, flow logs from network or system that can be fed in so that you can figure out what your posture and compliance and threats are. And not only it's important for you to gain insight, you need to have actionable intelligence so that you can start to remediate. You may figure out there's a vulnerability, a container image that you have deployed is vulnerable, so you can respin the container, so you can remediate and spin up a new container. There may be a particular access from a network that seems to be coming in from a suspicious network IP address, so you can block that. So ability to gain visibility and insights, and having that insights and turn it into actionable intelligence and remediate is very important. So let's talk about DevOps. DevOps is about development and operations. Traditionally, we think about, okay, there's an application team that is doing the design and architecture, who are building code, and then you throw it over the wall for the enterprise security team to secure it and manage it. That should be rethought. Fundamentally, it's not just about dev and ops, but security need to be a forethought, not an afterthought. So it should become SecDevOps approach to the way you build, manage, and run your applications. So you need to embed security into the entire lifecycle, what we call shift left. Not only you manage security, but shift left through the entire process. You need to have a secure design, So as you plan, as you design and say, what kind of data am I going to put? What level of classification? What kind of applications am I building? Is it container-based? Is it a workload that I'm migrating? Take that into account and what integrations you need to do so that you can plan it and architect it. Then as you build it, embed security as part of the process. So you have security aware applications. For example, you may want to encrypt data. If it is sensitive data, you may want to encrypt the data from your applications before you store into a data store. So secure build, and you manage security. As part of SecDevOps, as you have secure design and architecture, you pass on that and build secure applications and deploy and manage security in a continuous fashion. And then you have a closed loop so that whatever you find, you may need to remediate or re-architect your application or re-implement certain things as threats landscape evolve.
In the next video, we will look at identity and access management. According to the 2019 Cloud Security Report by Cybersecurity Insiders, the top cloud security concern of cybersecurity professionals is data loss and leakage. Unauthorized access through misuse of employee credentials and improper access controls is the single biggest perceived vulnerability to cloud security, followed by insecure interfaces and APIs. In this video, we will look at how identity and access management, also known as access control, works as the first line of defense, allowing you to authenticate and authorize users and provide user-specific access to cloud resources, services, and applications. A comprehensive security strategy needs to encompass the security needs of a wide audience, including organizational users, internet and social-based users, third-party business partner organizations, and vendors. There are three main types of users: administrative users, developer users, and application users. Administrative users include cloud platform administrators, operators, and managers, roles that typically create, update, and delete application and service instances, and also need insight into their team members' activities. An attacker on an administrative account can steal data from production database service instances, deploy malicious applications inside the customer's domain, or even deface or destroy existing applications. Developer users include cloud application developers, platform developers, and application publishers. Developer users are authorized to read sensitive information and to create, update, and delete applications. The third type of user is the application user. These are the users of the cloud-hosted applications. Let's look at the key components of identity and access management and how they work. Authentication, or the identity service, enables applications deployed to the cloud to authenticate users at an application level, based on a range of identity providers such as the Cloud Directory, social identity providers such as Google, LinkedIn, Facebook, and Twitter, enterprise-hosted identity provider, and cloud-hosted identity provider. Sometimes API keys, or unique identifiers, are passed into an API to identify the calling application or user. Multi-factor authentication is used to combat identity theft by adding an additional layer of authentication for application users, such as single-use passwords or PINs, certificates, tokens, risk-based authentication, such as changes in the user's location, past activity, and preferences. Cloud Directory services are used to securely manage user profiles and their associated credentials and password policy inside a cloud environment. A directory service within a cloud means that applications hosted on the cloud do not need to use their own user repository. Reporting helps provide a user-centric view of access to resources or a resource-centric view of access by users. Reports typically give information about which users have access to which resources,
which users have changes in access rights, which access is being exploited by each user, and under which conditions. Audit and compliance is a critical service within identity and access management framework, both for cloud provider and cloud consumer. Auditors use these processes to validate implemented controls against an organization's security policy, industry compliance, and risk policies, and to report deviations. User and service access management capability enables cloud application and service owners to provision and deprovision customer, partner, and vendor user profiles with minimal human interaction. This streamlines access control based on the role, organization, and access policies defined by the owner. User accounts of administrators or developers give access to sensitive information. In order to mitigate the risks of these accounts being hacked into, you require maximum control over the whole life cycle of these users. Some of the controls that can help secure these sensitive accounts include provisioning users by specifying roles on resources for each user, password policies that control the usage of special characters, minimum password lengths, and other similar settings, multi-factor authentication like time-based one-time passwords, and immediate deprovisioning of access when users leave or change roles. Cloud providers offer identity access and management services, typically including the ability to create access groups, add users to access groups, and manage access for existing users. An access group is a group of users and service IDs created so that the same access can be assigned to all entities within the group with one or more access policies. Access policies define how users, service IDs, and access groups in the account are given permission to access account resources. Policies include a subject, which can be users, service IDs, or access groups, a target, which is the resource or provision service offering to which you want to provide access, and role, which defines the actions allowed on the target of the policy, that is, the resource to which the access is being granted. Access groups provide a more streamlined access assignment process as compared to assigning individual access to each user and help reduce the number of policies in an account. In this video, we learned how identity and access management work as the first line of defense to secure the cloud. In the next video, we will learn about cloud encryption. Given the concerns around data security and privacy, especially in public cloud environments, encryption plays a key role and is often referred to as the last line of defense in a layered security model. This protection not only encrypts data, but also provides robust data access control, key management, and certificate management. In this video, we will take a closer look at cloud encryption. Encryption is defined as scrambling data in a way that makes it illegible. There are two parts to an encryption system, the encryption algorithm and the decryption key. The encryption algorithm defines the rules by which data will be transformed so that it becomes illegible, and the decryption key defines how the encrypted data will be transformed back to legible data. Encryption ensures that only authorized users have access to sensitive data, and when accessed or intercepted without authorization, data is unreadable and meaningless. Cloud providers offer various cloud encryption services. This could be limited encryption of data that is identified as sensitive, or end-to-end encryption of all data uploaded to the cloud. Data is encrypted upon receipt, and encryption keys are passed to the customers to decrypt data when needed. Keys need to be managed securely. If you lose your keys, you will not be able to read your data. Data needs protection in 3 states: at rest, in transit, and when it is in use. Encryption at rest protects data while it is physically stored in a database or the storage layer. Depending on the application and business requirements, there could be multiple options for encrypting data at rest, such as encryption for block and file storage, built-in encryption in object storage, and database encryption services. Encryption in transit protects data while it is transmitted from one location to another. Encryption in transit includes encrypting the data before transmission, authenticating endpoints, and decrypting and verifying data on arrival. Secure Sockets Layer, or SSL, and Transport Layer Security, TLS, are commonly used protocols for encryption in transit. They are not only used when accessing websites securely, but also for data moving between servers and services within the cloud. Encryption in use protects data when it is in use in memory for computations. It allows computations to be performed on encrypted text without needing to decrypt the data. Cloud storage encryption could be server-side or client-side. Server-side encryption occurs after cloud storage receives your data, but before the data is written to disk and stored. For server-side encryption, you can either create and manage your own encryption keys, known as customer-supplied encryption keys, or you can generate and manage your encryption keys using key management services offered by the cloud storage provider, known as customer-managed encryption keys. Client-side encryption occurs before data is sent to cloud storage. This way, users can utilize encryption keys and algorithms that are not visible to the cloud provider, making it virtually impossible for cloud providers to decrypt hosted data. Given that a majority of enterprises today operate in multi-cloud environments, there is a need to implement a singular data protection strategy across an enterprise on-premise, hybrid, and multi-cloud deployments. Some cloud providers offer multi-cloud data encryption services with a range of features such as data access management, integrated key management, and sophisticated encryption that combine to deliver the scalability and flexibility to help protect the most sensitive workloads across the enterprise, regardless of where the data resides. Using a multi-cloud data encryption console, you can define and manage access policies, create, rotate, and manage encryption keys, and aggregate access logs. Encryption does not eliminate data security risk. It separates the security risk from the data itself by moving security to the encryption keys. These keys need to be managed and protected against threats in order to keep the data secure. Key management services offered by some cloud providers help perform lifecycle management for encryption keys that are used in cloud services or customer-built applications. They enable customers to encrypt sensitive data at rest and to easily create and manage the entire lifecycle of cryptographic keys that are used to encrypt data. Since the keys remain in possession of the customer, the data is protected from cloud service providers as well as from other users. Some of the best practices for encryption key management include storing encryption keys separately from the encrypted data, taking key backups off-site and auditing them regularly, refreshing the keys periodically, implementing multi-factor authentication for both the master and recovery keys. In the next video, we will learn about cloud monitoring and its benefits. Cloud-based deployments can be complex. Monitoring performance across an entire stack of applications and services can be time-consuming and draining on internal resources. This is where cloud monitoring solutions come in. Cloud monitoring solutions assess data, application, and infrastructure behaviors for performance, resource allocation, network availability, compliance, and security risks and threats. Cloud monitoring is not just about automated tools. It includes the strategies, practices, and processes that need to be in place for analyzing, tracking, and managing cloud-based services and applications. It also serves to provide actionable insights that can help improve availability and user experience. Cloud monitoring helps to accelerate the diagnosis and resolution of performance incidences, control the cost of your monitoring infrastructure, mitigate the impact of abnormal situations with proactive notifications. Get critical Kubernetes and container insights for dynamic microservice monitoring. Troubleshoot your application and infrastructure. Cloud monitoring solutions are designed to give organizations visibility and control over their entire cloud-based infrastructure. They provide data in real time with round-the-clock monitoring of virtual machines, services, databases, and applications. Multi-layer visibility into application, user, and file access behavior across all cloud-based applications and services. Advanced reporting and auditing capabilities for ensuring regulatory standards are being met. Large-scale performance monitoring integrations across multi-cloud and hybrid cloud environments. One way to categorize cloud monitoring tools solutions is to break them down into infrastructure, database, and application performance monitoring. Infrastructure monitoring tools help identify minor and large-scale hardware failures and security gaps so that the developers and administrators can take corrective action before problems affect user experience. Database monitoring tools help track processes, queries, and availability of services to ensure the accuracy and reliability of database management systems. Application Performance Monitoring, or APM, measures application availability and performance, providing tools needed to troubleshoot issues in an application's environment. APM solutions help improve user experience, meet application and user service level agreements, or SLAs, minimize downtime, and lower overall operational costs. To get the most benefit from your cloud-based deployments, you can follow some standard cloud monitoring best practices. Leverage end-user experience monitoring solutions to capture the performance of an application from the point of view of its end users. These solutions monitor user journeys to track parameters such as application response time and frequency of use under varied conditions. These insights will help you to improve customer experience significantly. Consider moving all aspects of your infrastructure, whether in private, public, or hybrid clouds, under one unified monitoring platform. This can help you to manage all your KPIs in one place with complete visibility into performance optimization. Use monitoring tools that can help you track the usage and cost of your cloud resources and services. Increase cloud monitoring automation. This can help you gain significant operational efficiencies. Simulate outages and breach scenarios to evaluate how well your monitoring tools capture and alert against failures. Cloud monitoring needs to be a priority for organizations looking to leverage the benefits of cloud technologies. It will help you manage and optimize your cloud resources for cost and performance and create better customer experiences. In this video, we will look at some case studies that demonstrate the use of cloud computing in real business scenarios and the ensuing impact on these businesses and the customers they serve.
The weather company's mission is to map the atmosphere of the Earth and based on that generate the most accurate and hyper-local forecast which can be served out to all our consumers and devices, which number in millions across the globe.
Weather is unpredictable, and we need to be able to spin up and spin down as fast as weather happens.
Our normal day-to-day load is 30 million unique users, and when we peak into severe weather, that can go north of 100 million across our products.
So we generate forecasts on demand, and our forecast on demand system is responsible for generating forecasts at a resolution of 1 square kilometer grid.
We deliver forecasts on demand to the tune of 250 billion per day.
On the backside of that is our API platform, and that system operates at the scale of about 150,000 requests per second. If our products don't work and don't work fast, people's lives are in danger.
Imagine a hurricane is approaching east coast of the United States. As it is approaching the coast, usage of my weather data goes up tremendously. It can go up from anywhere from 2 times to 5 times.
It took us 6 months to migrate into IBM Kubernetes from our previous provider, and what we've noticed is some real efficiencies with DevOps. It's reduced our workflow and pipeline by about 80%.
With the latest hurricane, we were able to scale with IBM Cloud very easily, very seamlessly. IBM's Kubernetes service allows us to scale as fast as the weather happens.
As we migrated our web platform to IBM Cloud Kubernetes services, one of the biggest advantages is that this is a managed service,
which allows our team not to have to babysit our system, enables them to do other work.
With the migration to IBM Cloud Kubernetes, we've gained the ability to have automation, security baked in. This was a feature and a component that was very manual for us in the past.
IBM's security team proactively now notifies us of any security vulnerabilities.
The tools and the investment that the company's made gives us capabilities that we would have never had before. It gets us very excited, and it gives our developers and engineers opportunities to build new things that they wouldn't have otherwise been able to do. The global reach that IBM and the IBM Cloud, together with our technology, with our capabilities for forecasting, give us the ability to extend our products and services to keep people safe all over the world.
Good afternoon, ladies and gentlemen. Welcome aboard. Captain speaking. Pretty much anticipating on-time arrival.
In the scenario where there's a flight cancellation or some other off-schedule operation, we've had a system where we find new seats and flights availability for those customers. But I think oftentimes customers didn't necessarily know that that was the best option for them. What we wanted to do was create a system where they could actually see alternate options.
The goal was to facilitate a better experience for our customers on how to get to their destination in an automated fashion on the channel of their choice. In our business, hurricanes, storms, other natural events impact our customers on a fairly regular basis. What happened, and this is a true story, the hurricanes hit, and everybody said, this is ridiculous. Our customers were being impacted by the hurricanes immediately. Why are we mitigating risk of a traditional rollout when we have the power of the cloud? And this is exactly the scenario that our customers need this capability.
I think people will now realize that these kind of activities and integration are much easier when we can use cloud technology, and especially microservices. We can break problems into much smaller problems, and those get much easier to wrap your head around and develop.
This is the technology that we need to be adopting now in order to keep pace with our customer expectations.
What I loved about my job at Cementos Pacasmayo is that it challenges me every single day. Technology moves so agile that I have to keep up with it. And what I love is that the company is also on that same road, driving towards its digital transformations. Our customers are now demanding quicker time to market and also a more broad portfolio of products. We need to keep up and deliver like the best service and the best products that they can get in the least amount of time. We implemented SAP S/4HANA on IBM Cloud since it brings us a cost-effective infrastructure and also it's quite scalable. Cementos Pacasmayo is now turning from a product-driven company to a service-driven company. The accounting area now has real insights on real time of our financial statements that they didn't used to have. And also on our supply chain area, especially on the procurement. They now have the dashboard that helps them take decisions right on time.
My name is Mukesh Sharma, and I'm the Senior Manager of IT at Welch Food. Welch's started as an organization 150 years ago, and pretty fast it became the national drink. We're owned by the farmers. It's a co-op, and we value the sweat equity our farmers put into it. So that's what drives us every day, that our farmers are working out on the farms, and we're working here to make sure the organization gives the best benefit of each dollar spent back to them. Welch's IT is the heart of the business. All the manufacturing systems, any manufacturing data which comes in through different processing, ERP systems, and you name it. So we started this journey with the private cloud, and then at the same time we have started the process of asking ourselves on any new application request, can it be run in the public cloud? The approach we have taken is slowly and steadily start to move these non-mission critical systems which can be done better by somebody else, let them run outside, let them spend time on it while we spend time on our core values.
Liquid Power is a company that sells products
that when you inject them into crude oil or gasoline pipelines, it changes the flow characteristics to such a point that you can either, one, increase the flow of those fluids, or secondly, use less energy to actually push the fluids down the pipeline. We needed to become a standalone company under Berkshire Hathaway. Without any experience in running our own infrastructure, or SAP, we had to come up with the solution that was best for our business to operate as a standalone company. So there were many decisions we had to make. Do we go cloud? Do we stay on premise? How do we create our own infrastructure and back office? And what's the best decision for us, not only today and now, but in the future going forward? So I talked to some CIOs and IT professionals. If you had a blank sheet of paper, what would you do? Cloud or go on premise? Without a doubt, all of them say cloud. This whole process and the migration to the cloud is giving what we believe is a competitive advantage. And what I really love about having IBM with SAP on the cloud is it's scalable. We can do it much faster and change in a much faster time period than we could otherwise.
Cloud computing is a key part of an enterprise's digital transformation strategy. As more and more companies are moving critical business processes and applications to a mix of cloud infrastructures, qualified cloud computing professionals are in high demand. According to Gartner's report on the cloud services industry, from a market size of $182.4 billion USD in 2018 to a projected market size of $331.2 billion USD in 2022, the market size and growth of the cloud services industry is at nearly 3 times the growth of overall IT services. That is the scale at which the cloud market is growing. Employer demand is outpacing the number of qualified candidates available. Gartner Talent Neuron's database of more than 1 billion unique job listings scores the hiring scale for jobs requiring cloud computing skills at 78, which means that employers are finding it difficult to get the right applicants for open positions in cloud technologies. There are many specialization areas within this domain. Here's a look at some of the common roles available currently. Cloud developers or cloud software engineers work through all phases of the software development lifecycle, writing, testing, and maintaining the code. They work with the front and back end of applications, as well as platforms and systems that their applications run on. Cloud developers need to have a mix of technical skills, business knowledge, and experience with at least one of the major cloud providers. Technical skills for a cloud developer would typically include knowledge of data structures, distributed systems, operating systems, and algorithms, experience with databases, proficiency in commonly used web application development languages such as Python, JavaScript, Java, HTML, and CSS. Cloud integration specialists are responsible for integrating new cloud services, applications, and infrastructure into the organization's portfolio of internal systems and existing cloud services. These specialists assess the implications and trade-offs between different solutions as they relate to the integration between external and internal systems, optimize integration and user experience, and ensure that performance standards adhere to service-level agreements set with the enterprise. Cloud data engineers are responsible for designing, developing, and deploying scalable data pipelines and data services. They look at integrating new data management technologies and software engineering tools into existing infrastructure. Their responsibilities include understanding existing systems to recommend automated integration of disparate data sets, collaborating with data scientists and researchers to develop predictive models and proofs of concept, promoting best practices that enable teams to accelerate their consumption and understanding of data, improving overall efficiency by introducing new engineering processes and tools. Cloud security engineers provide expertise around the systems and processes needed to protect the confidentiality, integrity, and availability of an organization's systems and application data. They determine security requirements, plan, implement, and test security systems, perform threat simulations to detect possible risks, recommend innovative technologies that will enhance the security of cloud-based environments.
Cloud security engineers need to have deep knowledge of cloud platforms and services, software design patterns, and DevOps tools and methodologies. Cloud DevOps engineers collaborate with development and operations teams to create reliable and rapid release pipelines for software and updates. This may typically involve creating custom automation tools, building and maintaining configuration and deployment frameworks, tracking design bugs, and automating the debugging process for developers, maintaining and deploying web-based applications, monitoring security systems, measuring performance against expected business outcomes. Containerization expertise is increasingly a must-have for DevOps engineers. Cloud solutions architects work to translate business requirements into application architecture and design. Some of the technical skills required for a cloud architect role include deep knowledge of cloud platforms and services, deep understanding of software design patterns, knowledge of DevOps tools and methodologies, good understanding of networking, a high-level understanding of key security concepts. Solution architects work closely with cloud developers, networking specialists, security engineers, integration specialists, and DevOps engineers to architect and design solutions. There are several resources available for learning cloud technologies in a variety of delivery methods, including instructor-led courses, self-paced online courses, online videos, books, and also technology-focused community forums. Many cloud providers have dedicated learning portals with extensive resources available on the complete range of cloud technologies and services they provide. They offer learning paths, which make resources available as per specific career roles, hands-on learning labs with interactive learning resources that can be filtered by role, level, or product, free trials on their suite of products and services.
Welcome to IT Technical Support Case Studies and Capstone. Congratulations on completing all the courses in the Technical Support Professional Certificate Program. Now you get to show what you've learned and apply it to the types of situations that tech support specialists confront daily. This course has two main sections. During this course, you will first work through a series of technical support case studies that require hands-on work to resolve. Each module will include practice case studies and one graded case study. The case studies cover topics from the previous courses. And after you complete the case studies, you will demonstrate your preparedness for the CompTIA ITF Plus exam by taking a mock version of it. Your exam will include the same number and types of questions as the CompTIA's exam and cover the same topics. Fortunately, you have been studying these topics throughout this professional certificate program, and you will review many of them by completing the case studies. Module 1 draws from the Introduction to Hardware and Operating Systems course. Its case studies cover topics such as computer hardware, peripherals, connectivity, performance, and operating systems. Module 2 draws from the Introduction to Software, Programming, and Databases course. Its case studies cover topics such as browser versions, browser security, software updates, and database fundamentals. Module 3 draws from the Introduction to Networking and Storage course. Its case studies cover topics such as servers, VPNs, firewalls, SOHO networks, and hosted storage. Module 4 draws from the Introduction to Cybersecurity Essentials course. Its case studies cover topics such as intellectual property, information privacy, password management, multi-factor authentication, cyber threats, and safe browsing. And Module 5 draws from the Introduction to Cloud Computing course. Its case studies cover topics such as cloud service models, cloud deployment models, VPCs, IAM, and cloud storage. The case studies throughout each module will also require you to apply your knowledge of technical support basics. These basics include, but are not limited to, levels of support and escalation, ticketing systems and other support tools and systems, and communication and customer service skills essential for effective technical support. In addition to applying your knowledge to realistic situations, you'll demonstrate your preparedness for the CompTIA ITF Plus exam by taking a mock version of it. Like the real exam, the mock exam covers topics you have been studying throughout this professional certificate program, and you will have reviewed many of them by completing the case studies. Your mock exam will include the same number and types of questions as CompTIA's exam and cover the same topics. And when you successfully complete all the courses in this program, you'll receive dual credentials, a professional certificate to showcase your job readiness to potential employers, and an IBM digital badge to help your profile stand out. Oh, and after successfully finishing this course, you will receive a 30% discount voucher for the CompTIA ITF Plus certification exam and access to other study materials. We are excited to have you join us and hope you enjoy the course. Good luck, and let's get started.